Please be seated. It is my distinct honor as president of Gustavus Adolphus College to welcome you to this, the 49th Nobel Conference at Gustavus. As we officially open the conference, I would like to introduce one of the college's chaplains, Reverend Siri Erickson, for the invocation. But before I do so, I would like Chaplain Siri to stand along with Chaplain Brian Conkle. We have two new chaplains. This is quite a tradition at the Nobel Conference. In fact, the first director of the Nobel Conference was Chaplain Elvey. And what a pleasure it is to welcome these two new chaplains to this great institution. Chaplain Siri is a graduate of Carleton College, where she was Phi Beta Kappa and majored in chemistry. She received her Master of Divinity degree from the Claremont School of Theology. And before coming to Gustavus, Reverend Erickson served as pastor for lifelong learning at Trinity Lutheran Church in Stillwater. Chaplain Brian is a graduate of Viterbo University in La Crosse, Wisconsin, and he graduated from Luther Seminary and has served on two different occasions as a missionary, first in South America and then for 7 years in South Africa. Most recently, he served as a parish pastor in Madison, Wisconsin. We welcome both of you. Chaplain Siri, would you please join me at the podium as we welcome you?
Let us join our hearts and our minds together in a moment of gratitude. Compassionate and creative God, we give thanks for the beauty and magnificence of this universe and for our human capacity to explore its deepest mysteries. As we journey together in an epic adventure of truth-seeking, may we be challenged to expand our vision of the world. May we be dazzled by the wonders of scientific knowledge. And may we remain curious and open to a future of continued discovery. With gratitude for the scientists who are presenting at this conference, for their passionate pursuit of knowledge about the universe, and for their dedication to teaching and learning, we pray today with full hearts. Amen.
Thank you, Chaplain Siri. This year's Nobel Conference theme, The Universe at Its Limits, is, I believe, especially illustrative of the college's commitment and the commitment of our faculty to tackle cutting-edge topics from an interdisciplinary perspective and explore their philosophical and their theological implications. This year's theme and focus has generated tremendous excitement and an unusually high demand for tickets, as well as a significant interest on the web streaming of the conference. On Sunday evening, we had the largest attendance ever for the preview dinner and lecture done by Dr. James Gates, held at the Science Museum of Minnesota to introduce the conference to the business leaders, the nonprofit executives, educational leaders, and media representatives, and our alumni and friends in Minneapolis and in St. Paul. Gustavus's annual National Nobel Conference was the first educational conference of its kind in the United States and continues to be the only such conference of its magnitude at an undergraduate liberal arts college today. This year's conference marks the fourth year of a very special year-long outreach program for high school students and teachers throughout the state of Minnesota. The program was first funded through a grant from the Howard Hughes Medical Institute, and this year it is funded by the Catherine B. Anderson Fund of the St. Paul Foundation. We are taking advantage of this year's conference topic to enhance high school senior curriculum in the state and to better prepare participating teachers and their students for the conference. Engaging high school students and teachers has long been a hallmark of the conference. Of the over 5,000 individuals who will attend the two-day conference here in St. Peter, approximately 1,700 will be here from high schools all over the region, Minnesota and contiguous states. And this year we have 8 teachers from 8 different high schools in this program, in the Minnesota program that we have. And many of those students are attending the Nobel Conference today, and others are joining us tomorrow, as well as many other students from all over the state. I want to direct your attention to the students here. I believe they're seated in the balcony area, and I'd like to have them stand so that we can welcome them to this, their first Nobel Conference. Would you please stand? As we approach the 50th Nobel Conference at Gustavus, I think it is important to remind ourselves of how the conference began. The college was planning to build a new science building during its centennial year. For some of you alums, you will remember that. It was in 1962. Then President Edgar Carlson traveled to Sweden to ask the Nobel Foundation if, when a new science building is completed, whether we could name the building the Alfred Nobel Hall of Science, and they agreed. We have the Nobel Hall of Science. He was bold enough to ask the foundation then that when the building would be completed in 1964, if we could possibly invite all of the living Nobel laureates to St. Peter here on a hill in a small town in Minnesota, looking over the river valley. That was pretty visionary, wasn't it? 26 Nobel laureates came to St. Peter for what was the first such gathering of science scholars and is now the Nobel Conference at Gustavus. Today we are celebrating the fact that we have now had a total of 100 Nobel laureates visit our campus since that first conference. After conferring the honorary degrees here in a short while, over 100 laureates will have received an honorary degree from the Gustavus. I think that's pretty special. You might look at the banners along the wall that are from the earlier conferences. So when you have time between the lectures, you might want to walk around and remind yourself of those. I'm always amazed of how many people attend year in and year out and how many new ones we have coming. So a simple test here. Let's just raise our hands if this is our first Nobel Conference. That's great. Wow. You're in for a great experience, and please come back. For those who have been here for more years than one, please raise your hand. Wow, that's really great. And now the real test, and I know there are a few here. Of those seated, how many have been to every Nobel Conference? Please stand so we can recognize you. They're right over here. Right over here. Isn't that great? Thank you. I also think it is important to point out that the Nobel Conference at Gustavus has been made possible over the years through very significant and generous support. I call your attention to the descriptive materials in the program that outline the fact that the Nobel Conference Endowment Fund was originally created in July of 1978 and has been permanently secured now as a result of the generous support of the Reverend Drell and Adeline Bernardson. Other gifts to the endowment fund are listed in the program, and I hope you'll look through that. We also want to acknowledge the 2013 sponsors of the Nobel Conference, and they are listed in the program. One of our sponsors is Heroic Productions, owned by Gustavus alums John and Anita Young. Heroic Productions is truly heroic. They provide the extraordinary media production you are enjoying in this arena today, and thousands more will be able to view the conference remotely, and because of their tremendous work. We thank you, John and Anita, for all that you do for the college. At Gustavus, we believe the Nobel Conference represents all that is good about a liberal arts education in an undergraduate residential college environment. Today, more than ever before, questions are being asked about the value of a liberal arts education. Many are wanting to quantify education by comparing the value of education at one institution versus another by looking solely at what many call the return on investment, ROI. You've read it in the newsprint. You've seen it on television. Education cannot be quantified by simply looking at the jobs graduates receive or the salaries they are paid. We believe Gustavus is a place where there's return on investment, but we need to look at much more than the simple economics being discussed around the country. We believe we need to be talking about ROI, but also ROE, the return on a Gustavus education for a lifetime. The Nobel Conference and other opportunities for our students provide them with a deeper understanding of their place in the world and how they can make a difference. The learning outcomes of liberal arts education demonstrates how that education will be lived out over a lifetime by our students. Our alumni are the living proof of the real return on investment, the return on a Gustavus education. Thank you for being here to take part in this significant learning opportunity for all of us that will help enrich our lives as we expand upon our education and live out our lives meaningfully in an ever-changing world. I would hope that all of us, as we learn about the universe at its limits, would be mindful of the opportunities we have had as individuals and we have had collectively to stretch beyond our limits because of the education we have received. Now, it is my pleasure to introduce three outstanding Gustavus faculty who help students stretch beyond the limits. First, I want to introduce Dr. Steve Mellema, Professor of Physics. Steve, would you please stand? Steve is the chair of this year's conference, and you will meet him later. He will be moderating some of the discussion. He and his colleagues have worked tirelessly for more than a year now to organize this year's conference. Thank you, Steve, for all that you and your colleagues have done. Secondly, I would like to introduce and have Dr. Chuck Niederreiter stand. Chuck is a professor of physics. He has served for the last 5 years as director of the Nobel Conference and is stepping down this year from the director's position, a role that he has served admirably and brought significant strength to this program and to this college. In the conference's 49th year, we have had only 3 Nobel Conference directors. Chuck, on behalf of all of us at Gustavus, including the Board of Trustees, the faculty, staff, and students, and I might add the thousands that have attended the Nobel Conferences over the past 5 years, we say thank you. Finally, I would like to ask Dr. Scott Burr to stand. Scott is an associate professor of chemistry, and he will serve as the next director. Pretty big shoes to fill, Scott. He will serve as the director this next year. He has been working with Chuck and with Steve and all of their faculty colleagues over the last year to think about ways we can continue to build upon the strong traditions of the past 49 years. Next year, as I mentioned, will be the 50th year for the Nobel Conference. You will be receiving information, and I think there's actually some flyers in the back about the 50th Nobel. We will be looking retrospectively over the last 49 years as we begin to look at the next 50 years of the Nobel Conference and the tradition that we have. You will be delighted when you hear more about the programs from Scott and his colleagues. Scott, thank you for accepting this responsibility. I now ask, before we recognize three distinguished Nobel laureates with honorary degrees, to have Provost Mark Braun come to the podium. Provost Braun is in his third year now at Gustavus as provost, and he is leading a tremendous faculty. He is an individual that served on this faculty for 17 years before he left here for a little time away as the Chief Academic Officer at Augustana College in Sioux Falls. We are so pleased to have him here, and he will be making his remarks and introducing Dr. Niederreiter for his conference overview. Mark?
Thank you, President Oley. Could I ask the faculty to please rise? On behalf of the faculty of Gustavus Adolphus College, we welcome all of you to this 49th Nobel Conference. Thank you, faculty. It is consistent with our mission as a liberal arts college that we annually invite to the conference speakers and panelists who approach the subject from many perspectives. The process begins with conversations on campus, designed to identify and refine a topic, and assemble a Gustavus faculty committee to explore the best scholars in the world to address that topic. The conversation then expands to include our invited speakers, who present their unique perspectives as the talks are designed and coordinated. And now that we are all assembled here, the conversation really takes wing. We will come to a deeper appreciation of the topic through the presentations, through the dialogue among the panelists following each lecture, and through the questions from our audience. I invite all of you, the on-campus audience, and the online viewers worldwide, to actively join in the conversation on the universe at its limits. Now it's my pleasure to invite to the podium to launch our conversation the director of the Nobel Conference, Gustavus Physics Professor Dr. Charles Niederreiter.
It is my pleasure to welcome everyone to this, the 49th installment of the Nobel Conference, The Universe at Its Limits. For those of you who are with us for the first time, a special welcome. For nearly 50 years, the Nobel Conference has specialized in important scientific issues and their relevance to contemporary society. For myself and my colleagues in physics, this is our dream conference. What could be more noble than attacking the questions of the origins, constituents, and evolution of our universe? Or what could be more challenging? Leave it to the physicists. Those of us who made it to the end of an introductory astronomy course realize that the seemingly opposite lines of inquiry that began in ancient Greece over 2,000 years ago astronomy, and the study of what is inside matter both provide answers to the questions of the origin, constituents, and evolution of the universe. Indeed, we need both astronomy, the study of what is outside, beyond the boundaries of Earth, and the study of the realm of subatomic particles and the fundamental forces in nature in order to put together a coherent picture of our universe and how it got this way. The Nobel Conference 49 Committee has put together a panel of experts in both areas to help us answer questions about dark energy and the acceleration of the universe, to candidates for dark matter and its role in holding the whole thing together. Embedded in all of this are questions about how it all got started that initiate a discussion of the relationships between science and faith. At this time, let's meet our speakers. Dr. Frank Wilczek, Herman Feshbeck Professor of Physics at Massachusetts Institute of Technology and a 2004 Nobel laureate in physics, will get us started thinking about the connections between the very large and very small and the basic rules of our universe. Dr. Taras Shears, Professor of Physics at the University of Liverpool and Royal Society University Research Fellow at CERN, will tell us about research at the Large Hadron Collider and perhaps about the discovery of the Higgs boson. All right, we have a little problem with order here. Okay, I think I figured it out. Alex Filippenko is the Richard and Rhoda Goldman Distinguished Professor in the Physical Sciences in the Department of Astronomy at the University of California, Berkeley. And Dr. Alex Filippenko will talk to us about his research in the accelerating expansion of the universe. We'll hear about the quest to identify dark matter from Dr. Samuel Ting, Thomas Dudley Cabot Institute Professor of Physics at MIT, and a 1976 Nobel laureate in physics. Dr. George Smoot is Professor of Physics at the University of California, Berkeley, Senior Scientist at Lawrence Berkeley National Laboratory, and Professor of Physics at Paris Diderot University, and he won the Nobel Prize in Physics in 2006. Professor Smoot will help us understand what we can learn about the early universe from leftover radiation from the Big Bang. Dr. Lawrence Krauss, Foundation Professor of the School of Earth and Space Exploration and Director of the Origins Project at Arizona State University, will give us an idea what science can tell us about the origin of the universe. The Emeritus Director of the Vatican Observatory, Father George Coyne, who is currently McDivitt Chair of Religious Philosophy at Lemoyne College, will help us explore the relationships between the religious view of the origin of the universe and that of science. Dr. Sylvester James Gates, Jr. is the Regents Professor, John S. Toll Professor of Physics, and Director of the Center for String and Particle Theory at the University of Maryland. As this year's Rydell Professor at Gustavus, he has already started getting us to think about the underlying symmetry of the universe, and I hope that he will continue with his lecture at our banquet tomorrow evening. I also would like to acknowledge one of the leaders in exploration of the universe, Dr. Vera Rubin. Dr. Rubin was the first to recognize the existence of dark matter in her studies of rotational velocities of stars and galaxies. We invited her to be with us, and after initially accepting, she later informed us that her health wasn't good enough for her to travel to St. Peter. We wish her well and hope that she enjoys watching the conference on her computer. Our panel of speakers was put together by a committee chaired by my colleague Steve Mellema, as President Oley said. Steve had help from our colleagues in physics, Tom Huber and Jesse Petrika, as well as colleagues in math and computer science, Tom LaFaro and Mike Vidston, and from chemistry, Steve Miller and Larry Potts. You will meet them and other faculty hosts over the course of the next 2 days. I need to also acknowledge the assistance of a myriad of students who have helped or are helping in various ways. At this time, I'd also like to call your attention to other events taking place on campus with the Nobel Conference. At 6 p.m. tonight, our Art at the Nobel Conference reception at the Hillstrom Museum of Art, featuring String Theory and the Superconducting Supercollider series, paintings by Lucinda Mason, just to name a few. And at 8:15 this evening, the Nobel Conference concert, Dark Energy in Christ Chapel. Professor Yumiko Oshima Ryan has put together a real treat for us. As we continue to evaluate the Nobel Conference at Gustavus, we ask you to take a little time to fill out a survey to help us in this endeavor. A link to this survey will appear on the Nobel Conference website on Thursday and will be emailed out to those for whom we have email addresses. So once again, welcome to all of you. We're looking forward to an exciting 2 days. If you've been with us before, you probably know of the Gustavus tradition of bestowing honorary degrees on Nobel laureates who visit campus. So at this time, I'd like to call to the platform Professor Samuel Ting and citator Professor Huber for the conferral of the first honorary degree.
Stand right over there.
President Oley, Provost Braun, Deans Good and O'Loughlin, distinguished panelists, faculty, and Nobel Conference guests. Today, Gustavus Adolphus College honors Nobel laureate Samuel Ting, the Thomas D. Cabot Professor of Physics at MIT. Dr. Ting has dedicated his career to experiments exploring the fundamental constituents of the universe. His ability to identify challenging areas for research and then assemble a large international collaboration to achieve difficult physics goals is remarkable. His experiments have been critical in the development of the Standard Model and exploring physics beyond the Standard Model. In the early 1970s, Dr. Ting assembled a collaboration with a nearly unprecedented goal: to build a high-resolution electron-positron spectrometer that could operate with the intense proton beam at Brookhaven National Lab. As with all of his subsequent experiments, construction of this detector took tremendous creativity and attention to details. In 1974, this persistence was rewarded with their discovery of the J particle, which provided direct experimental evidence for the existence of the charm quark. Dr. Ting shared the Nobel Prize in 1976 for this discovery. Dr. Ting was the leader of the L3 collaboration at the LEP accelerator at CERN. From 1989 until LEP shut down in 2000 to make room for the LHC, the L3 collaboration involved hundreds of scientists from 50 institutions worldwide. Under Dr. Ting's leadership, the L3 collaboration performed high-resolution studies of the Standard Model predictions and performed searches for physics beyond the Standard Model. Dr. Ting's most recent and possibly most ambitious project was the construction, launch, and operation of the alpha magnetic spectrometer on the International Space Station. Only a physicist with Dr. Ting's stature and tenacity could have navigated the complicated technical and political challenge of this project. Design and construction of the $1.5 billion detector involved 500 scientists from 16 countries. Even after it was fully constructed, it took an intensive lobbying effort by Dr. Ting to convince NASA, the President, and Congress to add one final space shuttle flight of Endeavour to transport the detector to the space station. Although it has been in operation for only 2 years, this detector has provided tantalizing hints about the nature of dark matter in the universe. President Oley, for his contributions in experimental particle physics, the faculty of Gustavus Adolphus College recommends that Samuel Ting be awarded the honorary degree Doctor of Science.
Now, by the virtue of the authority vested in me by the Board of Trustees of Gustavus Adolphus College and upon the recommendation of the faculty and approval of the Board of Trustees, I hereby confer upon you, Dr. Samuel Ting, the degree of Doctor of Science, honoris causa, with all the rights, privileges, and honors pertaining thereto. This is wonderful. Thank you so much.
My notes, but okay. Now I'd like to call to the platform Professor Frank Wilczek and citator Professor Vidson for the conferral of the second honorary degree.
Thanks for checking.
President Oley, Provost Brown, Deans Good and O'Loughlin, distinguished panelists, faculty, and Nobel guests. Today, Gustavus Adolphus College honors Nobel laureate Frank Wilczek, the Hermann Feshbach Professor of Physics at MIT. Frank Wilczek received the Nobel Prize in 2004 for work he did as a graduate student at Princeton University when he was only 21 years old. He, along with his advisor, David Gross, developed the theory of quantum chromodynamics, also known as QCD. Their theory, independently developed by David Pulitzer, who also shared the prize in 2004, describes the strong interactions which govern the behavior of quarks, ever so tiny particles that combine to make protons and neutrons, the basis for all of the matter that we see around us. The Nobel Foundation, in presenting this award, stated, "The discovery which is awarded this year's Nobel Prize is of decisive importance for our understanding of how the theory of one of nature's fundamental forces works, the force that ties together the smallest pieces of matter, the quarks. David Gross, David Pulitzer, and Frank Wilczek have, through their theoretical contributions, made it possible to complete the standard model of particle physics, the model that describes the smallest objects in nature and how they interact. At the same time, it constitutes an important step in the endeavor to provide a unified description of all the forces of nature, regardless of the spatial scale, from the tiniest distances within the atomic nucleus to the vast distances of the universe," end quote. Dr. Wilczek has received many awards and honors for his outstanding work in theoretical physics. He was named a MacArthur Foundation Fellow in 1982. He was elected to the National Academy of Sciences in 1990 and was awarded the Lorentz Medal by the Royal Netherlands Academy of Arts and Science in 2002. He holds honorary degrees from The Ohio State University and the Maria Curie Sklodowska University, among others. Frank Wilczek has worked on an unusually wide range of topics, including condensed matter physics, astrophysics, and particle physics. He has helped to reveal and develop axions, anyons, asymptotic freedom, the color superconducting phases of quark matter, and other aspects of quantum field theory. He is an active writer, not only of scholarly papers in theoretical physics, but also of works aimed at translating the sometimes overly dense language of mathematics and physics into stories and adventures to which we can all relate. He has published 3 popular books: Longing for the Harmonies, written with his wife Betsy, Fantastic Realities, and The Lightness of Being. President Oley, for his contributions to developing the theory of quantum chromodynamics, the faculty of Gustavus Adolphus College recommends that Frank Wilczek be awarded the honorary degree Doctor of Science.
Now, by the virtue of the authority vested in me by the Board of Trustees of Gustavus Adolphus College, and upon the recommendation of the faculty and the approval of the Board of Trustees, I hereby confer upon you, Dr. Frank Walczek, the degree of Doctor of Science, honoris causa, with all the rights, privileges, and honors pertaining thereto.
Finally, I'd like to call to the platform Professor George Smoot and citator Professor Petrika for the conferral of our last honorary degree.
President Oley, Provost Braun, Deans Good and O'Loughlin, distinguished panelists, faculty, and Nobel Conference guests. Today, Gustavus Adolphus College honors Nobel laureate George F. Smoot III, Professor of Physics at the University of California, Berkeley, and Paris Diderot University. Professor Smoot shared the 2006 Nobel Prize in Physics with John Mather for, quote, their discovery of the black-body form and anisotropy of the cosmic microwave background radiation, end quote. In the mid-1970s, Professor Smoot and his collaborators developed a proposal for a satellite to study the cosmic microwave background, the radiation left over from the Big Bang. This mission, known as the Cosmic Background Explorer, or COBE, was launched into orbit on November 18, 1989, and contained 3 instruments. One was an instrument to measure the spatial variations, or anisotropies, of the microwave background. A second instrument was to measure precisely the spectrum of this background. And a third instrument was to measure the infrared background. Professor Smoot was the principal investigator of the instrument used to search for anisotropies. This instrument spent a number of years mapping the temperature across the sky, a task made more difficult by the need to remove nearby galactic sources and the Doppler effect produced by the motion of the Earth. This was done to a resolution of better than 50 microkelvin in temperature and 10 degrees spatially in the sky. In April 1992, the COBE team announced that their map had, for the first time, seen density variations that could serve as seeds for galaxies and galactic clusters to the then evolving universe, as temperature variation seen now directly correlates with the density variation of the early cosmos. Professor Smoot continues his research in cosmology and is involved in the Planck mission, a third-generation experiment to map the cosmic background. In addition, he is the author of more than 200 scientific articles and co-authored the book Wrinkles in Time, which detailed his efforts. His other honors include the 1991 NASA Medal for Exceptional Scientific Achievement, the 1995 Lawrence Award, the 2003 Einstein Medal, and the 2009 Oersted Medal. President Oley, for his contributions to observational astrophysics and cosmology, the faculty of Gustavus Adolphus College recommends that George Smoot be awarded the honorary degree Doctor of Science.
Now, by the virtue of the authority vested in me by the Board of Trustees of Gustavus Adolphus College, and upon the recommendation of the faculty and approval of the Board of Trustees, I hereby confer upon you, Dr. George Smoot, the degree of Doctor of Science honoris causa with all of the rights, privileges, and honors pertaining thereto. What a wonderful opportunity to recognize three outstanding scholars. Let's give all three a round of applause again. As we close this opening ceremony of this magnificent 49th Nobel Conference at Gustavus, it is my pleasure to welcome to the podium Reverend Brian Conkle to close the ceremony with a blessing. Following his blessing, we will leave the podium, go down, take a break, get everything set up. We're not going to leave the auditorium. We're going to start right into the first presentation so you can stand and rest and relax and meet some of the folks that are next to you. This truly is a great day at Gustavus Adolphus College, and it's a wonderful opportunity to invite and to have these individuals here at our institution for this great day. Chaplain Brian.
Receive the blessing. Spirit of life, subject of many possibilities, object of many identities. As the wheel of stars move above us, the plates of the earth shift below us, the web of neurons reposition within us. We give thanks for those beautiful moments in time when cosmic possibilities become our experienced realities. May we all be so blessed that we may honor this time together in the spirit of integrity and intrigue, so that our collective gifts may be animated, facilitated, and agitated. So we may remember who we are, lift up what matters most, and to be set free to explore the many possibilities of life in its fullness. So let it be so let us be blessed. Amen.
Thank you, Brian. What a great start, huh? Great start. Chuck, good job. Thank you. Well, of course, yeah. Right. I'll get the Zoom. Yeah, so yeah, we'll go through there first. And then, anything else you might need? No. Well, very good, very good.
Okay.
So is this the...
Okay, folks, I'd like you to find your seats, please. We are going to get this started very quickly. At this time, I'd like to introduce my colleague Mike Vidston from the Department of Math and Computer Science to formally introduce Frank Wilczek.
Was I speaking over before? Was I understand? Just a few hours north of St. Peter lies one of the most pristine wilderness areas in the country, the Boundary Waters Canoe Area. At night, there are no city lights, no house lights, no lights at all to obscure the dazzling complexity of the starry sky. The Milky Way stretches from horizon to horizon. Jupiter shines like a small moon. It is impossible not to wonder at the twinkling stardust, so infinitesimally small to our eyes, yet so incredibly stupendously distant. We see the universe at its limits on a still, dark night. a mystery, a riddle on the grandest scale. Frank Wilczek is a man well acquainted with the mysteries of the universe. As a child, he loved puzzles and games, so it was no surprise that he pursued a degree in mathematics at the University of Chicago, and subsequently graduate work in mathematics at Princeton. It was at Princeton that he learned of new work in theoretical physics that involved deep concepts from the mathematics of symmetry, in particular the gauge theory that was being used to describe electroweak interactions. He soon began work with a young professor named David Gross on the peculiar behaviors exhibited by subatomic objects called quarks. Quarks are the building blocks of protons and neutrons, thus of matter itself. Wilczek returned to the notion of gauge theory to model and thus explain the wild antics of quarks. For this work, he was awarded the Nobel Prize in 2004. Two things are immediately clear from even a brief review of Professor Wilczek's work. First, the sheer output of professional activity is truly stunning. Dr. Wilczek has published hundreds of research articles in a broad sweep of areas in modern physics. He has given invited talks at major universities and research institutions throughout the world. He has a rare gift for clear and engaging expository writing, with publications in Nature, The New Scientist, Physics Today, and Scientific American, as well as 3 popular books about physics. The second thing that is clear about Professor Wilczek's work is that it is infused with a sense of wonder about the world, a curiosity about what makes the universe tick. In his book, The Lightness of Being, he takes us on a journey from the Pythagoreans in ancient Greece with their motto that all is number, to the discovery of quarks and QCD, and finally to the frontiers of modern physics. It is a fascinating story. Professor Wilczek's playful and creative mind is evident throughout his career. In his book, Fantastic Realities, he describes how he came to predict the existence of a new particle called an axion. Axions might be the answer to the mystery of dark matter. When describing the origin of the name axion, Dr. Wilczek writes that, quote, "I named them after a laundry detergent since they clean up a problem with axial currents." Returning to the wilderness in our starry northern sky, we imagine all those throughout history who looked up in wonder and asked the question, what is it all about? This is the question at the heart of Frank Wilczek's work. It is my great honor and pleasure to introduce him today. Please join me in giving him a warm welcome.
It's lovely to be here, and lovely to have this cap to protect my hair-challenged skull from the sun. But we're enclosed here, so I can forgo that. Today, I'm going to talk about the universe at the limits of mind and matter, where mind meets matter in the subject of geometry. Geometry originated in very practical concerns. In fact, the word geometry derives literally from earth measure. But geometry took on a life of its own as people discovered it could be interesting, something you could play with, and that it led to very beautiful things. Perhaps the first great, beautiful discovery in geometry was Pythagoras' theorem about the sums of the squares of the lengths of the two smaller sides of a triangle, right triangle, being equal to the square of the largest side, or hypotenuse. We don't know exactly how Pythagoras proved that, but it's very likely to be something like this. This proof, by the way, was the subject of a wonderful story by Aldous Huxley called Young Archimedes, where young Archimedes, this genius, Guido, discovers it. He's 9 years old or something, and draws the picture and says, so simple. He sees Pythagoras' theorem in a glance, just looking at these figures. Let's spell it out a little bit if we're not quite young Archimedes. These two squares have the same size, and furthermore, they share in common 4 little colored right triangles. That means that if you take away the 4 right triangles, the areas of the remaining things have to be equal. But if we look at the left-hand side, we have the blue triangle, the blue square, whose area is the square of the shortest side of the triangle, and the red square, whose area is the square of the second shortest side. Whereas on the right-hand side, we have a square. When we take away with the triangles, we have a square whose side is equal to the longest side of the triangle, and therefore whose area is the square of the longest side. And so the 2 little squares have to add up to the big square, and that's Pythagoras' theorem. It's an unforgettable proof of an unforgettable theorem, and it appears in an unforgettable story, which I highly recommend to you. Pythagoras' theorem has inspired people over the millennia. In Einstein's autobiography, he mentions that his scientific awakening as a young man occurred, as a young boy really, occurred when he came to grips with Pythagoras' theorem. I remember that an uncle told me the Pythagorean theorem before the Holy Geometry booklet had come into my hands. After much effort, I succeeded in proving this theorem on the basis of the similarity of triangles. That's not really enough information to reconstruct Einstein's proof. We don't know what it is, but I've tried to reconstruct it, and in any case, I think what I'm about to show you is the best proof of Pythagoras' theorem, and makes it beautifully clear why it's the squares of the sides that appears. So here it comes. First, we have to make a preliminary observation about similar triangles. Right triangles, that is, triangles that have a right angle in them, will be similar. That is, there'll be magnifications or demagnifications, one of the other, if they have another angle in common. So if we have 2 similar triangles, and their sides are scaled up by some factor, one compared to the other, their areas will be scaled up by the square of that factor. Okay. Now in this diagram, we have 3 triangles. We have the 2 subtriangles and the big triangle. They all have an angle in common, namely phi, so they're all right triangles, so they're all similar. One of them has its longest side A. The other subtriangle has its longest side B. And the big triangle, the triangle made up of those 2, has its longest side C. Their areas are proportional to the squares of the longest sides. So the areas of the 2 little ones have to add up to the area of the big one. And so a squared plus b squared equals c squared. Again, Pythagoras' theorem. I can understand, really, how constructing this proof might have been an inspiration for Einstein's entirely scientific career. It's so beautiful and such a wonderful thing to discover. Now I'm going to sort of give you a brief historical tour through the evolution of geometry and how it's enriched our concepts of the world and how it's changed over time. When you first learn geometry in high school, you may think that it's a static subject, that it's never changed, that the rules are forever. The philosopher Kant even elevated that to a principle, that the rules of geometry were inherent in the human mind and would never change. That's totally wrong, of course. The first era in the evolution of geometry, once the idea that you could prove things and that it was beautiful to play with figures, came when people tried to construct the world based on beautiful elements of geometry. And use geometry as a source of intellectual standardized parts that could be models for atoms or structures in the world. The most famous attempt, and the most profound and fruitful, was made by Plato and involved what are called the Platonic solids. So let me briefly introduce you to what the Platonic solids are. Let me start with something simpler, the regular polygons in 2 dimensions. So regular polygons in 2 dimensions would be polygons that have sides all equal and angles all equal. So the simplest example would be an equilateral triangle. But then you could have a bigger one, one with more sides, which would be a square, or a bigger one would be the design for a building in Washington, the Pentagon. And then you have stop signs and so forth. And you can obviously have regular polygons with an arbitrary number of sides. So there's an infinite family of these things. When we move to 3 dimensions, we get something much more interesting when we try to extend this idea of regular figures. If we ask for figures in 3 dimensions, all of whose faces are regular polygons, identical, and all of which come together at identical vertices, then it's a great theorem of geometry. It's the last theorem in Euclid's Elements, and widely thought to be what he was building up to in this 13-volume work, that there are exactly 5 regular solids. These are called the Platonic solids. There's the tetrahedron, which has 4 equilateral triangles as its faces. The icosahedron, a wonderful figure that has 20 equilateral triangles. The dodecahedron, which has 12 pentagons and is widely used as a calendar for that reason. The octahedron with 8, and the cube with 6 sides, used, of course, in conventional dice. Plato, inspired by the fact that there are a finite number of these things, thought that that should have a profound meaning for the structure of the universe. And notice that the number 5 is quite close to the number 4. And at that time, people thought it would take 4 elements to make the universe: earth, air, fire, and water. So Plato postulated that the atoms of these different elements had the different shapes associated with these solids. The tetrahedron, which is pointy, would sting when you touched it, so that could be fire. The icosahedron is pretty smooth. Different icosahedra will roll over each other nicely, so that's water. For some reason, octahedron's air. And Earth can be made out of cubes because cubes kind of pack and get stuck and kind of are earthy. Now, An ordinary thinker might have been discouraged by the fact that 4 is not almost, but not quite equal to 5. But Plato was a genius, and persistence is a big part of genius. So he was undaunted by this. He found a use for the dodecahedron. The dodecahedron is meant to be the shape of the universe as a whole, so it also had a role. Plato later, who always tried to Aristotle later, who always tried to one-up Plato, had a different theory. He imagined that the celestial regions outside of Earth, the so-called celestial spheres, had their own element, the so-called ether for the ethereal regions, and that the dodecahedra were actually the atoms of ether. Nowadays, it's difficult to agree with these theories in detail. However, the inspiration that symmetry determines the possible structures that we should use to describe the world, and that when there are only a finite number of them, that's suggestive of the classification of things that exist in the world, has turned out to be extremely fruitful, and in fact, the basis of modern attempts at unification in physics and chemistry. Plato was very good at getting his name attached to things, but he didn't actually invent the Platonic solids. At the Ashmolean Museum in Oxford, you can find these dice, which were discovered at a site in Scotland and dated to about 2000 BC, and which have the shapes associated with the different Platonic solids. So they're really in the nature of things, and people knew about it quite early, at least in operational terms, even if they didn't have theorems. These were undoubtedly used for some early form of Dungeons and Dragons. This kind of thinking of trying to match geometric structures, and in particular the Platonic solids, to the shape of the universe, really took its final and, I have to say, decadent form in Kepler, where he tried to fit the orbits of the different planets to circumscribed and inscribed Platonic solids, and thus determine the shape of the solar system. And it's a beautiful figure, but unfortunately has very little to do with reality. Because shortly after Kepler's work, and based on some of his detailed discoveries, a very different kind of approach to figuring out how the universe worked. Still geometric, but incorporating not the geometry of timeless perfection, but the geometry of things that change in time, took over. This was the profoundest aspect, I think, of Newton's revolution in physics. The idea that it's laws of change, laws, not static object, that are simple and fundamental. I think Newton first hit on this principle, not by watching an apple fall from a tree, but by thinking about something along the lines of this diagram, which is my favorite diagram in all the scientific literature, and is the first diagram in Newton's Principia. What is it? Well, you're asked to imagine someone standing on a mountain, on a planet, and on a body, could be Earth, and throwing a projectile horizontally harder and harder. What would happen? Well, if you throw it not too hard, that's the familiar thing, it falls to the ground. But the harder you throw it, the further it'll go before it falls down. And Newton kept thinking harder and harder and harder, and came to the opinion, thought it was plausible or maybe even obvious, that if you threw it hard enough, you'd better duck because it'll come back and hit you in the head. It would never have fallen enough to hit the ground. So this concept means that the same thing, the same kind of force that causes things to fall to Earth could also be responsible for things orbiting. Furthermore, the mountain could have been bigger, so you could have bigger orbits. And for that matter, you could have other objects, not just Earth, but any object, having things falling into it or orbiting. So this suggests the universality of gravitation, that the terrestrial phenomena is the same as the phenomena that causes orbits, and that gravity is a universal force. Also suggests that orbiting is the same thing as falling. Just you're falling towards a target that's moving because you're moving, and therefore you never quite complete the process of falling. What's beautiful about this figure is not the shape of any particular orbit, but the thought that goes into it and the idea that the whole scheme of orbits makes sense and unites the idea of orbits and falling. Newton analyzed the motion mathematically as a series of small falls. So the object would move in a straight line if there were no force of gravity, but each time it tries to do that, there's a little force that deflects the orbital, the trajectory a little bit, and you can mathematically analyze the competition between those effects to determine the shape of the orbits mathematically. I think Newton, after considering the circular orbits, considered, suppose you threw it even harder, what shape would you get then? And that led him to the discovery of ellipses, which made contact with Kepler's work and drove the whole Newtonian revolution in classical and celestial mechanics. I really think it all comes from the visualization of that diagram that I showed you. And furthermore, the notion that motion can be analyzed most fruitfully from simplicities of its small bits, Newton generalized to a general mathematical framework for analyzing all kinds of things in terms of simplicities of their small bits. So for instance, to compute the area under this curve, you consider how fast the area is added to as you move along and add little bits to it, and you see that the area is going to be added to by the value of the elevation times how far you've moved, and that's the fundamental theorem of calculus from which so much flows. Newton's view of the world led to many triumphs and had an enormous impact on the surrounding culture, in many ways inspiring the Enlightenment. William Blake, in particular, was turned on by all this and imagined what Newton looked like as he was making his discoveries. I find this more or less plausible because I also like to work in the bathtub and looked very similar when I was discovering asymptotic freedom. Except that you can see in the determined look here and in the attention to detail that the new ethos of science also aspired to precision as well as to overarching ambition in describing the world as a whole. And Blake extrapolated that because this was the right way to understand the world, it probably was also the way the world was built. And and I find the juxtaposition of these two figures quite remarkable. So I've discussed now how geometry suggested building blocks for the universe through symmetry, and how adding the time dimension really changed and enriched and made the picture more accurate. Now, the next big idea in expanding what geometry means is the idea that geometry is not the science of space as given, but a realm where you can imagine other things and make models that are unusual. So, and in particular, models where space is bent and curved. So, in particular, you can not only imagine a flat plane as the arena for geometry, but you can consider two-dimensional creatures who occupied a horse saddle like that, or who occupied the surface of a sphere. What would geometry be like for them? Well, they could have analogs of straight lines, the straightest possible path, the things that are locally the shortest distance between 2 points. But they would find, in the case of the saddle, that if you made a triangle, instead of the angles of a triangle adding up to 180 degrees, they always add up to something less. If you live on a sphere, they always add up to something more. And whereas on a flat plane, you can have exactly one line parallel to some other line through a given point. On the saddle, you can have infinitely many, and on the sphere, two lines always meet, in fact, in 2 points when you draw them, continue them indefinitely. So geometry expanded once we allowed space to become flexible. This idea was developed initially through the work of Gauss and Riemann, describing the geometry of a curved Earth and then extending it to many dimensional spaces, and brought to a new level when Einstein, combining these ideas about flexibility of space with the idea that geometry should also include time and the element of change, developed the idea of flexible space-time. So not only can space bend, but time can also bend and distort in response to physical perturbations, in particular to the influence of large bodies. So the ultimate example of this, perhaps, is the black hole. What I've shown here is, well, I'm not supposed to use that, I'm sorry. Time runs vertically here, and you're supposed to imagine space running. Oh, this is fun. Space runs horizontally. So a curve like this represents the surface of a star moving through space as time passes, and ending up in a collapse to a much smaller object. So this is a stellar collapse, and what happens, according to general relativity, to Einstein's theory, is that when that happens, the collapsing matter pulls along space and time so that these cones, which indicate the paths of light rays, the path that light would follow, and far away represent the speed of light. You go a certain distance as time travels, so you get 45-degree angle lines. Those things tip over, get distorted, and eventually you reach a situation where light can't escape. No matter how hard you try, the light cone has tipped over, so light moving into the future, instead of going off to infinity where you can see it, collapses like the matter into the singular point. Well, this is just one particularly dramatic example of the power and the strange things you start to encounter when you combine the idea of flexible space with the idea of combining space and time to have a flexible space-time. Another direction that's quite remarkable and has an unforgettable picture associated with it is that if you can bend space and time, you can start to blow bubbles, also known as creating universes. So this is a picture of a model of cosmology called eternal inflation, where universes, once in a while, sprout new universes, roughly speaking, new big bangs, and as time goes on, universes sprout universes that sprout universes, and you have this enriched picture, the multiverse, for what the ultimate reality of cosmology is. So that makes space very big in the sense of volume, and also very various in different directions. Now I'd like to add one more idea to the mix, the idea that not only can it be big in extent, but nowadays we have to consider that the universe is very, very rich in the sense of having many, many different possible directions. We're accustomed to thinking there are three kinds of directions, two horizontal directions, north, south, and east, west, and also vertical. So a three-dimensional space, and you can throw in one extra dimension of time if you want to add the dynamical element. But there's nothing conceptually to prevent you from thinking about larger dimensional spaces. You can even draw what a four-dimensional cube would look like. For a three-dimensional cube, the sides, the faces are squares. For a four-dimensional cube, the sides are cubes. And mathematically, it's not difficult to figure out the relationships that connect the different points and make a four-dimensional cube. Of course, you have to project it down to two dimensions to display it on a computer screen and apply considerable imagination to lift it up twice to four dimensions. But the information really is all there. What do these higher dimensional spaces help us describe? Well, many things, some of them are quite subtle and profound in quantum mechanics, but also the experienced world of a mantis shrimp. Human vision is sensitive to three averages of intensities of light from the electromagnetic spectrum. We have three so-called photoreceptors that respond, one mainly to blue light, one mainly to green light, and one mainly to red light. In reality, they all respond to a continuum, but with different efficiencies. And so if you want to make a color photograph that humans will regard as being fully accurate, you only need three kinds of ink, because you only have to satisfy these three averages. Or if you want to make a computer display that has all the colors that human can sense, you only need three different types of light-generating elements. We say human visual space, human color visual space is three-dimensional. Well, the mantis shrimp puts us to shame. It has 16 receptors. So its color world is 16-dimensional. Things that look the same to us could look very, very different to a mantis shrimp. It's capable of making much finer distinctions. It can also see considerably into the ultraviolet and even make distinctions among different kinds of ultraviolet light. So if you want to do justice to the visual world of a mantis shrimp, you need a 16-dimensional space to describe the intensity in all these different channels. Well, I can't allow the opportunity to pass to show you what this creature looks like, this genius of color space. And you see, even humans can see that it's quite colorful, and also that it has very, very strange eyes, kind of googly-eyed creature. But now we realize they're not only strange, but extraordinarily powerful and insightful eyes that in some ways put ours to shame. But we have one advantage over the mantis shrimp. We have a much bigger brain. And using our brain, we can imagine not only 16 receptors, but an infinite number of receptors. We realize through our brains that color space is actually infinite dimensional. There are any number of frequencies. There's a continuum, according to Maxwell's great discovery of the identity of light with electromagnetic radiation of different wavelengths. There's a continuum of different possibilities. We only see 3 averages. The mantis shrimp sees 16 averages, but our minds could allow us to imagine an infinite number. And in fact, we can even extrapolate and, using Maxwell's equations, bring in new phenomena that are not seen as visible light at all, and one wouldn't naively think had anything to do with light, such as radio waves, infrared radiation, ultraviolet, X-rays, and gamma rays. So nowadays, you also cook with it, not only see it, and listen to rock music with it. So now I'd like to introduce yet another idea from the expanding realm of geometry. This one is absolutely central to our best description of the physical world. It's the idea of something called internal space. This one is not very widely known outside of physics, and not very widely appreciated even within physics. So I'm hoping you'll help me popularize it. So we've discussed various complicated geometric objects. This one may look paltry by comparison, just a cylinder. Let me introduce, however, a little more structure to it, drawing a line. And now let me ask you to imagine that you are, or that you're imagining, creatures whose world is one-dimensional, that live on that line. Okay. And imagine that line is very long and they're pretty big, so that the cylinder seems quite small to them. And their eyes, their senses are incapable of resolving directly the structure in that second dimension, which looks like an extra dimension to them. What would things occupying different places in that extra dimension look like to creatures in this world? Well, they might look like different colors, but if they had different properties of other kinds, such as not the colors of the rainbow, but the colors we talk about in QCD, the colors of quarks, then what would happen is that you would see the same fundamental object in different places as being a different kind of particle. So instead of having many independent kinds of particles within modern physics, even within the standard model, and also in more elaborate forms in unified theories, we imagine, we postulate, and make successful use of the idea that many different kinds of particles can all be the same kind of particle, just in different places, seen in different places in extra dimensions. So as this particle moves around, if it's seen in different places, we don't sense those as different places in the normal sense, but as different particles. This is the profound idea that what you are derives from where you are. So I've described now several different ideas, I hope quite a few ideas, about the encounter between mind and matter, where mind has adapted geometry and changed it as a result of its confrontation with the realities of matter. Now I'd like to discuss very briefly the frontier of where mind and matter meet, and the distinction between them starts to become blurry. And I think where we're working towards a unified concept, where both mind and matter are part of this, are the same entity at some level, same deeper unifying entity. This wonderful object is an example of a fractal. I think any human artist who came up with this would have been regarded as an extraordinarily creative genius who dreamed up something essentially new and quite beautiful, just at the sensual level. But this is a mathematical object that's generated by the computer following very simple rules. I won't tell you exactly what the rules are, but trust me, they're so simple that even a computer can follow them. In fact, they're so simple that even a vegetable can follow them. You see, this also has this kind of broccoli, an extremely elaborate kind of structure that follows by iterating simple rules of growth over and over again to make this kind of fractal, self-similar structure. So simple rules can give complicated objects. And we have to expand geometry to allow the operation of simple rules of new kinds. This network is a representation of a piece of the internet, a rather small one, telling who's connected to who. And we're developing new kinds of geometry to describe these kinds of connections and networks. This is another network which superficially looks similar, but this is the kind of network you have inside your skull. This is the pattern of neurons that are connected to each other. You can see, if you look carefully, a few cell bodies, and it's actually much denser than this, but only some of the neurons get stained. There's not much empty space, but presumably it's wired up in a pretty structured way so that this thing actually does useful computations, such as taking input from the eyes, running through the network, and then being able to decide whether what you saw was Julia Roberts or this other person or a baby. Ideas of geometry and quantitative descriptions of the effects of one neuron on another and on the effect of the architecture of the network are a fascinating and very fruitful and fast-growing area of research. So nowadays, geometry has become very flexible, not only bringing in the time direction, not only bending space and time, not only allowing spaces of arbitrary dimension, but even changing the notion that it's the description of space in any very direct way. Now it describes relationships, but the same kind of mathematical techniques and rigorous approach are allowing us to understand also the neural networks and the social networks that are so important to humans. And so finally, the end of this story is that mind and matter are becoming united as mind, by studying matter, finally realizes what it actually is. Thank you.
Thank you, Professor Wilczek, for that fantastic lecture. At this time, I'd like to ask the rest of the panelists to join us up on stage here for the question and answer period. And as they come up, I'll remind people how we do the Q&A sessions here at Gustavus. The ushers will have small tablets for you to write questions on, pieces of paper, and you can submit them, write your question on them, and hand them back to the ushers. They'll bring them to the front where we'll collect them and get them to the moderator. If you're on the internet, you can submit questions by clicking on the Submit a Question. Make sure you submit the question for Lecture 1. And Google Moderator will help you sort those. You can vote for other questions that people have already submitted as well. And as we gather our panel up here, we'll begin the question and answer period very shortly. Thank you.
know what happened to Sam Ting.
I heard he went to look for his wife, and they haven't seen him since then.
Okay.
Very strange.
Well, they'll find him.
We still, I'm John Young.
Hey, John.
We still have a couple more coming, or
So
Ting
Coyne
is here?
Coyne is not in town yet. He's flying in as
Not?
we speak.
Okay.
Ting is here, but he apparently went out to look for his wife, and somebody's trying to find him. So we may just
go with,
move with what we've got.
we'll make it work, and if he shows up, we'll wire him up. If he
Okay.
walks up, we'll wire him up.
Great. Thanks, John. So, no, I'll in the moment when we open, I'll moderate. I'll ask if anybody on the panel has a question first, and give everybody here first shot, and then I'll have questions from the audience and questions from the internet, and we'll just we'll roll. And Frank can peer over my shoulder and see, here's the questions that are coming in, right? The multiverse was the first question that came in, so. Yeah. Yeah, I mean, maybe Tom's with him. Yeah. Yeah, Tom's. And he missed the briefing at dinner last night, maybe, and doesn't know the routine. Could be.
I glanced occasionally just to check that people were seeing my photos. Pretty much. Because on my computer, you can see I have it.
Smile for Brianna.
But unfortunately, I didn't start my talk at time zero, so
Yeah, who knew?
I didn't know what.
All of when you're speaking with each other, you're going to hear your words coming from in front of you from these monitors, just to give you a little bit more presence, because it's so noisy in here, just so you know that that's where it's coming from. And you speak right into your mic.
Okay, straight ahead. That's Professor Ting. Excellent. Are you going to initiate this whole thing?
Yeah.
Okay. And you'll also do the when it's over? Thank you.
You set? Okay, please find your seats, folks. We'll get the question and answer period started in just a second here. Okay, Professor Mellema will start us off.
Okay. Thank you again, Professor Wilczek, for an amazing lecture. And I think we usually give our panelists the first shot at questions. So does anyone from the panel want to ask? Professor Krauss.
So Frank, do you think ultimately geometry is everything?
Well, yes, because geometry, by definition, will be everything. All the concepts that are used to describe the world will ultimately want to visualize and play with the way we play with figures. So they'll become geometric, even if their origin wasn't anything we'd recognize as geometry today.
Thank you.
Professor Dean.
Good.
So, Frank, I was intrigued by the last part of your presentation in two ways. You talked about the notion of internal space.
Yes.
And then at the end, you drew this very strange figure with the U, and a number of us have seen that. One of the eye is sort of representing the operation of the mind. So are you one of these people who thinks that what the mind does, which is process data, has something to do with the universe, that is an idea that we're starting to see emerge in physics?
Well, first of all, I should say that that figure was stolen from John Archibald Wheeler.
I'm aware of that.
who loved to draw those kinds of strange, profound figures. Well, some more profound than others. But well, I do think it may be a fruitful way to look for new laws of physics or understand implications of physical laws better, to think of them in unconventional ways now suggested by the study of neurobiology or by computer science, because it's given, just as in the early days it wasn't obvious that what geometers were doing measuring the Earth would turn out to be so fruitful for understanding the physical world, but they were doing a lot of stuff that you could exploit. Now, I think similarly, neurobiologists and computer scientists are developing ideas in information theory and analysis of networks that are very, very powerful ideas. And so we can look forward to stealing from them in physics. And also we can repay, because we have ideas in physics that I think can be very powerfully and fruitfully exploited in those realms and haven't yet been sufficiently appreciated. Yes.
Frank, when you developed quantum chromodynamics,
Yes.
was there much data upon which it was based, or was it largely mathematical like string theory right now and without that much experimental grounding?
There were enormous amounts of data about how the strong interaction worked. And in fact, in many ways, the hardest part of discovering asymptotic freedom and realizing its importance was to separate the signal from the noise, because most of the data, most of this enormous accumulation of data about the strong interaction turned out to be, well, not wrong, but not central. I had a great advantage. As I was mentioned, I was only 21 years old at the time. I had the great advantage of not knowing very much. So I didn't know all this irrelevant stuff. And I was lucky enough to focus on just the stuff that led in the right direction. But there were crucial experiments, in fact, pioneered especially by people at MIT. Kendall, Taylor was not at MIT, and Friedman, of course, who's still very much with us and a good friend of mine at MIT. That showed some very unusual behavior of quarks, that when they're close together, they interact very weakly, although when they're far apart, they interact strongly. And also that when you hit them very hard, although they have very powerful interactions usually, and you would think that therefore if you hit them very hard, they would radiate a lot of stuff. In fact, they radiate very little. And it turned out that those were the right phenomena to focus on. And just by trying to understand those and make them consistent with general principles of quantum mechanics and special relativity, we were led to a unique theory. Now, the unique theory we were led to was a highly mathematical theory of symmetry. But it was definitely informed by very concrete experimental facts. And it wasn't long before Sam Ting and others did experiments that really started to give new kinds of confirmations of the theory. So it didn't go through this long period of being a promising theory that hasn't delivered, that some other theories we might mention have been going through.
Professor Shears has a question.
Yeah.
So Frank, I have a really simple question for you. So I'm an experimentalist, and I've heard many, many theorists talk about the beauty of symmetry and the beauty in geometry. What is that beauty for you? Is it the simplicity? Is it the compelling nature of the laws? What exactly?
Well, I like to quote Salieri here. In the movie Amadeus, Salieri looks at one of Mozart's compositions in the manuscript form and is in wonder at it, and says, if you changed a note, it would be diminished, and if you changed a phrase, the structure would fall to the ground. And that's a form of beauty. Everything fits. You can't change it without making it worse. And that's what symmetry in physical equations gives us. It gives us equations that can't be changed without making them worse, because their different parts have to be perfectly balanced so that when you make the transformations that the symmetry says you're allowed to make, you still get equations with the same content. So that mathematical idea leads you to unique, very structured equations. And then the miracle is that those equations are actually the ones chosen by nature. So it was the same instinct that led Plato to the Platonic solids as models of atoms, but this time it's right.
Other questions from the panel? Professor Smoot?
I'll try this a little differently, so you can rattle Frank this way. In fact, a lot of the recent history of physics, the last 40 or 50 years, has been about understanding symmetry and exploiting them, starting from Noether's theorem. And in fact, it seems to me people have pushed that to an extreme limit with supersymmetry, even though the data has not yet supported that theory, even it's quite beautiful. And just because it doesn't look like the real world, you have some spontaneous symmetry breaking or something to get out of it. But geometry has a lot of symmetry in it, but it's different. And I've been thinking for a while that people have exploited symmetry enough that they know it a lot better than I do, so I should think other ways. And I'm with you. I think geometry is a way of doing it. And geometry has some built-in symmetries, but it has some other factors. And so when you were giving this talk on geometry, I was so eager to hear what was going on. Are you thinking the same thing, that we need this new approach?
Well, in broad terms, I think you're touching on a theme that actually was implicit in my talk, which is that the original idea of geometry as a static perfection doesn't do justice to the possibilities. When you add dynamics, you get enriched possibilities. When you allow the structures to bend, you get enriched possibilities. So, and now when you consider networks and things that don't have a continuous structure, you get additional possibilities. So it's a balance. You have to, on the one hand, have a structure that gives you something to work with, building blocks, but then you have to be creative in using those building blocks, I guess. And a lot of, you alluded to this, but a big theme of physics in the last few decades is that symmetry can be very deeply hidden in the phenomena. You can have symmetry in the equations that doesn't show up in any very direct way in the phenomena. You have to look very, very hard to find it. But then once you've found it, you can build back up to reality. So physics as it's developed has come to use longer and longer chains of deduction, getting from the basic equations to the phenomena that you observe. I mean, it's famous, for instance, that in Newtonian gravity you can solve the two-body problem and get Kepler's law for planets. In general relativity, you can solve the one-body problem to get the Schwarzschild geometry. In quantum field theory, you can't even solve the equations for empty space. So, and yet that gives us the deepest description of the world. And so we have to use more and more chains of deduction between between the starting point and what we actually observe.
Other questions from the panel?
I have one more.
Mr. Gates?
Since implicit in the discussion of the last few minutes has been the notion of symmetry, I want to describe an experiment and get your response to it. One can take a human face and cut it in half,
yes,
and throw away half of it and then invert and then glue back together to get an apparent human face back.
All right.
But people's reaction to that construct is actually very, very different than the original face.
Yes.
So do you think that this is some indication that we are so wired to regard symmetry as humans that it's a force in how we think about things far beyond the laws of nature?
Well, yeah, I think symmetry is certainly part of the notion of beauty, and is, well, of course, the way we use the word in science is somewhat different and more precise than it's used in general usage, but it's still the same word, and there's a reason for that. And symmetry in art and so forth has always been associated with the more general ideas of beauty. And well, as you said, humans are very attuned to symmetry or lack of symmetry, especially in other humans. I'm told, although I'm not an expert at this, I'm told that movie stars, for instance, typically have much more symmetric faces than the average human beings, because that is a sign of health and attractiveness that people use in assessing possible mates.
Let's turn to a question from our audience today. The questioner writes, regarding the theory on internal space, you said that different particles may actually be the same particle viewed at different angles.
Yes.
Should there not be an infinite spectrum of angles and therefore an infinite spectrum of particles?
Well, in classical mechanics there would be, but in quantum mechanics the infinity gets broken down to a finite number. So it's quantum mechanics that really enriches the picture and allows you to get a discrete number of possibilities out of a continuum of angles.
Another question from the audience. If time is the fourth dimension, can you speculate on how dimensions 5, 6, etc. would be described?
Well, I can certainly speculate. but I don't have to speculate. Even within this, well, within the standard model, I wasn't just making up this idea of internal dimensions. It's in accepted physics. It's the central concept in the standard model that, for instance, a quark, or a particle, a quark, in different directions in color space will be seen as either a red quark or a white quark or a blue quark, that we call them, will be seen as having different properties. And so that's what 3 extra dimensions look like. It's the dimensions that not all particles can move in. Quarks can move in those directions, but it turns out electrons can't, and that's why they don't participate in the strong interaction, theoretically. But we use very flexible ideas of what dimensions are in our equations. So they can look like almost anything.
Frank, I should add, though,
we use these extra dimensions as playgrounds for our equations. So you can use different equations based on those extra dimensions to describe a wide variety of things in principle.
But I should just add, in case people get a little confused by what you said, when you talked about red, we use the words color, but we don't mean color.
No,
we just
no.
ran out of words. Maybe not dimensions, but we ran out of
Well,
words.
it's a very unfortunate choice of words, actually, but Murray Gell-Mann chose it, and now we're stuck with it.
Yeah.
But when applied to quarks, the concept red, white, and blue really have absolutely nothing to do with visible colors. They're really different. They're much more like different kinds of charge, electric charge. But instead of, in electricity, we have just one kind of charge. It comes in positive and negative varieties, but it's just one. axis, so to speak. It's a strong interaction. It's kind of electrodynamics on steroids, and we have three different kinds of charges. And they're called colors for historical reasons.
I'll turn now
Basically because Murray likes to be clever. Clever, you know.
Let me turn to a question that came via the internet today from Alex in Sheboygan, Wisconsin. He asks, can we discuss multiverse theory and its relationship to geometry in some more detail?
Okay. There are actually two important multiverse theories in contemporary physics. One of which I think is, well, even it is controversial, but I think it deserves not to be controversial, having to do with quantum mechanics, where the wave functions that we use in quantum mechanics describe many, many possible outcomes of experiments that don't occur. When we make a measurement, we find out one result occurs out of many possibilities with different probabilities. And a possible interpretation of that, called the many worlds interpretation, which I really think is the only consistent interpretation, is that what's happening when we make a measurement is that the wave function describes many worlds. When we make a measurement, we discover which of those worlds we belong to. And so that's a kind of many worlds that's implicit in quantum mechanics. And, well, maybe I'll leave it at that and let other people talk. But the second use of the multiverse is much cruder, and it just means that there could be structures, spatial structures, that are very, very far away that we haven't seen yet, where physical laws look quite different. Multiverse has different nuances, but that's, I think, the main idea. This, of course, flies in the face of everything we know about the observed universe, which seems to be uniform and obey the same laws everywhere, and that's a very profound discovery in itself. But there are theoretical reasons to think that if we did persist and wait long enough, we might see different laws acting elsewhere, or that it's fruitful to consider theoretically the possibility that we're only sampling a small part of a much, much larger structure when we sample what we call the universe. So that's the multiverse theory.
Another question from our audience. The questioner asks, if mind and matter merge, then can we alter the state of our experience with disciplined, directed thought, for example, the practice of meditation?
Sure. But I think more effective than meditation is studying physics or mathematics.
A related question from the internet. It says, we talked
also, you should exercise. It's very good for your brain.
We talked a bit about the geometry that describes the physical aspect of the mind in terms of networking and neurons. This question from the internet is there any geometry that describes the mental space itself?
Yes. Yeah. I mean, there's a whole discipline called neural network theory, which is rapidly developing and very exciting these days, that describes, well, it's too early to say that it really describes how we think, but it describes a rich kind of mental universe that is capable, that allows machines to recognize patterns, to recognize faces, things like this, in absolutely explicit mathematical terms, as the operations of these mathematically defined imaginary objects. There are no real neurons. It's a mathematical construction, so it's geometry in a generalized sense. And the underlying geometry is the geometry of networks and connections between units that I sort of sketched.
Another question from the internet. We've talked a lot about symmetry and perhaps seeing beauty in symmetry. The questioner asks, what about imperfection? Isn't that beauty as well?
If properly done, yes.
If done perfectly.
No, I should emphasize that symmetry is only one form of beauty, and there are certainly additional forms. In fact, if we look at that fractal, which I think by any standard has a lot of symmetry, I mean, is very beautiful. Its symmetry is quite subtle. You can't turn it some way and get the same structure. You can't. It's certainly not spatially uniform. It's very, very structured. It has a kind of symmetry. If you blow it up, parts of it may look the same as the whole thing. And of course, if you look at any of the classical art objects, they're not perfectly symmetric. Michelangelo's David is not symmetric. So there's a lot more to beauty than symmetry. I mean, well, maybe I should leave it at that. But symmetry is one thing that can lead to beauty.
But just add, if the universe was perfectly symmetric, we wouldn't be here. So it's probably
yes, I mean,
that it's not.
That's right. I'm here and you're there. Therefore, different points in space are different, right? All right.
One more question from our audience for Professor Wilczek. What happens to geometry inside the black hole?
Well, no one knows for sure since no one's been there and done experiments. But the straightforward application of general relativity, which has been tested in other ways, leads to the idea that if you did fall into a black hole, you might not even notice if the black hole was big enough. You would feel some tidal forces as you pass through the surface, but basically nothing is there anymore. It's all been swept into the middle. And you can describe those tidal forces. They get more severe as you get towards the center of the black hole. You get squished into a spaghetti-like shape as you fall into the singularity. So, well, you can describe the geometry in terms of equations, but I think it's better to think about it, it's easier to think about it in terms of how you would sense it if you were moving in this space-time geometry. And that's what would happen. If the black hole is really big, you would hardly notice when you first fell in. In fact, the whole universe might be a black hole and we might be inside it. But nevertheless, you can't send signals to the outside world anymore. That's what's really happened when you fall in. And your fate is sealed. Eventually, you'll fall into the middle. And shortly before that, you'll notice that you're being squeezed into a piece of spaghetti.
One last question from our audience is, does time actually exist, or is it just a measurement of change?
Wow. Well, I think I reject that question. Questions about actual existence are kind of loaded questions. They have more to do with the use of the English language than actual questions. They're the kind of thing Wittgenstein called language games, where so I'd be much more comfortable with concrete questions about phenomena.
Okay, well, I happen to have maybe a last from the internet that relates to time, but is perhaps that kind of question. This questioner, Lauren from Sauk Rapids, asks, if time and space are flexible, is there any possibility that something like time travel is possible, or maybe a faster way to travel through space?
Well, exploiting the flexibility of space-time is actually very limited. You have to use extremely massive objects and concentrate a lot of energy in a small place to get significant bending. So for instance, whereas we use electromagnetic radiation for all kinds of practical purposes of communications and microwave cooking, not to mention sensing the external world, to date, our evidence for gravitational waves, which would be the corresponding effect of bending space-time, are very few and indirect. And very ambitious, difficult experiments are being planned and apparatus constructed to detect gravity waves at all. And the gravity waves they'll detect will be things triggered by violent effects in the universe. So it seems very far-fetched that you'll be able to magnify those kinds of effects in a practical way to speed up space travel or even more drastically to do anything like time travel. There may be fundamental limitations, or there may not be, to the possibility of time travel, but I think as a practical matter, don't hold your breath.
Thank you.
All right.
Thank you all for being patient here. I would just want to remind people as we close this session, we reconvene at 12:45 with music and 1 o'clock with Professor Shear's talk. Have a great lunch.
Would you folks, if you're hungry, if you folks are hungry, there's 100 of us from Wisconsin here to have a dining room set up. You think you are? Okay. everyone. My name's Scott Moore. I'm the chair of the music department, and I'm going to tell you a little bit about what the music you'll be hearing this afternoon. This is the Vasa Wind Orchestra, conducted by Karen Murphy Nelson. They're going to be performing 3 works for you. The American Fanfare by John Wasson was commissioned by the Dallas Brass back in 1989. Now, Wasson is from St. Paul, but he plays jazz trombone in a jazz ensemble down in Dallas, Texas. He toured with the Kenton Band for a little bit, and I understand there is no jazz in this tune, however. Is that right? Oh, okay. All right, maybe next time. Frank Ticelli is a name that's very popular these days, writes for almost any sort of ensemble, and the work you're going to hear, called Rest, was actually a choral work first. It was called There Will Be Rest, and he adapted it for concert band. The last work is by Howard Hanson. Now, Howard Hanson became director of the Eastman School of Music back in 1924 at the ripe old age of 28. He had planned on a career of composing, had a very promising career at that time. As a matter of fact, he kept composing even though he was directing a very busy school of music during that time. Some 40 years after he assumed directorship, he wrote this piece, The Chorale and Alleluia, for the American Bandmasters Association. Ladies and gentlemen, the Vasa Wind Orchestra, conducted by Karen Murphy Nelson.
Folks, we're going to get started here in just a second, so please find some seats. I hope everyone had a great lunch. I know I did. It was fun seeing old friends and meeting some new ones. We have an exciting afternoon planned, and we're going to get it started here. It's my pleasure now to introduce my colleague, Professor Josh Brown from our philosophy department.
So our next speaker is Dr. Tara Shears. She's professor of physics at the University of Liverpool and a member of the LHCb experiment at CERN's Large Hadron Collider, the LHC, where she initiated the QCD Electroweak and Exotica Physics Working Group. She's also one of the world's foremost public ambassadors for the LHC and for the science of particle physics more generally. Now, I am really, 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 really excited to introduce Dr. Shears because she's got the coolest job in the world. She smashes protons together at just shy of the speed of light and then sifts through the wreckage in order to look for clues about the nature of matter and about the evolution of the early universe. It's a little bit like this.
Let's get down to business.
Are you ready?
I'm ready.
Do you mind if I flip the switch?
Go for it.
This is compact rocket sled in 3, 2, 1. Wow!
Now, as I said, it's a little bit like this, but really, it's even cooler. Because, protons, of course, are much, much smaller than the Mythbusters rocket sled. But the protons that Dr. Shears smashes together are also moving much, much faster. The rocket sled is moving at about 650 miles an hour. That's faster than most passenger jets, and were you riding that sled, you could get from here on Gustavus's campus to downtown Minneapolis in about 6.5 minutes. Or from the LHC in Geneva to Stockholm in about 2 hours. The protons in the LHC are traveling over 1 million times faster, roughly 670,616,600 miles per hour. In your 6.5-minute rocket sled ride to the Twin Cities, an LHC proton could travel to Mars and halfway back, over 71 million miles. The proton gets from the LHC to Stockholm in 7/1000ths of a second. Now, when two of these protons collide, they don't just disintegrate like the car in the video. They briefly recreate the conditions that prevailed in the universe right after the Big Bang. A stew of particles with a temperature of over 2.5 trillion degrees Fahrenheit, hotter even than the center of the sun. Dr. Shears studies the birth and behavior of fundamental particles in this stew. Just this past spring, in April, Dr. Shears' LHCb experiment announced exciting results concerning a type of particle called a strange beauty meson. Now, what's really fascinating about strange beauty mesons is that they spontaneously can flip from being matter to being antimatter. The LHCb experiment looked at 70 trillion proton-proton collisions, isolated 1,000 or so strange beauty mesons, and discovered that matter mesons outnumbered antimatter mesons by about 25%. This is the first observation of what's called a charge parity, or CP, violation in strange beauty mesons. And it's one important experimental step in helping us understand why, when we look out to the farthest reaches of the universe, and so back in time towards the Big Bang, we see only matter and not antimatter. Dr. Shears' work thus reaches towards all of the disparate limits of the universe. By probing its smallest, most fundamental parts, she's helping explain its largest features and discover what it was like at its very beginning. Please join me in welcoming Dr. Tara Shears.
Thank you, everyone. So, in this talk, we're going to explore the universe right at the innermost frontiers. We're going to look at what matter is made of and how it behaves at the very smallest, the very deepest scales, the scales of particle physics. Now, what I want to do is to show you what particle physics has shown us, but I don't just want to talk about what we understand about the universe at these very tiny distance scales, because I also want to show you, in a sense, how little we understand and where the frontiers of our understanding lie. So I'm going to tell you about some of the biggest open questions in our subject. These are questions that drive us to do our research. They drive us to build enormous experimental facilities to try and find answers. And I'm going to tell you about one of those. I'm going to tell you a little bit about the Large Hadron Collider, because I work on it. It's most familiar to me. I'll show you what it looks like, how it works, but most importantly, I'll show you our latest results, because already the Large Hadron Collider is starting to fill in the gaps in our understanding of matter and the universe at these innermost scales. And so you'll see for yourselves just how far we've come and where the frontiers of our understanding have stretched to. Now let me start at the beginning, because I should tell you really what particle physics is and how it fits into the history of the entire universe. So in brief, particle physics, in particle physics, we have an idea that everything that we see around us is made of the same basic stuff, the same ingredients, the same fundamental particles that make everything. And we think that only if we could identify these and understand their behavior, well then, that would allow us to understand the behavior of the universe at larger scales. And that's the approach we take. Now, behind me, you can see almost everything we know about the universe through physics encapsulated in one picture, very simplistically. So, on the left, we have the Big Bang, where we think everything started. The Big Bang was this, if you like to imagine it, was a hugely, tremendously energetic fireball that brought everything in the universe into existence. And the early universe was a very different place to the universe that we know now. It didn't have stars in, it didn't have planets, it didn't even have atoms. Instead, it was populated just by the ingredients of atoms, the fundamental particles that I just talked about. Now, as time marched on, the universe expanded and cooled down until, at various points as it cooled, it became, energetically speaking, more effective for matter to start to clump together into new forms. So after a few fractions of a second, we start getting neutrons, protons. After a few 100,000 years, we have the first atoms. And then, as time marches on, we get larger and larger structures, stars, galaxies. And then, here we are, almost 14 billion years later. Well, that's what we think happened. But of course, how we know any of this, and I say this because I'm an experimental physicist, is through experiment. It's the only way to be sure. And to work out what the universe is made of now, it's quite straightforward. You can just look at it. You look at it through telescopes. You can send out probes to take measurements of anything if it's close enough to you. But if you really, really want to understand the universe, you also have to understand how it got from the Big Bang to now. And that's a problem, because you can't look at the very early universe through telescopes. It's opaque. You can't see into the universe before it was about 300,000 years old when atoms formed. So instead, if you want to work out what was going on just after the Big Bang, you have to recreate those incredibly hot conditions in the laboratory. And that's what we do in particle physics. That's what we do in our particle accelerators. So that's the angle, if you like, that particle physics brings to our understanding of the universe. It tells us what matter is made of at the very tiniest scales, what the universe is made of, but also what the universe was doing in the first brief seconds of its existence. Now, already, our experiments have shown us an awful lot about what the universe is made of. So we've realized that matter is made of no more than 12 fundamental types of particles, 6 quarks, 6 leptons. Now, these particles are really amazingly small. They're at least as small compared to atoms as atoms are compared to you. And I say at least as small because they're so small we've never been able to measure them. That's just the limit of technology. They are incredibly small. Now, in your everyday lives on Earth, you don't even see this many particles. You don't come across them. You just come across a fraction of them. The first two quarks up there, the up and down quarks, they're familiar to us in everyday life because collections of those form the neutrons and protons in our nuclei, which are orbited by electrons to make atoms. And the neutrino associated with the electron we often see in radioactive decay. We don't even come across these other more exotic particles unless we go to higher energies than we typically have around us on Earth. But they exist, and we've seen them in our experiments. We know they're an ingredient of the universe. Okay, so that's matter. That was easy. Now, what makes this matter set of fundamental particles stick together to form matter that looks and behaves in the way it does to us are a small number of fundamental forces. Not very many, just a small number. There's a weak force, for example. Now, it's the weak force's job to give us radioactive decay. The weak force describes radioactive decay. And it affects every single one of our matter particles. And we think that we have a picture for the way this force works. We think it's communicated by the exchange of other types of particles that carry the force, force-carrying particles, called W and Z bosons in this case. And this idea of a force working by exchanging a force-carrying particle between matter particles isn't just peculiar to the weak force. It's the idea we have for how forces work for really any of the forces that we can describe. So besides the weak force, we have another couple to get through. There's the electromagnetic force, which is much more familiar to us. It's driving the lights, it's driving the projector. You use it at home an awful lot. You know it acts on anything with an electrical charge. And that means it acts on any of our fundamental particles that are electrically charged too. And it's communicated by photons of light. And then quarks, and this is what makes them different from leptons, as Frank was telling us in his talk before, experience the strong force. And it's the strong force that keeps atomic nuclei stable, because it's an attractive force. And it's strong enough to overcome the electrostatic repulsion between the protons that you have in the nucleus that would otherwise drive it apart. And that's communicated by a number of force-carrying particles called gluons. Fantastic. And I have to say, that's almost all we consider in particle physics. That's almost all the ingredients of the universe that we've come across. Now, there is one more fundamental force that I haven't mentioned. And I don't know if you can think of what that might be, but it's a force that's responsible for the large-scale structure of the universe. It's gravity, of course. Gravity is incredibly important. Gravity acts on mass. It's what is keeping you stuck to your seats, stuck to the Earth. And we know that all of our fundamental particles have mass as well, because we've measured it. So therefore, they must also feel gravity too. However, gravity is so much weaker than the other forces that we can just neglect its effects when we're describing what goes on in the very small distance scales that we look at in particle physics. So I have it here with a question mark, because gravity, although we know it exists, it clearly does, is something that in our subject we have yet to fully understand. Okay, so we have matter, we have forces, and there's just one more ingredient left in the universe. And it's an ingredient that was only verified by a discovery last year. It's a very timely piece of information. And this extra piece of the universe goes back to this idea of mass that I just mentioned for gravity. Why do particles have mass? What causes them to have the value of mass that they do? Well, we think the explanation lies in something called the Higgs field. Now, the Higgs field is like a type of energy field which is present throughout the universe. It's part of the universe's structure. And fundamental particles, we think, obtain mass as they move through the universe and move through the Higgs field. And the amount of mass they get Just depends on how strong their interaction with that field is. And this field also has a particle associated with it, which is the Higgs boson, which was what was discovered last year, which is what allowed us to verify that this particular idea was correct. So in this idea, if you're a massless particle like a photon, you zip through the universe completely unaware of the Higgs field. But if you're a massive particle like the top quark, your path through the universe is impeded by your interaction with this field all around you. You are a heavy object. Now, we don't see the Higgs field, it's invisible. But we should be able to see the Higgs boson that's predicted to accompany it. We should be able to make it in our experiments. We should be able to detect it by the characteristic way it decays and leaves a signature behind. And indeed, that is the layer of logic that we followed in order to make the discovery. And I'll tell you a little bit about how that worked later on. Okay, we have mass, force, and an explanation for mass. And we even have a picture for how this all works together. And what's even better than that is that we can encapsulate this picture in mathematics. We can write it down in equations. And the equations that we write down form our theory of particle physics. And our theory of particle physics is so succinct, so elegant, that you can write it on the front of a T-shirt. And if you go to CERN over in Europe, you can even buy the T-shirt. It is a retail opportunity that awaits you as you go in the front door. I've always wanted one of these. And the reason that this equation is so beautiful harks back to what Frank was saying in his talk, because it's founded on the principles of mathematical beauty that he was talking about. So now you're starting to see where the frontiers of mathematics and geometric structure start to impinge on the world of reality and what we can measure. Now, not only is this equation really, really beautiful, it's also really, really good, because we haven't yet made any measurement at all that disagrees with any of its predictions. It's so good that we call it the standard model of particle physics. And that's brilliant. But it's not the whole story. It's not the whole story because we know that this theory is incomplete. For a start, it doesn't describe gravity. And that's not because we've been lazy and we think it doesn't matter. It's because we can't put gravity in the same type of equations as the other forces. It just doesn't work. It gives us rubbish out as answers. And besides not describing that, we know that there are many phenomena in the universe that we have observed, but which cannot be explained or predicted inside our theory. And for that reason, we think there must be a deeper, underlying understanding of the universe to be had, if only we can find it. And it's that that drives our research, to learn more and to understand more about this innermost layer of the universe. So, having told you about what we understand, I'm now going to move on to what we don't understand. And so the very fact that I've spent such a small fraction of my talk on what we understand should tell you that the entire universe is up for grabs when it comes for understanding it. There's so much to find out. I'm just going to tell you about some of the bigger questions that we have. The first one is such a basic question that I've given it number 0, not even number 1. And that's, is the standard model even correct? We know it's incomplete, but where it can describe data, is it even a correct description of data? Now, this was a much more leading question before the LHC started, because the standard model had a prediction for finding the Higgs boson. The Higgs boson hadn't been found, and the whole correctness of the standard model hinged on this particle being discovered and being known to be there, and being known to be the particle associated with the standard model. That would be the only way to verify this. Well, we have found Higgs, and not just the theorist, Peter Higgs himself. We have found a Higgs boson. But we still don't know very much about it. We still don't know if it's a Higgs boson we expect to see in the standard model, or a Higgs boson that's associated with some more exotic theory of nature. So that's why I've kept this question in my talk, and I haven't deleted not knowing if the theory is correct or not yet, because although we're close to the answer here, we don't entirely know, and I'll show you how close we've got later on. Okay, so let me talk about something that we really don't understand. And in fact, Josh beat me to it in his introduction. And this is the phenomena of antimatter. Now, antimatter sounds great. It sounds like science fiction, but it's not science fiction. It's actually science fact. It's just incredibly rare. Now, every type of particle I've told you about in the Standard Model has an antimatter counterpart, a type of mirror image, oppositely charged version. Now, we just don't see very much antimatter on Earth, and we know this because if I have antimatter and it meets its matter equivalent, it annihilates, and the resulting annihilation is huge. If I have 1/4 gram of antimatter meeting 1/4 gram of normal matter, this annihilation has the explosive force of 5 kilotons of TNT. It's a very good diagnostic tool if you have antimatter in the room. You immediately discover it. Well, we haven't seen that. We haven't seen it on Earth. We haven't seen it out in the universe anywhere we've looked. And so for that reason, we don't think there's very much antimatter around. And that is the problem. Because when the universe started in the Big Bang, we think that half of it was made of antimatter. And just after the Big Bang, matter and antimatter would meet, annihilate, releasing photons of light that then would split into new pairs of matter and antimatter that would meet, annihilate. And this whole process carried on as the universe expanded and cooled. Until eventually, when the universe was a matter of seconds old, the universe had expanded so much and cooled so much that these annihilation photons no longer had enough energy to make new pairs of matter-antimatter particles. And this whole battle between matter and antimatter stopped at that point. And what remains in the universe now, today, is a consequence of a very tiny difference between the amount of matter and antimatter that we had at that point. A very tiny difference, something like 1 part in a billion. But that very tiny difference is the reason why we're here. We're the leftovers. Because if there were equal amounts of matter and antimatter at that time, the universe now would just be full of light. It would be a very, very different place. So if we really do need to understand how the universe evolved, and that means we really do need to understand what made antimatter that little bit different to normal matter, what that little difference in behavior is. And that is one of the leading questions in particle physics today that we have to solve. But it's not the only one. So not only are we not 100% sure that our theory is correct, not only do we still have to understand how the universe evolved, everything I've told you about concerns visible matter. And cosmologists tell us that's a mere 4% or so of the whole thing. So in fact, what I've described to you is a small fraction of the universe. There's far more out there, and you'll be hearing about it in talks after mine. The vast majority of the universe's energy budget consists of mysterious dark energy and mysterious dark matter. Now, in particle physics, we have absolutely no idea what dark energy is. We have no idea what dark matter is either, if I'm perfectly honest. But at least we have some ways of testing what dark matter might be made of. We have ideas. We have possible alternative theories of matter that hypothesize what it could be composed of that we can test in our experiments. And one of the most popular versions of theories that could explain this is a theory called supersymmetry. We talked about it very briefly in the discussion after Frank's talk. Supersymmetry is a theory that takes the Standard Model and extends it. And it brings in deep, intimate connections between force and matter. And in the process, it predicts the existence of a whole new raft of particles, supersymmetric or SUSY particles, partners of the particles that we know about. And the supersymmetric partners of matter particles behave like force-carrying particles, and the supersymmetric partners of force-carrying particles behave like matter particles. Now, the really great thing about supersymmetry from the point of view of trying to work out what dark matter might be made of is that in many versions of supersymmetry theory, the lightest one of these new particles, is a really good candidate for dark matter. It's a really good candidate because it's massive, so it experiences the gravitational effects that led us to infer the existence of dark matter in the first place. And it's also a really good candidate because it's completely, experimentally unseeable, just like dark matter. Well, that seems rubbish. Why would you explain something you can't see by predicting something you can't see either? But it's not that bad. Because if supersymmetry is the right way to view the universe, although we wouldn't see the dark matter particle, we would expect to see the other supersymmetric particles predicted by the theory. We should be able to discover them in our experiments, measure their behavior, match that behavior up to what we expect to see with supersymmetry. And if we can do that, we can infer the existence of this lightest dark matter particle. We can infer what dark matter would be composed of, and that would be wonderful. So these are pretty big questions, but they're by no means the only questions. There are many, many fundamental questions. And these are just the known unknowns. We don't even know what the unknown unknowns are yet. Because what we found out is the more we discover about the universe, the more we find out there is to know about it. And it's questions like this that make us want to research the answers. It's questions like this that made me want to become an experimental particle physicist, because I wanted to know why. So, how do you find answers? Well, if you're an experimental particle physicist, you need an experiment to work on. And there aren't many particle physics experiments in the world. I have a map of the globe here with some of the main ones, and I stress this is a personal selection, so if I've missed out your favorite experiment, I'm very sorry. So the places in red are where we have particle accelerators. So there's Fermilab and Brookhaven in the States, CERN in Europe, KEK in Japan. Some of these have neutrino facilities as well. Neutrinos we don't know very much about. They need specialist detections, specialist experiments. And I've put some other facilities where neutrino experiments take place in blue on the map as well. So you pick one of these places. You pick the experiment that's going to give you access to the data that you need to explore these questions. And I work at CERN, which I'll tell you about now. It's a European Centre for Particle Physics. And it's been researching fundamental physics now for almost 60 years. And during that time, it's moved from being a European center set up just after the Second World War to allow physicists from different countries to be able to collaborate together when normally politics would not allow them to now being something more of a world center, because particle physicists from all over the world, from here, from Australia, from Africa, from India, all come to CERN to collaborate together and perform their experiments. And that's because CERN is an incredibly exciting place at the moment, because it's the home of our largest, most powerful particle accelerator. It's the home of the LHC, the Large Hadron Collider. Now, you may have heard of this before, but if you haven't, I'm going to tell you all about it. So the LHC, you can see it in this picture behind me, actually on either side. I've just realized there's two screens, so I should stand in the middle. On this aerial view, in red, you can see the outline of the LHC itself. It's a circular accelerator, and I'm mixing up my units here between metric and imperial. It's about 16 miles long, 27 kilometers. And it straddles the French-Swiss border near Geneva. So if you can see a dark area just above the ring, that's Lake Geneva. The city of Geneva is just at the right-hand end of that before you get to the mountains. And in the background, you see the snowy Alps. And Mont Blanc, the tallest mountain in Europe, is slap bang in the middle there. Now, the LHC is situated 100 meters under the ground, 110 yards. I looked it up. I did the translation. If you go to CERN, ever, if you find yourself in that area of Europe, you can go and visit it. As long as we're not running, you can actually go underground and visit it. And by the way, this year and the next year is a very good time because we're not running. And if you do that, you'll find yourself standing in a tunnel like this. And it's only by standing in this tunnel that you really appreciate just how very large the LHC is. You can just see it curving away in the distance. Hardly at all. It's almost like a straight line. The circle is that big. And you find yourself standing next to a long chain of blue magnets. Well, these magnets are the heart of the particle accelerator. It's their job to keep our particle beams bent round in this circular path. Because what happens when the LHC operates is that we have two beams of protons, hydrogen nuclei, circulating in opposite directions around the accelerator, and then accelerated to enormous energies. Until at design spec, these beams will be going just a few miles an hour less than the speed of light. Incredible. Now, I have to add, we haven't reached design spec yet. We're only halfway there, but it's still extremely fast. And when we've made the beams go this fast, we bring them together and we smash them into each other at 4 points around the ring. It's not quite as good visually as Josh's video, but it's still pretty effective. And we don't just do this once or twice. This process goes on 40 million times a second. And what's so amazing about that, what's so fascinating and compelling if you're a particle physicist, is that in every one of those collisions, for a tiny instant of time, in the tiniest area of space, what you've done is recreate the very hot conditions of the very early universe. And that means you can study matter as it existed at that point in the universe in terms of fundamental particles. That's how we get them to study them. And when I say very early universe, I do mean incredibly early. We're talking billionths of a second after the Big Bang. This is where we can access experimentally. Now, around these collision points, we build our experiments. And our experiments are like gigantic, three-dimensional digital cameras. And they allow us to take a snapshot of what happens during a collision. They allow us to take a snapshot of the fundamental particles that are produced and what happens as they fly outwards. We record their paths, their energies, everything we need to be able to deduce what's going on there. And the idea is, if we keep on taking snapshots of what goes on in the early universe and what goes on at matter at these very tiny levels, we can start to build up a bigger picture of what's happening. And we can compare it to our theory of what should be happening. And if it matches, great, fantastic. We understand what we're looking at. And if it doesn't, oh, that's even better. We're going to make a discovery. You can't lose in particle physics. Now, just like the LHC, our experiments are huge as well. This is a picture that you may have seen sometimes in stories in the media, often where CERN stories come up. It's a picture of the Atlas experiment, one of the two big experiments. CMS is the other one. America works on both of them. But it's a picture taken during construction. So all you can see here are the orange striped rings of the magnet held up by scaffolding. The important point here, and this is why I wanted to show you this picture, is to take note of the normal-sized man in the yellow hard hat standing at the front. That gives you the sense of scale for just how very large this experiment is. It's 20 meters high. It's 45 meters long. Now, if you see it, that entire volume is filled with precision particle detection equipment, with some 100 million channels of electronic information to read out every time we take a snapshot. It's extremely high-tech, extremely complex. Now, every experiment at the LHC is instrumented in the same way, using the same sort of ideas. So what we do immediately around the collision point is have a series of detectors that can tell us where particles go. Incredibly precise detectors, like this silicon-based detector we built for my experiment, LHCb. The silicon is a silver semicircle, and it's the size that would just fit in the palm of your hand. And it's so precise, it can tell you the position of a charged particle going through it within 1/10 of the thickness of your hair. And every experiment has its own version of this, a whole series of them that provide the dots we join together to trace out the paths of particles. Around this, we have other detectors that measure other features of the particles, how much energy they have, what type of particles they are, until by the time you get out to the edge of the experiments, these detectors get very large indeed. And what you see behind me here is a picture of one of the outermost detectors in the Atlas experiment being cabled up, finished off before we started data taking. Now, I wanted to show you this just to prove that we had filled the middle of Atlas with particle detection equipment, and we hadn't left it empty. If you can turn your brain round from where you saw the detector before, you're looking at it end on now, but you can still see those orange stripy magnets. But now they're buried inside lots and lots of detector material. You can also see two physicists cabling up the last part of this detector. But note, to get there, they're on a platform. And the platform is suspended by a crane 20 meters above the surface of the cavern that the experiment sits on. You really need a good head for heights if you're going to work on a particle physics experiment. Now, not every experiment is as big as Atlas, but as I say, they all work on the same principles. The LHC gives us a collision that makes the fundamental particles that we study. The experiments take a snapshot, and different particles leave different traces inside the experiment, depending on how far they travel before they're absorbed. And that's what allows us to recognize them. So if we read this out, we can write software programs to analyze what we're seeing. And then, if we do that, we can compare what we get out of these software programs to our theory to see if we're on the right track or not. So there's one extra ingredient we need before we can look at the data, of course, and that's the computers needed to manipulate the vast amount of data that these experiments produce. They produce petabytes of data. In 1 year, they should produce 1,000 times more information than the world annual book production. You know, no one's got enough computers to analyze that. And that presents a bit of a problem, because you do have to analyze a data set of that size if you're going to research any of the big questions I told you about in the beginning. If you want to find the Higgs, if you want to look for dark matter, you need to look through every single bit of that data. But we have a solution, and it was developed by computer scientists. The solution's called the grid, and it's like the next step up from the World Wide Web. It's a layer of software that we put on our computers that make it, from the outside to the user, look like all of our computers in particle physics are joined together in a way we just are completely unaware of. And it makes our computing facilities behave like a geographically distributed supercomputer that is powerful enough to meet our data processing needs. And this map of the world, wherever it has a blob, shows you where we've put computers and connected them onto the grid. And wherever you see a little line, that's where someone's written a program, a software program, and it's traveling around the computer looking for the data, or it's sending back its results. We spend hours looking at maps like this, wondering how our programs manage to get to exotic places when we don't. But it's the last step in our puzzle. So the LHC gives us fundamental particles. The experiments give us snapshots like this. And it's the grid that gives us the computing power to be able to turn this snapshot into an analysis that tells us that this is a candidate, for example, as it is, to be a Higgs boson. So that's how we do it. That's how we perform our research. That's the idea behind it. And the LHC has been running, I mean, really seriously running, since about 2010. And it's given us a huge amount of data, hundreds of trillions of proton-proton collisions. So now I want to go back to the big questions that I told you about at the beginning of the talk. And I want to show you how much progress the LHC has helped us make into finding out more about the universe. You know, let's tie it back and see how we're doing. So remember the first question. Was the theory correct? And that was all tied up with whether the Higgs boson existed, and if it did exist, was it a Higgs boson? Was it the sort of particle we expected to see in the standard model? Well, prior to the LHC, nobody had discovered the Higgs. Lots of experiments had looked for it, including at the Tevatron here in Chicago, but no one had seen it. All these experiments could do could home in on a certain region where, if the Higgs boson did exist, well, that would be where we'd expect to see it. It would have a mass in this region here. And that's what allowed the LHC to be designed in such a way that if that Higgs boson existed, then it should be discovered. So up until the LHC, your best chance of finding the Higgs, if you didn't bump into the man himself, was to buy the soft toy version. And I dread to think how this got started. I have this awful vision of 100 or so PhD students who are so fed up by having a PhD on finding the Higgs and then failing to do it that they're driven to doing things like this. But at least it was less expensive than a genuine Higgs boson. But all that changed when the LHC started, because the LHC had enough energy and produced enough data to be able to disentangle traces of the Higgs boson from all the many backgrounds that mimicked the signal, that messed up the signal for other experiments that went before it. And just over a year ago, on a date that Europeans now refer to as Higgs Dependence Day, I can say this because I'm European, then CERN held a public seminar where the ATLAS and CMS experiments that were driving the search for the Higgs publicly announced their latest findings. And this is what they said. Now, I'm going to have to do a little bit of translation from particle physics language, I think. So what had happened was hundreds of trillions of proton-proton collisions had been analyzed, and a new particle had genuinely been seen. And it had a mass of about 125 times the mass of the proton, where nothing else existed before. And it was seen at 4.9 standard deviation significance. Now, in particle physics, I have to explain this. It's a little bit embarrassing. We have a threshold where we officially define when something has been discovered and when it hasn't yet been discovered. And this threshold is really a matter of statistical precision. And our threshold happens to be 5 standard deviations. And so no particle physicist could really put the word discovery on that slide there. Now, the difference is 5 standard deviations just corresponds to a chance of 1 in 1.7 million that nature has somehow conspired to look like the thing that you're looking for without it being there. 4.9 standard deviations is only a chance of 1 in 1 million, quite different. But luckily, the media were on hand to translate for us. And this was widely reported as a discovery, as indeed it should have been, because both experiments independently saw the same behavior. They saw the same signal from independent data sets analyzed independently. That's a very strong confirmation that something new has happened. And indeed, no particle physicist present at CERN at that time was in any doubt that the Higgs had been discovered. And CERN weren't in any doubt either, because sneakily they had invited some of the theorists responsible for predicting the Higgs mechanism along to the seminar, just in case they were interested. Now, there's more theorists than just Higgs who predicted this. In fact, there are a set of 6 theorists who worked relatively independently in 3 groups that all came up with the same idea. And here's a picture of Peter Higgs on the right meeting one of those other theorists, François Englert from Belgium. And would you believe these people wrote their papers back in 1965, and this was the first time they had ever met in person. You'd think that would be impossible nowadays with the number of conferences and workshops and trips to CERN where people always meet each other, but they'd never met before. So there are many firsts going on that day for Higgs. Now, the reason it took us so long to find the Higgs is, as I say, it's incredibly rare. And let me show you how rare by showing you an animation of the signal from ATLAS building up. So what you see here points to data. The red area is what we expect to see from things that aren't the Higgs. So for a discovery, you want to see an accumulation of data at a place, a particular mass that isn't described by the red curve. And you can just see it becoming apparent now. Well, that's more data than was used for the discovery. And just coming up now is our entire data set that's been delivered. There we go. There's a discrepancy. The next thing to do is to see if it's consistent with what we expect from the Higgs boson. Here in light blue is what we expect. It matches up. That's great. But it matches up within the statistics that we've been able to measure. And there's not many of them. And for that reason, this question is still slightly open. What we've seen, for everything we've measured so far, is that this Higgs is consistent with the one we expected in the standard model, but we can't be absolutely sure yet. And to test that, well, we do things like look to see how often we see Higgs in different experimental signatures. We compare that to how often we should see it from the standard model. We compare how often we should see it to how often we do see it as a ratio. And all these different ways of seeing the Higgs, if it is a standard model Higgs, should give you a point that lines up at 1. We see it as often as we expect to. You can see there's a bit of fluctuation. And you can see from the size of the horizontal error band, there's still quite a lot of uncertainty. And it's at this level we think we've seen the standard model Higgs. But we need more data to be absolutely precise, and that's going to come in the future. Now, I have to say that hasn't stopped people just working out things, just in case it's not a standard model Higgs. I had a look on the web at the archive where we put our preprints before our papers are submitted to journal. And I counted from the start of 2012 the number of papers with Higgs in the title. Now, bear in mind, there can only be a handful of experimental papers with Higgs in the title. I counted 1,946 papers, all due, well, the majority due to theoretical physicists coming up with really wacky ways in which this Higgs could be something completely different. Those are the sorts of things we have available to us to test. Okay, so for the first question, we've made progress, tremendous progress. We're pretty sure that the theory is correct insofar as the Higgs boson exists and it looks like the one we expect to see. What about the other questions? Okay, let's go on to the next one, antimatter. Antimatter is really investigated at the LHC by the LHC-B experiment. It's what it was designed to do. And I have to point out that the B in our name doesn't come for coming second or being second best. The B is there because we study the properties of the B quark, one of the fundamental particles. And we do that because, for reasons we really don't understand, the effects of matter and antimatter for that particular fundamental particle are most different. And that makes it easier to study experimentally. And that affects the whole design of the shape of our experiment. You can see from this cartoon that it's a very different shape to the Atlas experiment. And that's because B quarks, when they're produced, preferentially travel in the same direction as the beam. So we just instrument the area immediately around the beam. So this is a cone-shaped detector where the collision between protons takes part at the left-hand end of the experiment. And we just make measurements of particles going forward. Now, to investigate antimatter and matter and their differences, the approach we take here is to isolate a sample of particles containing B quarks, like the B sub S mesons Josh was talking about. And we can do this from picking out a particular way that they leave a signature behind in our experiment. A signature that looks something like that picture, where in this case, the B sub S meson has decayed to two particles, a kaon and a pion. We obtain them from our data set, and then we subdivide them into matter and antimatter, depending on the electrical charge of those kaons and pions they've decayed to. And essentially, all we do is count how many of one we have compared to the other, because we expect B and anti-B quarks to be produced in equal amounts. So if we don't have equal amounts by the time they've decayed, that tells us something a bit strange is going on with antimatter, and it's that bit strange behavior that is what we want to understand. Now, as Josh mentioned, we made our first measurement of this difference earlier this summer. And here is an extract from the experimental paper. What it shows you is a number of B sub S mesons we reconstructed, we found out from our data. The matter version on the left, the antimatter version on the right. And the B sub S mesons, I'm afraid, don't correspond to the great big thing that goes off the top of the graph. They correspond to the little green area next to it. There's only about 1,000 of these things that we found in our data, despite looking at over 70 trillion proton-proton collisions to get them. That's why you need something like the LHC to generate the huge data sets for you to find them. It's very, very rare. Anyway, as you can see from the relative heights of those green peaks, we saw more matter than antimatter. And as Josh said, it was about 25% more. And that was great. So let's go back to our quarks and the difference between matter and antimatter. So we made a difference of it for made a measurement of it for the B quark. And it was a measurement that had a value of what we expected to see. And that was very good news and very bad news at the same time. I'll tell you what is bad news in a moment. And other experiments have investigated the B quark, the strange quark. LHCb can also investigate the charm quark, where we don't expect to see any differences between matter and antimatter. We can make measurements of that, and we don't see any differences between matter and antimatter. So that agrees with what we expect to see too, which is bad news as well. Now, why is this bad news? Well, the bad news is that we don't have an underlying theory of antimatter that gives us predictions for how it behaves that we can test to see if we're on the right track. We only have experimental measurements that matter and antimatter are different. And that means we have to describe this somehow in the standard model, because it's an experimentally observed phenomena. It means essentially we have to patch up this very beautiful, elegant theory with something quite ugly to just try and fit what we see. And the way that the standard model does that is by 4 numbers. It's quite simple. And of these 4 numbers, one of them directly describes the difference between matter and antimatter and matter, and the other 3 describe differences in quark behavior with the weak force, where we see matter and antimatter behaving differently, as opposed to the other forces where they don't. And we take all the measurements we ever made in any of our experiments that are sensitive to differences in matter and antimatter, and using our theory, we extract values for these 4 numbers from them, from our experimental results, and we compare the numbers that we get. So if these 4 numbers are a good way of describing antimatter, we should expect the numbers that we extract from all our experimental measurements to all match up and be consistent. If it's a really rubbish way of doing it, then they're not going to match at all, and that's going to tell us we have to think again. But in fact, what we find in this somewhat colorful plot is that it all works really well. So what you can see here are lots of different colored areas. These different colored areas are the allowed values for this standard model parameter that describes the difference between matter and antimatter from a huge variety of different experimental results, direct measurements of matter-antimatter differences, measurements of matter mixing into antimatter and back again, measurements of matter decaying, antimatter decaying, it all goes into here. But what we see is that all these allowed values coincide at one point. And that means that although there's no understanding, no deep reason to have this particular way of describing matter and antimatter in the standard model, it does the job. It describes what we see in our experiments really well. So perhaps that gives us a clue to its deep nature. Well, we can think about that, and we can look at the amount of matter we see around in the universe, and we can look at the difference between matter and antimatter that the standard model describes, and we can work back to see how much antimatter that implies at the start of the universe. That's a really good test. And what we find is that we don't end up with half a universe of antimatter. In fact, it's nowhere near that. We fall well short. We have found that we only describe something like a galaxy's worth of antimatter. And that's a problem, because we've described matter and antimatter behaving differently in the way we can test it with quarks. But this explanation does not explain how the universe evolved. We've made progress in understanding this question, but there's more to it. There has to be another way of tackling this problem. And indeed, there are other experiments that try to work on measuring antimatter in different ways to try and work out where the extra antimatter went. There's another experiment at CERN that isn't situated on the LHC. It's situated on an accelerator called the Antiproton Decelerator. Lovely name. And what this does is it makes samples of anti-atoms. You have antiprotons slowed down, cooled down in this accelerator, bombarded by positrons, which are anti-electrons, until some of them are captured into an anti-atom. And there's one experiment there called Alpha that tries to hold these anti-atoms in one place for long enough to make some measurements of their qualities and their behavior to compare directly to hydrogen atoms. And this is the only way we have of looking at antimatter directly. But it's really tricky, because as soon as you make an anti-atom and it hits an atom, or it hits protons or electrons, it just annihilates. It's very difficult to keep it in one place long enough to study it. And what Alpha have worked out is a way of doing that. They've made what's called a magnetic trap. It's very, very strong magnetic fields that can hold these antiatoms in suspension by the subtle interplay between the magnetic field that's applied and the magnetic effects that go on inside the atoms. And that holds them in suspension. It stops them touching the walls of the tube and annihilating. And that means you can make tests of them. Well, so far, ALVA has only really done a technology prover. It's managed to generate about 400 antiatoms and hold them in one place for about 15 minutes. But it allows you to make some tests. You can test, for example, the effect of gravity on antimatter. I mean, this is a question. Does antimatter fall down under gravity, or does it fall up? Who knows? Antimatter is weird. You'd think it would fall down, but you really, really have to test it. And in this case, you can just turn off the magnetic field and see if your antiatoms float up to the top and annihilate, or just fall down and annihilate. Well, that test has been done, but without much in the way of statistical precision, and it will be done in the future with more precision. And also, we want to study the structure of antiatoms, the energy levels the positrons can have in them, compare them to the energy levels electrons have in hydrogen atoms, and so forth. And this is an area of investigation that's really going to start going next year, in 2014, when an upgraded version of this trap is going to be commissioned so that larger samples can be studied. Again, it's not the only handle we have on antimatter. These are just experiments on Earth. There's also a really good experiment out in space that you're going to hear about later on from Sam. It's the AMS experiment, and that is out in space looking for dark matter and antimatter. Now, there are sources of antimatter that we know about in space that just are a byproduct of protons moving around in the interstellar gas and scattering. They produce positrons as a byproduct, low-energy positrons. So we'd expect to see those. But there are other potential causes of antimatter. Dark matter may be annihilating. Now, that would be really good, because then we could understand maybe a bit more about dark matter, and we'd understand where extra sources of antimatter are in the universe that aren't described by quarks. You can have astrophysical sources that accelerate up positrons to enormous energies too. It's a really intriguing subject. And I was going to put the results here, but I'm not, because you can all wait for Sam's talk this evening, because I'm sure he's going to show you what they've seen so far. And it's really interesting. And the last way you can look at antimatter is a way we haven't managed to yet. I've told you about quarks. I haven't told you about neutrinos, because we know so little about neutrinos. And the next generation of neutrino experiments hopes to make the first measurements of matter and antimatter versions of neutrinos. That's in the future. Okay, so antimatter, we're making progress, and there's many, many avenues of research going on. What about beyond the standard model? What about dark matter, my second big question? What about supersymmetry? Have we seen any evidence for supersymmetry yet in our experiments? Well, no. We're in the dark about dark matter still. And that's not for want of looking for evidence of supersymmetry to try and see if this theory is correct or not. Let me show you this list of investigations that the ATLAS experiment have done, looking for different supersymmetric particles behaving in different ways in the experiment. In each one, you see a colored line. That colored line corresponds to where we haven't seen that particle, where if it existed, we would have seen it. We've drawn a blank everywhere. So much so that when CMS, who also look for supersymmetry, presented their latest reports in an open report to CERN last week, they retitled this plot. Instead of calling it the CMS supersymmetry searches plot, they've called it the CMS we did not find supersymmetry plot. And here is their version. Again, the colored region showing you where we've looked for supersymmetry and not found any evidence for it. Now, just because we don't see it directly in front of our eyes, that doesn't mean to say it's not there and that we can't look for it in a more clever way. And we can also look for it in what we call an indirect way. And that's akin, let me give you an analogy. It's akin to flying an aircraft and just looking to see what's in the sky in front of you. You can look with your eyes at what's visible, that's direct. You can use radar to see what's hiding out there behind clouds. That's indirect. Well, we have our own version of this sort of indirect radar search for supersymmetry going on as well. And it comes back to this very popular B sub S meson. What we can do is study a very rare process where 3 out of every billion times this B sub S meson is produced. It will give us an experimental signature when it decays of a pair of muons. Very rare in the standard model. However, this rate can be enhanced or suppressed, changed about generally, by any new physics that's out there that can participate in this reaction. So that makes it a very delicate, sensitive probe of new physics because it can reach out to higher masses than we can access directly. Now, with our entire data set at the LHC, LHCb and the CMS experiment have made their first measurements of this process, and it's bang on the standard model value, yet again. There's no smoking gun for a signal of supersymmetry. And this always makes the press, in Britain at least, get incredibly excited every time a new result fails to come out. And they have a whole variety of phrases and hyperbole that gets more and more extreme. So to start with, supersymmetry was being put on the spot. Awkward questions were being asked of the theory. And now it's got so bad that every time a new result comes out, we have headlines like, supersymmetry in hospital, supersymmetry badly damaged. Well, the point about supersymmetry is it's an immensely elastic theory because there are so many unknowns inside it. What these results have done have ruled out classes of possible versions of supersymmetry, but by no means have they ruled out every type of supersymmetry. There's still much out there to test. And so, because we've failed to see supersymmetry so far doesn't mean to say that we're not going to be able to describe dark matter and that it doesn't exist. It just means to say that we need to go to higher energies to look further in order to find it. And of course, supersymmetry itself might not be the deep underlying theory of the universe that we've been looking for. Frank mentioned extra dimensions in the universe. We're looking for evidence of those experimentally. We're looking for evidence of new types of fundamental particles that we haven't thought of yet. We're looking for evidence for anything. And as you can see behind me, with all these colored lines, we haven't found any evidence of anything untoward or unexpected yet. We haven't even found evidence for the one thing we assured you would not be produced when the LHC started back in 2008. We've looked for them in our data, and we failed to find black holes being produced as well, which I must say is quite a reassuring thing. However, it doesn't really answer that question. Dark matter is still a huge mystery to us. The true nature of our understanding of the universe at this innermost level, this innermost frontier, is still a mystery to us. But research never, ever stops. So what I've shown you here is what we understand about the universe at the subatomic level, what our big questions are, our areas of uncertainty are, and where we've made our latest progress. But there's still more progress going on. What's happening now, although we're in a rest period with the LHC, is that we're performing maintenance on it so we can run at higher energies when we start up again in 2015. We hope to run at the design specifications, the design energies, and that will give us a much greater reach to look for supersymmetry and evidence of dark matter and evidence of really bizarre stuff that would be great if we could find something that would just show us where to look beyond the standard model. And it will also give us the extra Higgs events that we need to fully pin down whether that Higgs is a standard model Higgs or perhaps one associated with another theory like supersymmetry. Alpha and AMS are just at the start of their respective investigations and are going to continue to give us really interesting results that will hopefully give us progress in our understanding of dark matter and antimatter. And then beyond this, in the future, we're already thinking of the next generation of particle facilities. And this is important because it takes an immensely long time to design and build these facilities. You're looking at a lead time of something like 30 years from the decision to do something to the development of the technology to make it happen, the construction, the commissioning, to get to data taking. So that means that we have to plan now, even though we plan to run the LHC until 2030. And there are many, many, many discussions about what might come afterwards. But whatever comes afterwards, we're in a really, really incredibly exciting time because we're in a phase of particle physics where almost every year we push the amount of universe that we're able to see, we push our horizons out further, where we can make more discoveries, or where we don't make discoveries, but in so doing, we just learn more about the universe and its behavior than we knew before. And what's incredibly exciting at the moment is we're just about to take another one of those steps by going up to full energy at the LHC. And we could find anything there, because it's in a part of the universe that we've never been able to study before. It's completely open, and I hope very much we'll find the answers to some of the open questions I've been telling you about. We may not. That's the beauty of research. We have no idea. So this is a subject in flux. You're going to have to wait to see how we push the frontiers of our understanding of the innermost universe out in the next few years. Thank you.
Thank you, Professor Shears, for that smashing talk. Sorry, I couldn't resist. At this time, I would like to invite our panelists to come up to the front, and we'll begin to collect questions from our audience. Remember, find an usher with a sheet to write your questions on, and then get them back to them. And we'll begin the question and answer period in a short time. Thanks.
Oh, you're George Coyne. Hi, nice to meet you. Thank you. Thank you. Thank you. You realize I'm going to pass all the difficult questions on to my esteemed theoretical colleagues? Oh, you're so nice. Thank you.
Or Tara?
Tara.
Tara.
But it's fine. Anyway, does it? Doesn't matter.
Sure.
Oh, no. Very good. Thank you.
Okay, folks, please find a seat, and we'll begin the question and answer period in just a second. Okay, Professor Mellema, you can start the questioning.
All right, we'll begin as always with any questions from our panel for Professor Shears. Anybody want to start? Jim.
I have a question. First of all, I wanted to thank Tara for a fantastic brief on what's going on at the LHC. It was just stunning. It was super, shall we say.
Absolutely.
Thank you.
A lot of people know that I wrote the first PhD thesis at MIT on supersymmetry in 1977, so I've been watching this idea forever in my life. And I noticed that on one of your transparencies, the one where you were talking about the decays of the Higgs, where you had the red arrow bars, there was one, which I believe was the Higgs go to 2W, where the red line did not line up with the rest of the data sets. Can you speak to that for the audience?
I can indeed. So how I would reply to this is that I showed 5 different signatures that Higgs leaves behind. And statistically speaking, if you look at how you would expect to see your data line up, that difference is completely probable. If you work out the probability of seeing that distribution, there's nothing wrong with it. It's not a sign that there's anything wrong. I mean, it might be interesting to motivate looking for it in the future, but there's nothing about that that says it's inconsistent.
Were those error bars 1 or 3 or 2 sigma?
1 sigma.
1 sigma. So yeah, that wasn't very far away from the line.
Yeah, that's just
really 1.5
67%.
sigma.
I wanted to make sure that that point was made clearly to the audience for the eagle eyes out there watching the line.
As a theorist, it's even more important. There's an old maxim that no theory should agree with all the data because some of the data is wrong.
Sure.
Yeah.
I don't know that I agree with that.
But my serious question is actually this. You actually, in the latter part of your presentation, really kept returning to supersymmetry. And for a lot of people who follow the literature, the popular discussion, they keep hearing the supersymmetry is dead. So can you speak a little bit more about why, in your eyes, it was so important to come back and tell this more nuanced version of the story?
Well, it's impossible to kill off supersymmetry as a theory. And I said when I described supersymmetry, that was because there are a large number of unknowns in the theory. It's not very tightly known. There are many different values, different parameters in it can take, and that affects the masses of these new particles that are predicted. So they could be much more massive than we've seen so far. And that would still be perfectly allowable. Now, the LHC has ruled out masses, and that's great. So it's ruled out versions of those theories that predicted masses in that region, but it can't rule out everything. In supersymmetry, I must say, you must be very proud if it was your thesis. It's a theory that keeps on giving. You have predictions all the time.
But
I would like to mention that there is one bit of circumstantial evidence that's in favor of supersymmetry.
Is this the Higgs?
No. Well,
we know where he's going.
Maybe we should count that as 1.5. So I'll mention that also. That's good. Yeah. So when you consider unification of the forces of the standard model, which is based on strong electromagnetic and weak forces, all with different strengths, we'd like to unify those into one force that has just one strength, of course. However, as observed, they have different strengths. Fortunately, this phenomenon of asymptotic freedom that was mentioned predicts that the effective power of forces changes depending on what distance at which you measure them. And we expect the underlying simplicity and unity to emerge only at short distances. So you can calculate with the stroke of a pen how the forces will behave at much shorter distances. If you do that without including supersymmetry, the unification fails. But if you do it with supersymmetry, the unification works. So to me, that's very strong circumstantial evidence that supersymmetry is a feature of the physical world. Furthermore, the calculation relies on the supersymmetric particles not being too heavy. So I think there's an excellent chance that they will be found at CERN.
Frank, I'd like to thank you.
Also, Also, I won a couple of bets based on faith in supersymmetry. Because before the Higgs particle was discovered, nothing was known about its mass. Its mass could have been, well, nothing is too strong, but its mass could have been anything, say, between 80 GeV and 800 GeV, an enormous range of possibilities. But supersymmetry predicted the mass would be on the low side, less than 150 GeV. So I put some bets at very long odds, like 10 to 1, against that supersymmetry would be found at the LHC with a mass, the Higgs particle would be found at the LHC with a mass less than 150 GeV. And I won.
And now, if I may have my say, thank you. This is a commercial. You guys don't know this, but what Frank just did was give you a commercial for my talk.
You want to go first, and then, yeah, you got your
hand. Yeah, Tara, you expressed some relief that miniature black holes had not been found. But of course, even had they been produced, they wouldn't pose any danger to us for a number of reasons. And moreover, had they been produced, it would have indicated the possibility of an extra macroscopically big dimension. So astrophysicists would love this kind of thing, you know?
I do apologize. But I was quite relieved simply because of the fuss at the start of the LHC. And you're perfectly right. There's a really easy, logical way to understand that this isn't a problem with black hole production at LHC, because the energies involved in LHC, even though they're massive and much really energetic compared to other accelerators we've built, they're still tiny on the cosmic scale, and much harder interactions go on out in outer space. So if this is a mechanism, it would be happening all the time. But still, it makes our lives easier when we explain what we've done, just to show that that was right, and that's what gave me relief, even though I appreciate your concern.
I just wanted to add some to the play between Jim and Frank and Tara that there's an interesting sociological phenomenon with experimental physics, which is usually wanting to try to prove the theorist wrong, and which is a good thing. But it's interesting that in the case of the Higgs, for example, before it was found, the amazing thing about the LHC and the machines before it is that it had ruled it out from all but a very small region. And I remember the experiment saying, we're going to show it's not there, you know. And of course, that was the region it was in. And so I think it's important to realize that the experimental non-discovery of supersymmetry will only be a non-discovery until it's discovered. If it's there. So it's really important to constrain it, but not having seen it is not the same as it not existing. I think that's really important.
I'd like to make a related point, actually, broader, which is when you report that you're not discovering something, what you're actually reporting is that you're discovering that the standard model works extremely well, much better than its original evidence would have indicated. So we did well. And I mean, not only did we do well in formulating the theory, but enormous amounts of work and ingenuity have gone into calculating its consequences. And one wouldn't be able to make sense of anything that happens at the LHC without tremendous control on how things usually behave in the standard model, which usually means, as you mentioned, parts per billion or parts per trillion. When you're looking for discrepancies from the standard model, you're looking for very small effects. You're looking through enormous haystacks for little bitty needles. So you'd better understand Hay very well. And it turns out that we do.
And in fact, as I know you're proud of, Frank, the thing you won the Nobel Prize for is now the background.
That's right, that's right. Yeah. Testing, there used to be an enterprise called Testing QCD, which was to test whether the theory was right. But now, after, well, depending on how you count, perhaps, I don't know, 10,000 sigma evidence in favor of QCD. Now we have pretty good faith in it. So now, instead of talking about testing QCD, people talk about calculating backgrounds. It's exactly the same activity.
There is one point. There's a point, however, if I may, that I think it's really important for Americans to understand.
Okay.
We salute the great triumph that took place at the LHC and with the discovery of the Higgs.
But it's, I should point out, it's a triumph that belongs to everybody.
And I agree, and that's exactly where I'm going with my comment. On the occasion of my previous presentation here at the Nobel Conference, I spoke about the fact that we Americans stepped back from supporting something that didn't happen, which was the SSC, which you're very well aware of. The SSC would have operated at 3 times the initial design energies of the LHC, and a lot of the technologies, as you just alluded to, that go into the operation and the detection of the Higgs is made in America. However, it shows the danger of what bad choices can do when it goes out in the political realm and we look for questions where we ask the American people for their support in science. So there's a slightly cautionary tale here.
Actually, it's worse, because I remember when that happened, I used to think Congress was crazy.
Used to.
Professor Coyne has a question.
Could I ask Lawrence a question? Are they any crazier?
Oh, yeah. I mean, they seem like geniuses now. I mean,
If I may change the topic from supersymmetry, this smashing discussion, as Chuck said, of supersymmetry. I'm wondering, Sarah, it may have been buried in your talk, but I didn't hear it. Are WIMPs still a candidate for a fairly good fraction of dark matter?
Well, yes, they are. But we just haven't seen any evidence for them yet.
the lightest supersymmetric particle is a WIMP.
It's a WIMP, yes.
They're the one and the same.
Oh, I see. WIMPs is weakly interacting massive particles.
Yes.
Did I get that right?
Yeah, absolutely. Since the subject of WIMPs, can I chime in just a little bit here? Because a lot of us are real fans of WIMPs, and we don't mean the guys that walk down the streets, right? We mean the weakly interacting massive particles. In Frank's talk earlier today, he did something rather beautiful that I'd like to illustrate for the audience. He talked about inner space. Now, we physicists have been talking about this forever. We almost never talk about this to the public, and so this was actually a brave choice. But the thing that's really interesting that follows from this is that if you take the idea of inner space and combine it with string theory, you figure out that there are 2 forms of dark matter, WIMP dark matter and another form of dark matter called hidden dark matter. So it's rather interesting that this extension speaks to things that we still don't know about yet.
Well, I've got a question here from the internet that maybe accompanies that. This is from a Gustavus student named Jen, but she submitted it over the internet. What do you think needs to be done or invented before dark matter is something that can be discovered in the lab? And how close do you think scientists and physicists are to study dark matter in the lab?
Well, it all depends what dark matter actually is.
Yes.
So that's a very good question, and if I knew the answer, I would put bets on and then rake in the money.
People are exploring many different possible signatures or signals for dark matter. Professor Ting will tell us later about cosmic rays, which are one promising way, searches at accelerators. Another contender for dark matter that I'm very fond of, that I think is the best, actually, it's not a WIMP at all. It's this so-called axion that I introduced a long time ago, and certainly it has it has a much better name than WIMPs. And important experiments to look for that are also being done that are quite different. They are more like the experiments used to search for the microwave background radiation and explore its properties. They use very special kind of antennas, because in some ways the axions are like photons, but more elusive. Then it's also possible, and in fact, such evidence, I should say, over the last few years, and especially in the recent couple of years, there's been one rumor after another of possible dark matter signals. And I think there are probably even 5 or 6 now, different groups that claim to have some kind of hint for dark matter. The problem is that these different hints all disagree with each other and basically rule each other out. But none of them has fit very well into any of the existing paradigms of dark matter, of WIMPs or supersymmetry or axions. So they're probably all wrong, but people are looking very hard for any non-gravitational effect of dark matter.
Let me say the other thing that makes it very exciting, and I may talk about this tomorrow, is that there's this competition because there are there's two ways to look for dark matter. One is to create it in the lab, as Tara's talked about. The other one is to look at the dark matter left over from the universe, which is in this room, as I'll talk about. And that means that you can actually build direct detectors, and it's a kind of a neat competition because the existing direct detectors, some of which are underground, near here, in fact, are sensitive to almost the same kind of scale of physics that the LHC, that Tara talked about. And so there's this really neat competition. You don't know who's going to do it first. And anytime there's competition in physics, it's a great thing. Yeah.
Anybody else on the panel? I've got another question from the internet from Brad in Sioux Falls for Professor Shears about the LHC. He asks, what are some of the limiting factors in the energy produced by the LHC? Why is the design spec 13 TeV and perhaps probably not beyond that?
Oh, that's just a function of the engineering and of the magnets that we use to be able to control the beam and the devices that we use to accelerate the beam. Now, when charged particles go around in a circle, they actually lose energy. They radiate all the time, and it means that you have to keep on pumping energy into them, especially if you want them to go faster. And this has two effects. One is that you need to pick a type of particle that you'll be able to do that efficiently with, and that's why we use protons. But then that has a side effect. Protons are really hard to keep on bending round in a circle because they've got a lot of momentum. You need very strong magnetic fields to keep those beams going round. And when you have a circle of the diameter of the LHC. Now, why we run at 14 TeV was because that was the strength of the magnets that could be manufactured industrially at the time. It's the limit of the superconducting technology that was accessible at the time, which I guess we thank you for. But progress could be made if we could find higher temperature superconductors that are possible to manufacture magnets from at over the same scales, and that would help us push up the energy. The other alternative, and this is on the table for a future facility at CERN, is to build a bigger ring. Because if you have a ring of a larger diameter, then you could use the same strength magnets, but just make everything go faster. And people have already started making gestures towards the potential digging out of another ring at CERN that instead of being 27 kilometers long is 80 kilometers long, and it goes up completely under mountains and completely under the lake. It's quite speculative at the moment. But those are the only ways in which you can change your effective energy scale, and that's why we picked 14 TeV, because it was the limit of what was available.
And of course, that's why the SSC would have gotten to greater energies, because it was a much bigger scale.
Can I ask a question?
Of course.
Frank, you talk about axion. What is the most unique feature of axion?
Well, the axion is a very, very light particle. The theory has one parameter, so when I speak of axions, there's a range of possible properties. But given this one, it was like the Higgs particle before the mass was discovered. We know everything about it except one parameter, which could be thought of as its mass. But in this case, the mass, instead of being 125 GeV or thereabouts, is more like 10 to the minus 5 electron volts. So really, really small. It's a spin zero bosonic particle, very, very, very feebly interacting. And we believe, well, if you take the consequences of the theory, it would be produced in great abundance in the early universe in a kind of Bose-Einstein condensate that we could hope to detect as a relic today. Depending on what the mass is, you could hope to detect it either with appropriate kinds of fancy antennas, and that kind of experiment is underway at Livermore. They have a very ambitious program. But if the parameter is in another regime, very large, The most promising ways involve either looking for unusual effects around black holes, where axions could form atmospheres around black holes, or very sensitive magnetic resonance experiments that could detect.
Does it have a limit on its speed?
On speed?
Yeah.
But its speed would be cold dark matter. So the speed.
No. The speed would be faster than the speed of light, or less than the speed of light.
The speed of
axion.
Oh no, much less. It's cold dark matter. It's cold by now, so it cools off, and its mass would be just the mass of things that fall into the galaxy and are subject to its gravitational field. So 200 meters per second or thereabouts.
I've got one last question from the audience here for Professor Shears, which is there a project in the works at CERN that you're aware of to look for the force particle responsible for gravity?
For gravity? Oh. Well, the problem with gravity is that we don't have a good testable theory to make predictions to look how best to look for it. We do have some theories that are testable at the LHC, that, like the theory of extra dimensions, which can help explain why gravity is so weak in our four-dimensional space by allowing there to be extra dimensions in space where it can be a lot stronger and where we can see detectable experimental signatures from that feature. So we can test those models at the LHC, and although we haven't seen any evidence yet. Other experiments at CERN, I don't believe there's any others that are testing that sort of physics. There are other experiments at CERN that are testing antimatter, that are making very precise measurements of particular processes to try and deduce new physics beyond the standard model.
Well, I would have put it a different way. We do have quite a good theory of what gravitational effects should be produced at the LHC. It predicts you shouldn't find any.
Yeah, I mean, that's one thing we should really make clear that we maybe haven't, is that you sort of been implicitly said, and I guess once earlier too, that gravity is unbelievably weak. It's the first force we get to know of when we wake up and try and get out of bed. But that's because the whole Earth is acting on us. And in every particle sense, gravity is essentially irrelevant. The gravitational force between two elementary particles is so small, as Frank pointed out, that there's no conceivable laboratory experiment that could measure that. And that makes it very difficult because we have this really wonderful classical theory of gravity, and we'd like to understand if it can be made like the other theories as a quantum theory. But if we can't even test at a fundamental level the classical theory of gravity acting between particles, you can imagine how much harder it is to try and measure the quantum theory, and that's part of the conundrum of the forefront of physics.
But this alternative theory that would include gravity at the same level as the other forces also isn't at the level of sophistication yet to provide predictions that we can test elsewhere. So
it's very speculative.
It's undoubtedly wrong.
Well, nevertheless, as I mentioned, if there were at least one additional dimension that's macroscopically big at the 0.1 millimeter level, something like that, then gravity is strong enough to produce a black hole under the 14 TeV collisions that you hope to achieve. So I mean, that to me would be a really fantastic discovery, because it would imply or suggest the possibility of extra dimensions, which are so important to string theory and everything, right?
It also demonstrates the complementarity, which I'm sure will come up in a number of times in the rest of these talks, between particle physics and cosmology. The universe is a laboratory, which is one of the reasons I spend a lot of time thinking about it as a particle physicist. And there are many experiments you can do with the universe that you can't do in a laboratory, and vice versa. And so the universe does allow us to test many things that we can't test at the Large Hadron Collider, the discovery of dark energy. And in fact, it may allow us to test, even at some level, the quantization of gravity, because the universe has certain properties. So that complementarity allows us to do things that's really important. We need both areas.
If I may, I want to make sure the audience is aware that there is a classical test of gravity underway right now. Everyone on this panel knows about it. It's called LIGO. It's a ground-based observation system where people are looking for waves of gravity. It's located in 2 states here in the United States, in the state of Washington and in the state of Louisiana. And so it's not that we physicists are sort of sitting back saying we can't test gravity classically at all. There is a test underway right now.
And to expand upon that, we're also looking for gravitational waves from the early universe, which will be another great test of classical gravity, but in fact, as actually Frank and I just showed, it may even allow us to test quantum gravity.
Yeah. Actually, well, there are many tests of gravity.
Yeah.
Things fall down after all. And I mean, astrophysicists combine gravity in their calculations with quantum theory every day.
Yeah.
That's what they do. So despite a lot of loose talk, there's really no conflict between gravity and quantum mechanics. The conflicts arise only under much more extreme conditions than are practically realized or realizable in laboratories, or certainly most, maybe all astrophysical situations. So you have to work very hard to find any evidence for quantum gravity, and in fact, none has been found so far. An effect that you couldn't ascribe to classical gravity. People have looked for all kinds of things. People have looked for fifth forces, and which would be significant deviations from Einstein's theory of gravity, and briefly found them, but those were discredited. People test very carefully the equivalence principle, the perihelion shift of Mercury. Many, many experiments are done to test gravity. The people, modern cosmology is based on general relativity, so it provides many indirect tests of Einstein gravity. The trouble, if you want to call it trouble, is that Einstein gravity always works. It works very, very well. It's just like the standard model. And I don't think it should be considered as distinct from the standard model. It really is part of the standard model. If you take the standard model, it gives you a unique prescription for how you should incorporate gravity. That's the prescription we use, and it works.
Well, Frank, I would take issue with that. The back of the envelope calculation predicts a vacuum energy that's 120 orders of magnitude larger than what is actually seen. Right. Well, so I think that's the biggest error ever in theoretical physics.
No, but that's not a legitimate calculation.
No, it is, though.
The real,
it's the Planck scale to the 4th power.
The real answer that you get from that, the real answer you get from that calculation is no answer, because the ingredients that go into it are undetermined. So if you actually did the calculation, you'd find infinity, which definitely shows your theory has failed. In other cases where you encounter infinities, we invoke a procedure called renormalization, which sweeps them under the rug, which has succeeded in the past, and certainly, although it's inelegant, succeeds also in this case. I mean, you just, okay, so it's smaller than it should be, but if you take its value, put in that very small determination, nothing goes wrong. The theory still works. It's perfectly fine.
In fact, the canonical theoretical argument was that because it's infinite, it must be zero.
Yes.
Yeah.
Okay, folks, I think we're going to have to cut off the discussion at this point. We will have an opportunity for continuing the discussion after Alex Filipenko's talk at 3 o'clock. Thank you.
else up
I
here?
don't see anything moving at all. It could just be, if there are already bugs in there, it could be the mice. There could be flies.
Yes.
How about if I stop?
Folks, we're going to start in about 2 minutes, so please find your seats. Okay, folks, we're going to get started now with the next lecture. It's my pleasure to introduce my colleague, Professor of Chemistry, Steve Miller, to introduce Alex Filippenko.
First of all, I'd like to apologize. I'm not going to have any exploding rocket sleds. So, thanks, Josh. If you, like me, are a fan of the PBS program Nova, you might well recognize Dr. Alex Filippenko, who has been a contributor to that show in recent years. I remember one episode in particular in which he was explaining Doppler shifts using the example of a car horn as the car drove down a highway. And as the car passes a stationary observer, the apparent pitch of the horn changes. I remember this instance not for the lesson in Doppler shifts, but because of the two questions going through my head at the time. What kind of astrophysicist gets to drive a classic Ford Mustang down the highway for a TV show? And how can I get that job? It turns out that the answers to those questions are respectively Alex Filippenko and I can't.
Dr. Filipenko earned a Bachelor of Arts degree in physics from the University of California, Santa Barbara in 1979. And after that, he entered the PhD program in astronomy at the California Institute of Technology, where he graduated in 1984. He then accepted a Miller Fellowship to the University of California at Berkeley. And after the term of that fellowship, he accepted a full-time faculty position at Berkeley, and he has been there ever since. And he is now the Richard and Rhoda Goldman Distinguished Professor in the Physical Sciences there. He has done quite well in the intervening period. He was awarded a Guggenheim Fellowship in 2000. He shared the Gruber Cosmology Prize in 2007 and was elected to the National Academy of Sciences in 2009, among his many accolades. He's also one of the most prolific and widely cited astronomers in the world, having already published more than 700 publications. Dr. Filipenko's research largely focuses on identifying and studying supernovae, black holes, and other related objects or events. His group developed and operates the robotic Katzmann Automatic Imaging Telescope, or CATE, on the slide there, which has contributed to their discovery and characterization of more than 300 supernovae since it went into operation. The resulting data have contributed significantly to our understanding of the ways in which stars die. His group has also worked to identify possible black holes and study their relationships to other objects in the sky, such as galactic nuclei and quasars. But Dr. Filipenko is probably best known for his contributions to the work which will be the basis of his talk here today. In the mid-1990s, he was a member of both the Supernova Cosmology Project and the High-Z Supernova Search Team. These groups used observed redshifts in distant supernovae to demonstrate that the universe not only continues to expand, but does so at an ever-increasing rate. This discovery was hailed by Science magazine as the science breakthrough of 1998. It has since given rise to the idea of dark energy and resulted in the 2011 Nobel Prize in Physics being awarded to the heads of the two independent teams. Here's this picture. As impressive as his body of work as a researcher has been, a second talent contributes to Dr. Filipenko driving a classic convertible for a TV show while many others sit at home and watch. He is widely regarded as a great speaker, teacher, and ambassador of science. Among his many teaching accolades, he was named the Carnegie Foundation's 2006 U.S. Professor of the Year, and he has been voted by the UC Berkeley student body as their best professor a record 9 times. And remember, he teaches physics. It is ultimately his place at the forefront of modern astronomy and his ability to communicate its ideas clearly to colleagues and lay audiences alike that make him a natural contributor to Nobel Conference 49. And so please join me in welcoming Dr. Alex Filipenko.
There we go. Well, thank you very much, Steve, for that wonderful introduction. And I thank you all for being here. Wow, a full house. It's actually great that Gustavus Adolphus College is not shut down today, as is our federal government. I was a little bit worried there, yeah. So you all know where to be, here to listen to all these wonderful presentations at the forefront of science. As Steve mentioned, the 2011 Nobel Prize in Physics was awarded for the discovery of the accelerating expansion of the universe. And it was awarded to the leaders of the two teams. Saul Perlmutter, in the middle there, led the Supernova Cosmology Project, and Brian Schmidt, at right, led the High Redshift Supernova Search Team. It was also awarded to Adam Rees, on the left there, a member of Schmidt's team. He was my postdoctoral scholar at Berkeley in the mid to late 1990s when we did the research leading to this discovery. He was charged with analyzing the data. He was the first on the Schmidt team to realize what the data were trying to tell us, and I think it's appropriate that he received a share of the prize as well. I was the only person to have been at one time or another associated with both teams, and if you get me sufficiently drunk, I'll tell you the story behind that. It's unfortunate that there's a tradition among the Nobel Prizes in all fields other than the Peace Prize. They can be awarded to, at most, 3 individuals. And there were 48 others on the 2 teams that contributed to this discovery, and additional astronomers who did groundbreaking work in preparation for this discovery. And, without the hard work of all these other people, these 3 gentlemen wouldn't have been so recognized. My colleague at Harvard, Bob Kirshner, likes to quip, "It's not every day that you don't win a Nobel Prize." Anyway, these 3 gentlemen understood that without the rest of us working hard in the trenches, they wouldn't have been recognized in this way. And so they spent a good fraction of their prize money flying the rest of us out to Stockholm in December of 2011 to participate in Nobel Week. A nonstop set of parties and celebrations, receptions, all in the name of science. It was like the Swedish Super Bowl, actually, but for science. And I'm told that it was all televised, and in particular, the Swedes loved to observe the poor manners, primarily of Americans, at the Nobel banquet. So a topic of much discussion. Anyway, there's the Supernova Cosmology Project led by Saul. At the time, the High Z team, with which I was more associated, was having their team lunch, and I couldn't clone myself, and so I couldn't be in this photograph. But that's one team, and then the high redshift search is shown here right after the awarding of the Nobel Prize to Schmidt and Rees on this team. And the rest of us like to say that we got to participate in nearly everything, all the parties, all the receptions, except for the handshake from the King of Sweden, the gold medal, and a share of $1.5 million. But that's the way it goes. All right, well, my talk today will be on cosmology, that subset of astronomy that deals with the structure and evolution of the universe as a whole. We're interested in some of the grandest questions. How big is the universe? Is it infinite, or does it somehow wrap around itself? What is its shape overall? What is its age? Is it infinite? Is it finite? This is a big time story. You see that? Big time story. When did the universe begin? Well, we now know that it began 13.8 billion years ago. A very long time indeed, but not infinitely long. And that's an amazing discovery, worthy of the cover of Time magazine. And you know that these national magazines want to educate the public, of course, but they also want to make money. And they won't choose a cover story that they think will not sell. But astronomy, and in particular cosmology, they sell. People are interested in this stuff. Cosmologists are also interested in the fate of the universe. Will it expand forever, or will it implode in on itself? This too was a big time story, how the universe will end. And back in 2001, when this cover story was written, we thought we knew how the universe would end, and so there's no question mark there. Now, a dozen years later, we've conducted more research, and we're not so sure how it will end. But I will tell you how we think it will probably end, the betting person, all right? How to lay your odds. Cosmologists are also interested in the fundamental building blocks of the universe. Those are galaxies, gigantic, gravitationally bound collections of tens or hundreds of billions of stars. Now, our Milky Way galaxy would look like this if we could see it from the outside. This is not a picture of our Milky Way. If anyone has such a picture of the Milky Way, please see me afterwards. I'd like to purchase usage rights from you, okay? This is seen from up above. But it's about 100,000 light years from end to end, and light travels, 186,000 miles a second, 6 million miles per year, and it's 100,000 of those units across. So if you were on a planet orbiting a star here, and you sent a radio signal at the speed of light to an alien friend over there, saying, hey, let's go to the Nobel conference, the 49th one, that is. It would take 100,000 years for your signal to reach that friend, and another 100,000 years for the reply to come back saying, well, let's go to the 200,049th Nobel conference, okay? Round-trip conversation of 200,000 years, hardly a stimulating conversation. I'm sorry, this is the way the universe is built. I'm just the messenger here. It's built out of these gigantic galaxies. And there are lots of them. Here's one of my favorite photographs from the Hubble Space Telescope, the Hubble Ultra Deep Field. The telescope stared at just one tiny part of the sky for the equivalent of 2 weeks, collecting light, seeing ever fainter objects. And this is a tiny but representative fraction of the sky. Imagine a grain of sand held out at arm's length. Imagine how small that looks. That's about the size of this picture here. And everywhere it's filled with galaxies. I could spend my hour counting them. 1, 2, 3, 4, 5. That would be pretty boring for you. But hey, it's a rather cushy job. They pay us to sit around and count galaxies. What could get better than that? Anyway, we've taken a number of such photographs, and we can tell that this is representative. So, extrapolating over the whole sky, we can estimate that within the realm of today's great telescopes, there's something like 100 billion galaxies. And that's just in the parts of the universe that we can see. We now have very good reasons to believe that the universe extends far, far beyond the parts that we can see. And everywhere it is filled with these galaxies, the basic building blocks. How do they form? How do they evolve with time? These too are among the central questions of cosmology. So you can see what an amazing, vibrant, intellectually interesting field it is. And I feel very privileged to have been able to work in this field and contribute to the findings. Now, before I move on, let me point out that among the general public, present company excluded because you're at this conference, you're interested, you're somewhat knowledgeable. But among the general public, there's considerable confusion between cosmology, the study of the structure and evolution of the universe as a whole, and cosmetology, the study of hairdos and facials. Now, I admit they sound similar, as do astronomy and astrology, by the way. But they are different. They're spelled differently. In fact, if you write them down, you will find out that cosmetology is simply cosmology with an extra ET in it, like the extraterrestrial. I don't know the cosmic significance of that, but nevertheless, that's how they differ. And they mean rather different things. Now, you might say, surely people don't have this confusion. Show me the evidence. Well, I'm a scientist. I will show you the evidence. Here's a copy of an ad that a colleague of mine placed in my mailbox some time ago. Make cosmology your career. Training and supervision in hairstyling, blow drying, permanent waves, coloring and frosting. You laugh, but these are very important topics, okay? Scalp treatments, body and skin care, style cuts, basic cuts. For further information and interviews, call that number. Now, classes started back in March, so you missed the spring quarter. But I'm sure this will be offered at your local college or university in the next quarter or semester. So if you want to do, as I and many of my colleagues have done, and get to the cutting edge of this field, you need to take a course like this. Well, these guys need a course not only on their own profession, but a course on spelling and proofreading, because in addition to feather here, you see hair slying. Whoops, hair slying. See that? And coloring. Well, that's the British spelling, and my own thesis advisor was British, so I'll allow that one. Anyway, maybe their spell checker wasn't working or something, but they don't even know their own field. Actually, my father-in-law says, you know, Alex, the only real difference between your UC Berkeley course on cosmology and a course on cosmetology is that you don't give makeup exams. Oh my goodness. See, my students have to put up with me every other day. You willingly came here. Puns are a highly underappreciated form of humor, but both my father-in-law and I like puns quite a lot. All right, well, the story of cosmology, in a sense, starts with Vesto Slipher, the observational story of cosmology, an astronomer in Arizona who examined the light from galaxies before it was even fully understood that they were actually outside our Milky Way system. He passed the light of galaxies through a prism, producing a rainbow, a spectrum. From the spectrum, a scientist can tell all kinds of interesting things about the object he or she is studying. We can tell the temperature of the gases, the pressure of the gases, the chemical composition. For example, this line is due to hydrogen. There's neutral sodium. There's singly ionized calcium, that pair of lines. A trained spectroscopist can recognize the fingerprints of different elements and their ionization stages. But we can also tell whether an object is moving toward us or away from us, and how fast. If it's moving toward us, the pattern of these lines produced by various elements remains the same, but shifted toward bluer colors, shorter wavelengths, higher frequencies. And if the object is moving away, then you get a redshift. So the audible version of this phenomenon is quite well known. You hear the siren going like that. And that's because as it's coming toward you, in between the emission of two consecutive wave crests, the siren has moved toward you, making the distance between the wave crests smaller, the wavelength shorter, the pitch higher. Conversely, when it's moving away, during the time between the emission of two wave crests, the object has moved away, thus stretching the wave, giving a lower pitch. Now, if you hear an ee-ah, it doesn't mean that the driver is drunk and can't make up his mind which way to go. It just means you don't have a constant pitch siren. But you can hear that it goes from high-pitched to low-pitched. Well, Slipher noticed that with few exceptions, other galaxies have redshifted spectra. But he couldn't do much else with this discovery because he didn't know the distances of the galaxies. Enter Edwin Hubble, after whom the Hubble Space Telescope is named. He measured the distances of relatively nearby galaxies using a technique I'll describe in a few minutes. And he found something very interesting. They're all moving away, other than those that are so close to us that they're gravitationally bound to us. Forget about them. So they're all moving away. But right now, at a given time, the more distant ones, which generally appear fainter and smaller in the sky, they're moving away faster. Okay? So there's a greater redshift, a greater recession velocity at greater distances. Now, Hubble resisted this interpretation for a while, but we now know that in the case of the galaxies, the redshift is caused by a stretching of space itself, not by the motion of particles through a pre-existing space. So in fact, it's not the classical Doppler effect. Basically, Earth and objects that are bound, that are solid, we're bound by electromagnetic forces, we're bound to the Earth by gravity. Anything that's bound to be strong doesn't expand. You may think you expand after a big lunch, but that's your fault, that's not the universe's fault. But the space away from strong gravitational fields does expand, and electromagnetic waves, light, expands with it. And so you can see that you start out with a short wavelength blue wave, and it gradually becomes longer. That's the cosmological redshift. It's an expansion of the universe. And there are ways we can now distinguish that from motion of objects through a pre-existing space. And it's definitely an expansion. So from our perspective in the Milky Way galaxy, a snapshot of the universe looks like this. All the galaxies are moving away, and the more distant ones are moving faster than the nearby ones. Now let me pause here for a second, because there's something kind of strange about this diagram as I've drawn it. What's peculiar about it? Yeah, a bunch of people said it. We're at the center. Why would that be? Do all these other galaxies not like us? Is it something we said, or do we smell? Are all these other galaxies lactose intolerant? Get it? Milky Way galaxy, lactose intolerant galaxies. When I talk about cosmology to my introductory astronomy class at Berkeley, I say, what is it? Are we from Stanford or something? Big rivalry, okay, academic and athletic. No, first of all, with due apologies to those of you who might be Stanford alumni, it's an outstanding institution, it really is. Just not quite as outstanding as Cal. Anyway, we don't think we're in any privileged position. We think that this is a property of a uniformly expanding universe. Let me show you this little demo, which I noticed was on the slide that started the presentation that Steve had. Here's a hypothetical one-dimensional expanding universe where the ping pong balls are the galaxies. They're gravitationally bound. They're not expanding. And the rubber is the space between them. So fix your attention on this ping pong ball. All the others are moving away. But the same could be said from the perspective of any other ping pong ball. And let this rubber be either infinite or wrapping around itself. The edges are irrelevant here. I'm not trying to fool you in any tricky way. All right? You get this apparent centrality in the universe without actually being the unique center. Notice also that the more distant ping pong balls move faster than the nearby ones because every little bit of space stretches. And the more space there is to begin with, the greater will be the stretching in a given amount of time. So this explains Hubble's relationship. It works not just in one-dimensional universes, works in three-dimensional universes. Here's an expanding loaf of raisin bread where the dough is uniformly filled with yeast. You let it bake for an hour, all the guys move away from each other. Again, imagine an infinite universe or one that wraps around itself. This one thinks that it's at the center, but all the others say that they're at the center as well. And in fact, there is no unique center, at least not in the dimensions that we can physically probe. There may be a center in a mathematically definable dimension, and I can discuss that later in the Q&A with, say, a balloon. Anyway, notice also that the more distant raisins move away faster than the nearby raisins. This one went from 5 centimeters to 10 centimeters. This one went from 10 to 20 in the same amount of time. That's because, again, every bit of space expands. The more there is to begin with, the greater will be the expansion factor. Okay, so that's the expanding universe. And with today's modern telescopes, we've measured pretty well the current rate of expansion. And you might think we're done. But we're not done, and this goes all the way back to Newton, who considered gravity. And here's an apple. You can't give a talk about gravity without using the proverbial Newtonian apple, so here it is. Boom. He supposedly watched it fall from a tree, and he wondered whether whatever it was that makes it fall is somehow related to what keeps the moon in its orbit. And Frank showed the interesting diagram from the Principia, imagining the cannonball fired at different speeds. Indeed, there is this deep connection, this law of universal attraction. So if we toss the apple up, the mutual gravitational attraction between the apple and the Earth slows it down. And in fact, it comes to a halt at the top and then comes back to my hand. So suppose you have a dense universe, a lot of matter per unit volume. Then every unit volume will be pulling on every other unit volume a lot, slowing down the universe quite quickly. In that case, the currently expanding universe would someday stop expanding and then collapse. It would implode on itself. So in this case, you could say Big Bang, Big Crunch. Starts with a big bang, ends with a big crunch, high densities, high temperatures again. Or you could say Big Bang gnab gib, which is Big Bang backwards, okay? So that's what kind of universe you would have if it were a dense universe. If you were lying on your back looking at the galaxies through a telescope, you would see them getting smaller and fainter, and you would say that's a well-behaved universe. And then you would notice something a little bit odd. They would get brighter and bigger again, and right around now you'd start getting a bit nervous, and then it'd be, goodbye, cruel world, and you would be crushed into oblivion, all right? So that's one possible fate of the universe. But there's another possibility. Suppose I had eaten my Wheaties this morning. In that case, I could heave this apple, forgetting about the technical difficulty of a ceiling here, I could heave it at a speed greater than or equal to Earth's escape speed, around 11 kilometers per second. And in that case, although it would be slowing down forever, it would never come back. It would either approach zero speed as time approaches infinity, or it would approach some constant positive speed as time approaches infinity. So that would be an apple that never comes back. In a low-density universe, all the galaxies are pulling on all the other galaxies, slowing down the expansion of the universe, but not enough to ever have it implode in upon itself. That would be an eternally expanding universe, and if you were watching galaxies on a dark Minnesotan night, you would see that they keep getting fainter and smaller, although at a progressively slower rate. So eternal expansion versus the gnab gib. Which one is it? We want to know. Doesn't matter that we'll not be around to see what will actually happen. We just want to know. That's what drives all scientists. How might we proceed to find out? Let's go back to the apple. Measure the speed of the apple at different stages of its path. See whether it's been slowing down a lot, in which case it'll stop and come back someday, or not slow down a lot, in which case it'll keep on going away from the Earth forever. Examine the past history of the motion of the apple to predict the future. So in a similar way, examine the past history of the expansion of the universe in order to determine the fate of the universe. Well, to do that, we need to know how far back in time we're looking. Here are galaxies that are far away, say 1 billion light years away, 4 billion light years away. Maybe that little blob there is 9 billion light years away. You're seeing them as they were 1, 4, 9 billion years ago, because it takes time for light to travel from there to here. In fact, fun fact to know and tell, light travels about a foot per nanosecond, a foot per billionth of a second. So I'm seeing Steve, not as he is right now, but as he was maybe 25 or 30 billionths of a second ago. He may not even exist anymore. Oh, he does. Good for him. He's still on this good earth. You see the sun as it was about 8 1/3 minutes ago, because that's how long it takes to traverse 93 million miles, okay, the light. You see the typical stars in the sky. The bright stars are some tens or hundreds of light years away. In a few cases, 1,000 light years. So you're seeing them as they were tens or hundreds or thousands of years ago. So if you look at galaxies that are 1, 4, 9 billion light years away, you're seeing them as they were 1, 4, 9 billion years ago. You're looking back in time. Telescopes allow us to look back in time. And encrypted in the light from those galaxies is information about how much the universe has expanded during the time that the light was traveling. That information is the redshift, okay? So if you know distances, hence look-back times, and you can measure redshifts, then in fact you can reconstruct the past history of expansion of the universe. So how do we determine distances? For relatively nearby galaxies, it's pretty easy. This is the technique Hubble used. This is a Hubble Space Telescope picture. He didn't have those, but in such a picture you can sometimes see individual stars. Let's call that one Chuck, just for kicks. And let's say we know through studies of Chuck that it's the same kind of star as Betelgeuse. The left shoulder of the great hunter Orion in the sky, okay? And this is a relatively nearby star. We know how distant it is. We can measure how bright it appears to be, and thus we can calculate the true power. If we now say, well, Chuck is the same type of star, and there are different kinds of stars, by the way, you can figure out how far away Chuck must be in order to look this faint. And if you do the same thing with other stars, Tara and Frank and Lawrence and others in this galaxy, and you get the same result each time, well, that builds confidence that your technique is correct. And in fact, Hubble used a type of star known as a Cepheid variable. Now, this is the same principle by which you judge the distance of an oncoming car at night. You've calibrated how bright the headlights are of a car of known distance, 6 feet away. You say, ooh, those are pretty bright. And then you look at dimmer headlights and you almost intuitively, almost instinctively calculate the distance of the car. And if you're not very good at doing this, then you shouldn't be driving at night, okay? You get a consistency check through the angular separation of the two headlights. That gives your brain a consistency check because the angular separation decreases with increasing distance. Well, cars, stars, it's the same idea. Find stars of known luminosity or power or oomph, measure how bright they appear to be, and thus determine their distance, and thus how far back in time you're looking. Now you might say, well, that works fine for nearby galaxies, but what about these galaxies here? You know, how do you know that that one's 4 billion light years away and not 5 or pi or something like that billion light years? All the stars are too faint to be seen individually, and they merge together. So it sounds like you're hosed if you want to look far enough back in time in order to really trace the expansion history of the universe. But you're not hosed. There is one type of star that's so brilliant that it can be seen at distances of billions of light years and separated from its neighbors. Anyone know what kind of a star that is? A supernova. Someone said a type 1a supernova. Ooh, boy, you know a lot. Okay, want to come give this talk? Anyway, so yes, a supernova, an exploding star. Now, very few stars explode at the end of their lives, but those that do can become millions or even several billion times as powerful as the sun. And here's one in a galaxy where I've sped things up a bit. It typically takes a few weeks to rise and many months to decline. At its brightest, that supernova is about as bright as the central few billion stars in this galaxy. They're really bright. If our sun were to do this, and it won't, don't worry, be happy, but if it were to do this, sunblock of 50 just wouldn't cut it, folks. You'd need sunblock or supernova block of a few billion to protect yourself. But that's not going to happen, all right? Okay. Well, you first have to find a whole bunch of relatively nearby supernovae in galaxies whose distances have been measured through observations of relatively normal stars in those galaxies, because it's the combination of known distance and measured brightness that gives you the luminosity or power of a supernova. But you've got to find a bunch of these things because there might be more than one way in which stars can explode. Indeed, there are several ways in which stars can explode. And even given a single physical mechanism, you have to measure whether there's a dispersion, a variation in the peak power. So you've got to first find a bunch of nearby ones. Now, this is a bit hard, actually, because in a typical galaxy, a star might explode only once every 30 or 40 years. So if I were a really cruel advisor, I would have each of my students staring through the eyepiece of a telescope at one and only one galaxy, preferably at night. You see more stars and galaxies at night than during the day. Until the student finds a supernova. And then we would let the student graduate and move on to greener pastures. Meanwhile, I will have had decades worth of slave labor from said student. Now, there are some crimes that are so egregious that even a tenured professor can and should get fired. I mean, we can't take advantage of students in this way. But we can improve the odds by observing lots of galaxies. So let's say there's one supernova per galaxy per century. Statistically, that's the same as one supernova per 100 galaxies per year. Each of these 100 galaxies will produce a supernova sometime in the next century. Odds are that there will be one a year. Maybe some years there will be 0, some years there will be 2 or 3, but roughly one a year, okay? Or if you monitor 1,000 galaxies, there will be 10, all right? So that's getting to be pretty good. I could have my students scanning thousands of galaxies until they find several dozen supernovae. Then we let them graduate and move on to greener pastures. But this would be considered, you know, terrible punishment to the student as well, right? This would be an egregious crime, and I would probably get fired. Because, you know, students need to study and sleep, and most importantly, party, all right? Fortunately, with modern technology, we have a better technique. We attach digital cameras, like your little CCD camera, to the eyepiece end of a telescope, and we take photographs of thousands of galaxies throughout the sky, and we simply look for arrows. And where there's arrows, there are exploding stars. You see, it worked once, twice, 3 times, 4 times, 5 times. By rigorous mathematical induction, I conclude that this technique works every time. Well, obviously, it can't be quite that simple, otherwise we wouldn't give degrees for this kind of work. A number of teams, including my own, have developed largely robotic telescopes that do the work for us. And here's the telescope that my team runs at Lick Observatory, the Katzmann Automatic Imaging Telescope. It's been expertly programmed to look at over 1,000 galaxies a night, nearly 10,000 in a week. And it compares the new pictures with the old pictures, and it finds supernova candidates. Here's an example. Wei-Dong Lee, my close associate, expertly programmed it. Here's a before picture of a galaxy, and then here it is again. And there's something new. There's this arrow here. Well, the arrow was put in with Adobe Photoshop or something. The new thing is this little guy there. And that's a supernova candidate. It's not necessarily a supernova. It could be a cosmic ray, a charged particle that interacted with the detector in a way that looks like a star. Or it could be an asteroid flying through the field of view with Earth's name written on it. Astronomers will someday save humanity by finding the asteroids decades before they hit. And then physicists and engineers will figure out a way to deflect them. So you know, together we will save humanity. Anyway, one person's garbage is another person's gold. We don't care about the asteroids. We screen out most of the several dozen candidates that are found automatically by the system each night and focus on the 1 or 2 that appear interesting. And this is done by slaves, undergraduate students who, through their superior eye-brain combination, examine the candidates at the end of each night and determine which ones are likely to be genuine supernovae and worthy of further consideration. And I'm very proud of my team. For about a decade, we actually found more nearby supernovae than all other teams in the world combined. And actually, Steve, our current count is closer to 1,000, exceeding 900. So you saw an old reference. I should update that. Let me know where you found the 300, okay? Because that sounds a little bit embarrassing compared to 900 or 1,000. Anyway, I'm very proud of my team. And this fellow at the left is kind of interesting. There he is. I like to say that he's the cosmetologist in our group, okay? Maybe he's trying to get a date or something, and then I realized I teach at Berkeley, and so this is not at all unusual. Every week I have a pizza lunch for my group. I bring them pizza, and they justify their existence for the past week. Anyway, through studies that we've been doing, and many other teams as well, and by the way, the studies with Kate did not contribute to the Nobel Prize winning work. Other studies had already calibrated supernovae pretty well before that, but we've been refining the technique since that time, and a number of groups have been working on this, okay? Nevertheless, we've contributed to this, and we and many others have found that when you pass the light of supernovae through a prism and produce a spectrum, you find that they come in 2 main types. There are now many other types, but they're called type 1 and type 2. Now, we could have called them Fred and Jean, but we call them type 1 and type 2. Astronomers are kind of boring people. Type 1s don't have any evidence of hydrogen in their spectrum. They have everything else: calcium, magnesium, iron, sulfur, silicon, oxygen, but no hydrogen. This is important. because hydrogen is by far the dominant element of the universe. By the way, these supernovae produce and disperse into the cosmos the heavy elements of which we are made. So the carbon in your cells, the oxygen that you breathe, the calcium in your bones, the iron in your red blood cells, all of these elements were generated in stars prior to and during their explosions and ejected into the cosmos, making them available as raw material for the formation of new stars, planets, and ultimately life. And this is what Sagan meant when he so eloquently said, "We are made of star stuff." He did not discover this, but he popularized the notion. Quite literally, the heavy elements in your bodies were created by stars many billions of years ago. So you are not just within the cosmos, but part of the cosmos in this very direct way. If that does not grab you, you were either brain dead or you were momentarily thinking about something else, like the government shutdown or how the football team did or something. I know it happens to me all the time, so let me not accuse you of being brain dead. But anyway, type 1s, no hydrogen. Type 2s, they do have hydrogen. Okay. The type 1s in particular have a subclass called type 1a, which is thought to come from a weird kind of a star, kind of like what our sun will turn into at the end of its life. It'll be what's called a white dwarf, made out of degenerate matter, not because it's morally reprehensible, but it's very, very dense, and this is the term that quantum physicists give to it. And if you're part of a binary system, which our sun is not, then the white dwarf can steal material from the other star, grow in mass, and become unstable at some point and explode. Or it can merge with another white dwarf to which it's gravitationally bound. And that gives rise to a type 1a supernova. They are very luminous. They're nearly all the same. There are some differences among them, and we had to generate ways to read the label on the light bulb, but I won't go into those details. All right. So because of the work of many, many people, by the late 1980s, early 1990s, it was already recognized that type 1a supernovae are excellent cosmic beacons with which to determine distances of galaxies and hence look-back times. So two teams set off to find distant examples of type 1a supernovae and to measure them. And a given supernova is used in two ways. Its apparent brightness is used to determine the distance and hence the look-back time of a galaxy, using the inverse square law of light, which I described before. The recession speed, or the redshift, due to the expansion of space, is measured from the spectrum. So the supernovae are critical for these two reasons: measuring distances, hence look-back times, and redshifts. And it's the relationship between look-back time and redshift that traces the expansion history of the universe. The teams found the supernovae using telescopes primarily in Chile, equipped with wide-angle cameras that could survey thousands of galaxies at a time. This is a picture, roughly the area of the full moon. Now, the full moon is not rectangular in shape, but this has about the same area. And nearly every little blob you see here is another galaxy, not a star in our own Milky Way galaxy. There are thousands of them. You know, with your naked eye, the sky is dominated by stars in our own galaxy. But when you take deep photographs with big telescopes, the sky is dominated by other galaxies, okay? So if you take a bunch of photographs of different parts of the sky like this, and then repeat the process 3 weeks later, some of those roughly 100,000 galaxies will have produced a type 1a supernova. They're pretty rare. They're once per galaxy per several centuries, actually. Nevertheless, with 100,000 galaxies, any sample examined 3 weeks apart will reveal a dozen or so of these things. You can do the math. So they're found by digital subtraction. Here's part of an image taken on the 7th of April, 1997, another one the 28th of April. You subtract the earlier one from the later one, you get a bunch of noise. That's okay. Every measurement process necessarily has some noise associated with it. But here, cleverly placed in the middle of the square, is something that looks like it might be real. And a Hubble picture of it a few weeks later reveals it as well, and it's marked with an arrow, so it's got to be a type 1a supernova, right? Well, it's not that simple. You have to get the spectrum, the fingerprint to be sure, and you need the spectrum in order to determine the redshift. And that was my main role on both teams. I'm a spectroscopist by training. I've studied supernovae since the mid-1980s, and I have access to the world's greatest optical telescopes, the twin 10-meter Keck telescopes in Hawaii. These are gigantic light buckets with which we can collect the data and disperse the light into a spectrum. These are amazing machines to use. 36 hexagonal segments structured in a honeycomb pattern, acting in unison like one mirror, but much, much cheaper to make. And this technique was invented by Jerry Nelson when he was at Berkeley. He's now at Santa Cruz. Here's Fred Chaffee, a former director of Keck, showing for perspective the size of the telescope. And he usually wasn't there when we were taking data. The extra light gathering power provided by his pupils is dwarfed by the glass here, so this is just a PR shot. Anyway, I would get spectra of the supernova candidates that my colleagues got, and they would look sometimes something like this. Here's a nearby type 1a, brightness versus wavelength, a lot of squiggles, and one at redshift 0.455, which means it's roughly 5 billion light years away, has the same squiggles. Some small differences due to noise and stuff, but no great differences. And when we got data like this, well then, I was a very happy camper. And now you see the real reason we build observatories in Hawaii. I find San Francisco Bay Area water to be too cold for swimming without a wetsuit. Well, here are 3 examples of type 1a spectroscopically confirmed supernovae, marked with arrows. And the punchline is they're faint. They're really, really faint. And you might say, well, big deal. They're in these scrawny, pathetic-looking, faint galaxies that are obviously far away. I mean, here, look, you can't even see the galaxy there. I mean, it's there, but you can see the supernova. So these are obviously very distant galaxies, so you expect the supernovae to be faint. That's true, but these were fainter than they have any right to be. They imply greater distances than could be accommodated in a well-behaved universe. Distances that were greater than expected based on their redshifts in any well-behaved universe. Let me give a simple example. Suppose I go back to the apple, and suppose I toss it and I assume the universe is just 1 second old, okay? I can measure the distance of the apple from my hand after 1 second. That's some distance. But the apple has slowed down in its upward journey. If the mass of the Earth were less, then for the same toss, there would be less deceleration, and in 1 second, the apple would go farther. Now, I can't make the mass of the Earth less, but I can do the next best thing. I can toss the apple faster, and it's the same desired effect. It goes farther in 1 second. Now suppose the Earth didn't exist at all, and you ignore Jupiter and the sun and all those other things. Would there be any reason for the apple to slow down? Hey, physics students, any reason for it to slow down at all? No, that's just Newton's first law of motion. It would keep on going in the same direction with a constant speed. So in 1 second, it would traverse an even bigger distance, right? But that's the biggest distance you can get under the influence of gravity or no gravity. What we found was that the supernovae, the galaxies in which they're located, the apples, so to speak, were at greater distances than you could have reached in the amount of available time. And we had to rule out other possibilities for what might be going on, like maybe there's fog in the way making the supernovae look too faint or something. But we ruled all that out. So the natural interpretation is that they're at a greater distance. To achieve that greater distance, what must you have? Acceleration. That's right. If I attach a rocket to this apple and it goes zoop, then in 1 second, it can cover a greater distance than that which is covered with no deceleration. Just no forces acting upon it. Now you might be wondering, well, wait. Your argument depended on an assumed age of the universe. What if it were 2 seconds old? Then obviously the apple goes farther in 2 seconds. Good try if that's what you were thinking, but the detailed argument is independent of the assumed age of the universe. Really, the measured distances were greater than expected given the redshifts in any decelerating or constant expansion universe. And so the implication was acceleration. And I was privileged to be able to announce this result at a meeting in the Los Angeles area in late February of '98. The headline that came out was "Astronomers see a cosmic anti-gravity force at work." We use this term anti-gravity hesitantly because people ask us, can we gather this stuff, whatever it is, and attach it to our cars and levitate over traffic jams? And the answer is no. It's either a property of space that cannot be harnessed, or there's so little of it that it'll never be harnessed with any, reasonable amount. Nevertheless, it has an anti-gravitating-like effect, all right, in that it accelerates the universe rather than decelerating the universe. A very strange thing. And no one would have paid attention had there not been two teams that came up with the same result at about the same time. This forced other physicists and astronomers to take the results seriously. The High-Z team submitted their paper in March of '98, and it was published in September of '98, and the Supernova Cosmology Project submitted in September of '98, and it was published in June of '99. And so because there were two teams that got the same result, people had to take notice. Maybe the technique is flawed. That's still a possibility. And so every scientific result has to be verified through independent techniques, for sure. But at least there were two teams using the same technique that got the same answer. That probably meant that neither one of them made some really stupid error like a programming error, 2 + 2 = 5, which is a huge embarrassment and causes you to lose your funding. Well, by the end of 1998, no one had found any obvious flaws in the methods by which the data were collected or analyzed or interpreted. So the editors of Science magazine proclaimed this to be the single most important discovery in all sciences in 1998. And the caricature of Einstein is surprised here. You might think it's because he's blowing multiple universes out of his pipe. Now, Lawrence might talk about this later, the fact that we think that there are multiple universes and they come from the pipes of famous theoretical physicists. Well, the first part of that statement might be right. Okay, there may well be multiple universes. I'm actually pretty convinced that there are, but I have no definitive evidence. No, he's surprised because this one universe is expanding faster and faster with time rather than more and more slowly, as a well-behaved universe would. He's doubly surprised because he has a sheaf of papers here where there's an equation. The Greek letter lambda equals 8 pi g, Newton's constant, times the density of the vacuum. Now you might say, whoa, the Nobel Conference organizers have sunk to new lows, inviting this bozo from Berkeley, who's talking about the density of the vacuum. You were taught on your mother's knee that the vacuum is sheer emptiness, nothing at all, zilch. How can it have a non-zero matter or energy per unit volume? Well, again, I'm just the messenger here. This was Einstein's idea. He was a lot smarter than I am. He came up with this possibility when, in 1917, shortly after developing the general theory of relativity, he realized that, the universe should be either collapsing in on itself because the gravitational force between galaxies should be causing them to implode on each other, or maybe the universe was started out in an expanding state, in which case it should keep on expanding, but there was no evidence for anything but a static universe. The sky didn't appear to be falling. There was no evidence for change. He and many others found a static universe to be aesthetically pleasing. So he introduced an idea, the cosmological constant, an effect of unknown physical origin, which acts in a direction opposite to that of gravity and has a magnitude exactly equal to that of the attractive gravity. That would prevent a collapsing universe. It's like this apple. It all goes back to the apple. If the net force is 0, the apple doesn't move, or at least it doesn't accelerate. If the net force is non-zero, then it accelerates. You know, George Lucas said, "May the force be with you." No, no, no. May the net force be with you. He has to go back to freshman physics, okay? The force may be with you, but if some other force is against you, then you're going to lose. May the net force be with you, okay? Here the net force would be 0. Einstein didn't like this because it appeared to be a mathematical fudge factor that did not make the equations mathematically wrong, but it made them look less aesthetically pleasing. There had to be this fine tuning between the size of the upward arrow and the downward arrow, for which there was no real physical reason. And there was certainly no experimental evidence in a laboratory for this effect. And this effect implies that the vacuum energy is non-zero and that it's repulsive. And many physicists found that to be a repugnant idea. So Einstein never liked the cosmological constant. And when Hubble, 12 years later, discovered that the universe isn't static after all, the whole physical and philosophical motivation for the cosmological constant vanished. Einstein renounced the idea, supposedly as having been the biggest blunder of his career. Because had he not introduced it, he would have predicted, as some theorists did do, that the universe is likely to be in a dynamic state, either collapsing or expanding. He could have been famous had he not introduced this idea. So here he is, sad that he ever introduced the idea. Now, I don't know that that's what he's thinking, but it could be what he's thinking. What have we done the better part of a century later? We've reincarnated the idea, not to have a static universe, but one which over the largest scales is accelerating, is expanding faster and faster with time. So here in this room, the down arrow dominates. Everywhere in our solar system, down. In our galaxy, down. In our local cluster, our local group of galaxies, down. But as you get to sufficiently large scales of order 100 million light years, the up arrow dominates and the universe expands faster and faster with time. And if Einstein were around now, he would see that maybe his biggest blunder was actually his greatest triumph, the idea of such an effect. The only blunder was the small mathematical, the arithmetic error of giving an equal magnitude to the two arrows. And so maybe Einstein's reaction would have been something like on the cover of Science magazine. Well, the discovery that was initially made with supernovae that were 4 or 5 billion light years away, that meant that in the last 4 or 5 billion years, the universe has been accelerating. If it's being accelerated by something like the cosmological constant, whose effect per unit volume is always the same throughout the history of the universe, then there's a clear prediction. Long ago, when the universe was denser, it should have been slowing down in its expansion. That's because galaxies were closer to each other, so attractive gravity was bigger than it is now, and moreover, the amount of volume between them was smaller, so the cumulative effect of the repulsion would have been smaller. So in a sense, gravity dominated over anti-gravity, and as the universe expanded, one declined, the other got bigger, and at some point in the past, they crossed each other. So the prediction was that early in the history of the universe, it should have been decelerating. So Adam Rees was the principal investigator of a project using the Hubble Space Telescope with which we found more distant examples of supernovae, 6, 7, 8, even 10 billion light years away. And we found that indeed, for the first 9 billion years of its history, the universe was slowing down. And it's only roughly in the last 5 billion years that it has started speeding up. This transition from slowing down to speeding up mathematically is known as a jerk. So in a sense, we measured the cosmos to have gone through a jerk. And the New York Times headline that came out was, "A cosmic jerk that reversed the universe," and there's my former postdoc, Adam Rees. Now, I start getting all these phone calls, "Hey, who's this jerk you work with who reversed the expansion of the universe?" And Adam's mother was not very pleased with this juxtaposition. All right, well, What is the stuff that's causing it? It's not the visible matter in the universe. Visible matter always pulls. Even antimatter, we think, pulls. It's a positive, regular form of energy, although I don't disagree with Tara. It should be measured before we can completely claim that, but everyone believes it pulls. So antimatter is not going to do it. Dark matter doesn't do it either. By the way, there's dark matter there. It's not that hard to detect, Tara. There, you know. What's the big deal? No, anyway, we know that there's a bunch of dark matter there precisely because this cluster of galaxies is gravitationally bound. The galaxies are moving around so fast, you can measure that with spectra, that it would quickly disintegrate unless they were bound by extra matter. Indeed, it's the extra matter that causes those speeds. And that argument was actually first made by Fritz Zwicky in the early 1930s, one of my heroes, an astrophysicist at my graduate alma mater, Caltech. He was decades ahead of his time on a number of issues, but he wasn't believed very much and he wasn't well liked, in part because he was arrogant and abrasive and didn't think highly of the intellectual capacity of his Caltech colleagues. Now, he might be showing you here what he thinks of the typical brain size of one of his faculty colleagues. And again, I don't know that that's what he's thinking, but it could be what he's thinking. And he is on record as having referred to his colleagues as spherical bastards, because, you know, they're bastards any way you look at them. A sphere is the only object that looks the same from all directions. I do not encourage you to start referring to your friends as spherical bastards. You will quickly end up friendless. But anyway, Zwicky came to the idea of dark matter in an oblique sort of way. I mean, that's the genesis of it. And then decades later, Vera Rubin came up with the same explanation for the fact that spiral galaxies, which are spinning quickly, don't appear to be disintegrating. And just as Zwicky was ignored for a long, long time, Rubin and her colleagues were ignored as well. But now, as you heard earlier this afternoon, dark matter is like the big thing in astrophysics, eclipsed only, in a sense, by dark energy, the term that has been dreamed up for whatever it is that's causing the acceleration. You know, it's not luminous matter, it's not dark matter, it's not antimatter, it's something. It's some form of energy, but we can't see it, so it's dark. And it's mysterious, so it's dark in that regard too. Dark energy, a term coined by Michael Turner at University of Chicago, a theorist. It's regrettable in a sense, because if there's one equation people have heard of, what's that equation? E equals mc squared, right? Most people have heard of it, even though the actual understanding of it is actually pretty profound and subtle. But I'm continually being asked, are dark energy and dark matter just two sides of the same coin? And the answer is almost certainly not. Dark matter pulls, dark energy pushes. They appear to probably have very different physical origins. But in honor of the discovery of the accelerating expansion of the universe and the implication of dark energy, my wife Noel made the following t-shirt, which was distributed to members of the Nobel winning teams. Dark energy is the new black. A limited edition. By the way, the other possibility for explaining acceleration is that Einstein's general theory of relativity is incorrect on the largest scales. That's an amazing conclusion as well, if correct. Most theorists seem to be focused on dark energy being the explanation rather than relativity being wrong. But in interest of completeness, let me just mention that. What is the dark energy? Well, we don't know. I think it's probably the vacuum energy. In other words, these little things, virtual particles, are created in pairs and live for a very short time. We know that that happens. Their presence affects the measured energy levels of the electron in a hydrogen atom, for example. But they're fleeting. And it was always thought by physicists that, in a sense, for every positive energy fluctuation, there's a negative energy one, and so the total ends up being zero. Mostly, as you heard during the discussion, because if you do the back of the envelope calculation, you actually come up with an infinite vacuum energy. And you can get it down to 10 to the 120th power with a little trick, or maybe 10 to the 55 power with another little trick. But the point is, it's a real problem, and everyone had assumed that it's zero. But if there's a slight non-cancellation with a positive net energy density, this has the desired effect of expanding space away from gravitational fields like that of Earth faster and faster with time. And all the evidence seems to be consistent with that. But another idea is that dark energy is some new kind of energy associated with a new field, kind of like the Higgs field about which you heard from Tara, but different from it. And it goes by the generic name of quintessence, like the Aristotelian fifth essence. But there are hundreds, if not thousands, of different models. Now you might say, well, wait a minute. Before I close, I've only presented to you evidence from supernovae. What if the technique is flawed? Could be flawed. So, as I said, it's important in science to have other independent techniques, and I won't go into them, but let me just say very briefly that there are now many other techniques, in part measurements of the microwave background radiation, and I believe my colleague George Smoot will be discussing that tomorrow. But a number of different ways of studying the microwave background radiation and the little tiny temperature fluctuations which are associated with density variations in the early universe, they give rise to the same conclusion. And one piece of evidence is that if you take those little tiny density variations when the universe was just 380,000 years old, and you let gravity sculpt the universe for the next 13.8 billion years, and you ignore dark energy, and you do your computer simulations, then you find that the formation of galaxies and clusters of galaxies and voids doesn't quite end up resembling the observed universe now. Whereas if you include dark energy plus gravity and rerun these simulations, then the growth of galaxies and clusters of galaxies and voids ends up now at redshift 0, giving us a structure that actually looks like the observed structure of the universe. Okay? And there are other arguments as well. So in the end, when you put everything together, we come up with this pie chart, a little bit updated using the Planck results, which George will probably discuss, a little bit updated pie diagram compared with what Tara showed. For years, we'd been saying dark energy is 73%, but it's more like 70, it appears. So the dominant stuff of the universe averaged over billion light-year diameter volumes, okay? Not this room, let me emphasize, okay? But giant volumes filled with what we thought was empty space. Well, it's not empty. It's got this dark energy. When you add it all up, it dominates. And we don't really know what it is. For the youngsters among you, if anyone tells you that physics is dead, there's nothing left to be discovered, you tell them, what about 70% of the universe? Nay, what about 95% of the universe? Because most of the remaining is this dark matter. And we don't really know what that is. I think it's probably a WIMP, but I'm not sure. Okay? So we don't really know what 95% of the universe is. We know pretty well 5%. And in fact, the stuff that easily shines, stars and planets and stuff, is only 0.5%. That's the only part we understand well. So in a sense, we're the debris of the universe. We're the afterthought of creation. That's not to say you're not important. You are to yourselves, your family, your friends, your loved ones. But you're not made of the dominant stuff of the universe. The dominant stuff is the dark energy, and we don't know what it is, followed by dark matter, and we know only a little bit more about what that is. And dark energy is also important because it is widely thought to be a quantum scale phenomenon that acts everywhere and thus dictates the dynamics of the universe overall. So it's the one of very few observational tests of quantum theories of gravity or string theories, those theories that are attempting to unify the two great pillars of modern physics, quantum physics, the physics of the very small, and general relativity, the physics of the very large. Any such theory that's incompatible with dark energy or a failure of general relativity can be ruled out as not being a viable candidate theory. So the implications of the acceleration have been extreme. That's why it was awarded, the discovery was awarded the Nobel Prize. And finally then, let me go back to the question I asked, how will the universe end? Well, it's pretty clear that if the dark energy continues to be repulsive, then the universe will expand faster and faster and faster with time as the dark energy dominates more and more over attractive gravity. A runaway universe, so to speak. So if you want to actually see galaxies like this one with your very own eyes through a telescope, you'd better go and look pretty soon in the next few tens of billions of years. Because beyond that time, galaxies will have been whisked away to such great distances that they will be too faint to see, and the universe will be cold and dark and empty. That's what we thought 12 years ago. But theorists like André Linde at Stanford and others have pointed out that we don't really know what the dark energy is. And there are models, theoretical models of dark energy, in which the sign changes in the future from one of repulsion to one of attraction. There's a historical precedent for that in the inflation of the early universe. That's something that acted like dark energy when the universe was a tiny blink of an eye old, but then it reverted to an attractive kind of gravity. But maybe, today's dark energy will do that someday. If that's the case, and if there's enough of it, then it turns out that despite accelerating right now, it will someday start decelerating and maybe even will come back. And so there might be a big crunch after all. But I think the data are compatible right now, best with eternal expansion, the cosmological constant, and that we will live in a universe that is a runaway universe effectively. Well, to close, let me point out that the famous American poet Robert Frost in 1920 certainly didn't know about anti-gravity and the accelerating universe. He didn't even really know about the two possibilities of an eternally expanding and a collapsing universe that hadn't been studied in great detail by cosmologists yet. But in the context of, I guess, Dante's Inferno, or some say in the context of a conversation he had with Harlow Shapley, an astronomer who said the sun might blow up or the earth might someday freeze, he came up with a poem that, in retrospect, is relevant to what I had to say right now. It's called Fire and Ice. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So you see, in the context of what I discussed today, Frost would prefer a universe that ends in a big crunch, hot and compressed like fire. Hot like fire. Fire isn't compressed, but whatever. But if the universe and he had to perish twice, then eternal expansion and an ending in ice would be okay with him, and that's perhaps appropriate given his name, Robert Frost. Thank you for your attention.
Thank you, Professor Filipenko, for that mind-expanding lecture. We will take a few minutes to gather our panel up front, and at the same time, our ushers will begin to pass out pieces of paper for you to submit questions. Thank you.
Sorry for going a little bit over there.
What's that?
I went a little bit over.
Well, that's okay. Yeah. I don't think anybody's going to complain.
Yeah.
Very entertaining.
And we have until 5, I guess.
Yeah, we got lots of time.
Oh, okay.
No, no, it's just
Oh, yeah, okay. Good. Yeah, all right, good. Yeah.
How's that work?
Oh, thank you.
QR code back, actually.
Okay, folks, please find your seats. We'll get started in just a minute. 1 minute now, okay?
Steve, you look good.
All right, let's begin our questions with members of the panel. Does anyone have a
I'm not very
question
hopeful
on the
about
panel?
experimental clarification either, but we'll see.
Do you want me to go ahead? All right. So first I want to make a comment about the dark energy, and you can tell them about how wrong it is. But we were there in a small meeting when Mike Turner, we were discussing what should we call it. And the answer that we said, you can't call it the cosmological constant because all the grad students will assume we have the correct answer. Right? So we have to give it a new mysterious name so people will actually investigate and understand. And so we tried several different names. I can't remember all of them. But in the end, Mike Turner says we have to call it dark energy because it's clearly an energy. And besides, we want the Department of Energy to pay for part of it. As well as NASA and NSF. And if it says energy in the name, they will certainly take care of it. And so he's a far-thinking guy, and that's why he's now becoming the president of the APS. He's been very active in not only the theory, but in also making the field progress and being head of many committees. And it's certainly on one of those commissions, he said the study of the acceleration of the universe, which is we label the dark energy problem, is a really key and critical problem. So you talked about where we are now, but you didn't talk about what we might be doing next. Do you have, I have my own ideas on this, but.
So, right, what to do next? Well, it's a combination of many different measurements that allow us to set constraints on the dark energy or whatever it is that's causing this acceleration. From the supernova perspective, if you measure the expansion history of the universe in greater and greater detail, then you can rule out some ideas for what dark energy is because they will not agree, the predictions for how quantitatively the universe expanded with time will not agree with the observations. So that's one way of doing it, and that's the technique that I and my colleagues are pursuing. We're trying to measure through supernovae the expansion history in more detail. Of course, we have to combine that with measurements of the microwave background, and the Planck measurements, about which I think you'll be talking tomorrow, are certainly very interesting. I'm not sure what's beyond Planck in terms of microwave background, but we need to make those measurements more carefully. We need to do other things like, as you know, measuring the so-called integrated Sachs-Wolf effect. That's an effect where you can see microwave background photons going through superclusters of galaxies. And if there were no dark energy, then it turns out that the photons would gain energy on their way in because they're falling into a gravitational field, and then they would lose exactly the same amount of energy coming out. So you get a net gravitational shift of 0. But because the supercluster expands due to dark energy during the time of flight of the photons across it, the blue shift coming in is a little bit greater than the red shift going out because the cluster has expanded more, on the way out. And so there's a net blue shift. The radiation looks a little bit hotter, So measuring that is another constraint. Measuring X-ray clusters of galaxies provides additional constraints. So it's many, many different constraints that give you this concordance cosmology, as we now call it, to ever greater precision. And one of the interesting things to me is that there are certain tensions that are appearing. The Planck data give a Hubble constant, this expansion rate of the universe right now, which is significantly lower than what we have measured using, Cepheid variables in relatively nearby galaxies. And so not everything is rosy, and this is actually good. It's a little bit like Tara said, that if you find things that are unexpected, that might lead to a whole new discovery. So we'll see as the data get better and better. But the dark energy, the JDEM mission and, all these things, I guess now it's called WFIRST, if it ever gets built, given the state of the economy, will help. And there's a European mission called Euclid that'll help. Measuring gravitational lensing of galaxies is another way of getting additional constraints. So there are many different types of observations that we hope will let us home in on whether this really is the cosmological constant or something else.
Yeah, I think that when it's really exciting when there are little discordant results, but again, I want to go back to my result that some of the results are wrong. The Hubble constant itself, as you know, if you look at history, was measured to be 100 with 10% accuracy and 50 with 10% accuracy, and instead of be 75.
We think we're better than
and
that.
Then we say, no, exactly. But so one has to be careful about this. But what is a little what may happen, and while I don't like to predict anything that's less than 1 trillion years from now, it could be a little like particle physics, as Frank and Tar were saying. I mean, the standard model works just too well, and that's been a big frustration in particle physics for many, many years. And this picture of a cosmological constant, unfortunately, everything seems to be coming down to it. But unfortunately, that's the one value where you really can't say what it is. And it could be that it's quite possible that while we've had this incredible period of discovery, that we have this model that we can't understand that explains all the data, and it may continue. My bet is that we'll see that everything is going to be consistent with this model that isn't explainable for the foreseeable future.
Yeah, it could become so difficult and so expensive to show a difference from the prediction of the cosmological constant that effectively we can't reach that kind of precision.
It would have been easier if it hadn't been, because then it would be easier. But it looks
that's right.
It looks like one and walks like one, and make back like one.
Right.
Yeah.
So I actually think that this is another reason for the multiverse idea. The vacuum energy can be pretty much anything.
Well, we'll talk about that.
And we don't live in a universe with a high vacuum energy because stars and galaxies wouldn't have formed. But we don't live in a universe with zero vacuum energy because out of the continuum of numbers, 0 is a very unlikely number, as is any other single number. But, you know, the point is we live in a low vacuum energy universe, and that was conducive for the development of complexity. So I'm okay with that, but I can't prove it, and it leaves me in a dissatisfied state.
It should.
Yep, it does. Good. We're in agreement, Lawrence.
Professor Shears has a question.
So Alexei, you also mentioned that it might be possible that Einstein's theory of general relativity might fail at these really large distance scales that we haven't been able to test.
Yeah.
But you said that people didn't really like that.
Yeah, the failure of general relativity is a possibility, but general relativity is such a beautiful theory. It's based on the most simple assumption. I mean, beyond special relativity, which just assumes that you can't tell if you're moving at a uniform speed, and the speed of light is independent of your motion or the motion of the emitter, and that's an experimentally testable fact. Those two things lead to special relativity, and then the principle of equivalence, the idea that you can't tell whether you're in an elevator accelerating upward or in a gravitational field pointing downward. And any of you who have been in an elevator, you know, you kind of feel heavier when it first starts accelerating. How do you know the Earth's mass didn't become bigger for a bit? You know, well, that's the principle of equivalence. And that is such a obvious and measured thing, you know, from which all of general relativity falls, right? And then the mathematical framework that comes out of that is so pretty that many of us just are reluctant to abandon general relativity. But it's definitely a possibility that it may be wrong. It's just that I think most theorists, if you look at the numbers of papers that are written, there are many, many more papers exploring the possibility of dark energy versus those exploring the possible failure of general relativity.
General relativity is very difficult to modify in a consistent way. Most attempts fail with very gross confrontation with experiment. So I think many people, many theorists have tried to modify general relativity, but most of those attempts never leave the desk drawers in the end. They don't go public because they're obvious failures.
There's another reason. Indeed, in fact, most of those modifications are far uglier than the possibility of dark energy, I think, for most theorists. There's two other things. We think that really at small scales, at very small scales, that general relativity probably will change when we have to introduce quantum mechanics.
Right.
But so it's not just that it's hard to change theoretically. The question is, why does it suddenly change on a scale of galaxies?
Yeah.
And that sort of seems kind of arbitrary.
Right.
If you put fundamental physics constants together, it's not a natural scale to change. Now, some people have argued that, well, there is one other scale, which is the size of the universe, and maybe there may be some, it could be evidence of something outside of our universe, and you can make those hand-waving arguments.
Right.
But from a fundamental physics perspective, it's not you wouldn't, if you locked a physicist in a room and asked her, what scale would general relativity change on? She wouldn't say the scale that we measure it to be. So I think that's another factor.
Nevertheless, just as a final point on this issue before moving on, I must confess that occasionally at 3 in the morning I wake up screaming. My wife can attest to this. Because I'm concerned that dark energy and dark matter may be our modern day equivalents of Ptolemaic epicycles. Remember, Ptolemy had the idea based on Aristotelian physics that essentially everything circles the Earth, but to get the predicted positions of planets to match the observed positions of planets, you had to have these extra little epicycles, these little orbits. And if he added epicycles on top of epicycles, he could have achieved arbitrarily good agreement with the data. Because in fact, any periodic function can be decomposed into a sum of sines and cosines of different amplitude and phase. This is, for those studying mathematics, you may recognize this as being Fourier analysis, okay? So in a sense, he was inventing Fourier analysis, so it was mathematically brilliant and arbitrarily good agreement with observations, yet we now know fundamentally wrong. So I do worry sometimes.
I would also like to add a bit of historical perspective. In the past, there have been theories that look extremely well established. far better established than our current cosmological standard model. Like Newtonian gravity. Newtonian gravity went from triumph to triumph, among other things, solving an earlier dark matter problem when the gravity acting on the planet Uranus seemed to be wrong.
Yeah.
And people used that to predict the new planet, Neptune, which was subsequently found. Similarly, the wave theory of light in the 19th century was a great triumph and had mountains of experimental evidence and even a profound theory with Maxwell's equations and electromagnetism. Nevertheless, it was drastically modified in the 20th century. Both of those things were drastically modified in the 20th century. Newton's gravity eventually gave way to Einstein's, and the wave theory of light had to be generalized to incorporate quantum mechanics. So we may be in a situation like that. But what I think is true is that a modification of gravity will have to be profound. Little tricks and ugly fixes are not worthy and are unlikely to agree with the vast body of data that is accumulated.
I want to add one thing to Frank, just because I worry, because I get lots of letters, you probably do too, from people who say, you know, everyone thought Einstein was crazy. People think I'm crazy, therefore I'm Einstein.
Great logic.
But the idea is that some people think that, okay, all these fundamental theories have been overthrown and I can show everything's wrong. And the really important thing for people to realize is that Newton's law of gravity isn't wrong. It's right. It works very, very well, and NASA uses it a lot. And intercontinental ballistic missiles depend on it, and all sorts of stuff that affect our lives. And similarly, the wave theory of light isn't wrong. We modify our understanding at some level, but those explanations which have satisfied the test of experiment still are valid, and that's a really important part of the continuity of science.
Yeah, I also would like to say that when we can, we try to tweak things and add things rather than considering radically different changes in successful theories. So certainly in the case of dark matter as opposed to dark energy, it's very plausible that it's just a new kind of particle of some kind, either an axion or a WIMP or some other kind of new particle. And although there have been attempts to mimic the effects of dark matter by changing gravity, I think those are widely regarded as silly at this point. If there's a more conservative fix, that should certainly be explored fully.
I think Professor Ting has a question.
Yeah, I just wondering, would you like to make a comment? Why it happened 5 billion years ago?
Yeah, why did it happen 5 billion years ago that this rough equality between gravity and anti-gravity, if you will, occurred? Yeah. So that's one of the big cosmic questions. It's part of the reason many theorists don't like the cosmological constant. First, the fact that it's a very small value but not quite zero. That's very weird. And then the fact that there's this rough equality, 0.7 versus 0.3. That's roughly 50-50. It could have been 100 to 1. It could have been a quadrillion to 1. It could have been a Google to 1. You know, why is it 50-50? And I don't know. You know, it's the why here, why now problem that Michael Turner talks about.
Yeah, I'll talk about
the Tanya Harding problem. Yeah. Some of you are old enough to remember that, you know, right? You know.
We'll probably hear about that from Professor Krauss tomorrow.
Yeah, but we don't really know. But we do know it couldn't have been a very large cosmological constant if that's what it is, because then stars and galaxies would not have formed. And it's a pretty small value. It could have been smaller, but 0 is simply unlikely, you know, out of the continuum of numbers. So an anthropic type argument, which Steven Weinberg actually did make in the late 1980s. He made this argument that, you know, clearly the cosmological constant isn't more than 100 in some units, the units I've been using, because otherwise we wouldn't be here. And he was right, you know. Yeah.
Good.
But 0 is a much more beautiful number.
0 is more beautiful, except that no theorists have come up with the exact cancellation.
But everyone
thought, you know, right?
Yeah, but everyone thought it was, and we should point out that a universe in which it was 0 would be nicer than the universe we live in. I had this debate with several fundamentalists, and maybe I'll get into that.
Professor Coyne has a question.
Yeah, why do all type 1a supernova more or less have the same energy output?
Yeah, the type 1As are all more or less the same.
Especially
because...
considering it's very cataclysmic exchange.
Yeah, it's cataclysmic, but it occurs at or near the same mass, the Chandrasekhar limit, each time. Yeah. It becomes unstable at that point. You get a runaway set of nuclear reactions. Now, to be fair, we're finding all kinds of weirdo supernovae recently that don't seem to fit in that paradigm. So there may be ways in which the surface layers of a white dwarf can explode more than they do in what is called a nova explosion. This would be a supernova as opposed to a supernova, right. Or a nova, right? Anyway, in between a nova and a supernova. We're getting into the fine details here. But it appears that many, if not most, of the white dwarfs that do explode with a high luminosity do so at or near the Chandra limit.
Good, thank you.
Your time? No time.
Okay, folks, I think we'll have to cut it off at this point. I know there are a lot of questions. We took a lot of questions from the audience, and I know your folks are going to be disappointed that we're not going to be able to get to those. I'm going to offer that we will make copies of the questions and try to answer them on the internet. So watch the Nobel Conference website in the near future for answers to some of those questions. And at this point, I think we should adjourn and reconvene at 6:30 for Professor Ting's talk. Thank you.
there's a variant of dark energy called phantom energy, where the amount per unit volume increases with time. In that case, you don't get the big chill, which is what we're going to get with distance runaway waves, but rather the big rip. As clusters of galaxies eventually get torn apart, as the dark energy gets strong enough, then galaxies get torn apart, and planetary systems, and planets and stars and people, and the very atoms of which you are made will get ripped apart. But that's an unlikely form of dark energy. Yes, hi. Hi. Yeah. Yeah, sure. Yeah, email me. I did. Okay, great. Sure, okay. Yeah, sounds good. Good. Yeah, what happens is the universe, and only later, I don't think it's 2 or 3 stars and galaxies. From that point on, they're expanding more or less slowly in the decelerating way, and then more recently. So the initial expansion was superluminal, and that does not violate special relativity, because again, you have enough little bits of space for each of them doubles in size, and the distance between the 2 points can grow arbitrarily. What relativity forbids is for any particles to travel through space faster than the speed of light. It does not forbid space, but yes, inflation made essentially arbitrarily large. Okay, so you were exactly on the right track.
That's right, I forgot about it.
Yeah.
I should have warned him that the joke here was... Right, yeah, exactly. Yeah, they were introducing
What often happens is that if someone goes and gets a high pacing job, they just never come back, because it's a long...
I've never asked Heather if she tells her students that she's an old student.
No, as long as you come back and what you need to actually do is indicate that you've kept up with, that you've retained your knowledge by continuing to read books and solving problems and stuff. Because if you've been away from your undergrad education for too many years, there might be the concern that you have to take a bunch of courses over again, because we just forget stuff, all of us do. So you want to say that, well, you kept on, in fact, you might continue reading even some of the more advanced texts and stuff, and solve some problems and things like that. Chuck, I'm just answering some questions here. Where should I go? Yeah. Is that far? Yeah. Back where we were. Okay.
We're over here.
So I can continue answering some questions. Okay. Right. Okay. Yeah. Okay. No. And the concert thing starts at, but Tim's talk is at 6:30. So maybe okay. Yeah. Why don't you check? Okay. Because I'm happy to continue answering questions. Oh yeah. Yeah. Oh, that's right. Yes. Right. Yeah. Oh, cool. Where is that? Okay. I'll take a look at that. Will it also be open to all? Yeah. Okay. Yeah. Thank you. Is this on here? Okay. Thank you. Oh, cool.
I'm actually
Thank you. And good luck to you. Yeah.
And when I start grading exams, I can't stop. That's all I don't care. I don't know how many 2 o'clock emails I've sent to class. So grades are posted.
Right. So the dark energy could be some sort of a new energy field that has an associated particle. But so in that sense, it takes
Had a
light.
couple more conceptual ones.
But it's probably not the Higgs that they found that seems to explain or be a fundamental missing link in the standard model. Right. So it's probably not the thing that they found. But in the context of these field theories that have an energy and associated with it is a particle, it's easier to detect clumps of field. This quintessence stuff would be, I mean, it sounds similar. Yeah.
I want to go tour JPL someday. That was cool.
In my presentation, I just showed this.
Okay, very good.
So I began by showing, where is it? I begin with this one.
Okay, yep. And what we can do.
This is what it would like if the rocket accidentally flew into the station area.
Yeah, okay.
Okay, and then here, just so you can get in a sense, if you want to just try speaking, just so you can
So then can you hear me? If you go back, can you hear me?
Good, Brad?
Can you hear me? Very good.
A rotating disk with like a hole in it, and light would pass through the hole. So it would go along and pass through the hole of this disk and then it would be detected. And by increasing the, and most of the time the light would hit the disk and not go through the hole. But if you increase the spin rate of the disk, then you could get the light to go through the hole at a certain rate of spin. And if you know the distance between, no, they just kind of knowing the distance between the place where the light was emitted and the place where it was passed through this other little hole, and knowing the rate of spin of this other disk, you could figure out how long, no, just time of flight. You know how long it's been since the hole went around, and the pulse of light has gone through it again successfully, and you know the distance. And so it was based on that. Now we can bounce light off of distant things. Actually, that's how we actually go the other way around. That's how we measure distances. In fact, the speed of light is now a defined quantity. It's never ever going to change again because it was known so well that physicists basically said, let it be an exact quantity.
Chris and I, when we visited the
determined,
Tower Sudan mine,
I guess, is it the second?
and you know where they've got the neutrino and stuff there, but the day we were there, it was
the second, right? Because the meter is some number.
I forget what happened.
Wavelength, whatever, right? But so the
yeah,
speed
they
of
had
light
some
is now a
flooding or something,
defined
and we
quantity, you know.
we decided to visit
but
it
it
there,
was measured
like
in many,
while they
many
were still
ways.
cleaning it out, so we couldn't.
A guy in the 17th century called Romer measured the speed of light pretty well by monitoring the moons of Jupiter going around Jupiter, and you know, occasionally they go behind Jupiter. And he noticed that when Jupiter was going away from us,
Get in an elevator and go down and down, and then you.
the
At some point, you
periodicity
kind of
of the
think,
eclipses
why am I doing
this? And that's because when it's coming toward us, in between two eclipses, Jupiter has moved some distance toward us. So the remaining distance for the light to travel is less than before. No, that's not a redshift. It was just a time of flight thing. And he got the right answer to like 20% or something. And this was in the 17th century. So there are many, many methods, you know. But you can look up like the Wikipedia article on measurement of the speed of light. It'll have lots of sure. Okay. Yeah, sure. What's that? Yeah, that's right. Oh, autographs.
I wish more people were interested.
Really? Oh, you've been coming for 40 years?
Yeah.
Wow, fantastic. Yeah, so you're a local or nearly local. Hi. Yeah, that was just a joke, Yeah. Just, they're all going away. Forget about the fact that the more distant ones are going away faster. But you're right, that is an inconsistency if you take my joke a little bit too far. Pardon? Well, we don't know, but we think it might be a particle left over from the Big Bang. No, it doesn't make up us, but it does make up 25% of the universe as a whole. Pardon? 25%.
See how it reacts to transition. Do some spectroscopy on it. Do some calculations. Yeah.
All the material and
see if I can make dark matter not darking.
25%.
Illuminate. Yes, I would have tried to illuminate.
And that's another 7%. So only 5% is the normal stuff.
There you go.
Okay.
Pump some
Cool.
dark energy into the dialyzer.
No question. Okay.
Increase the power.
Oh, cool. What is your name? Oh, Meg. Okay, good. Sure. Would you like me to do it, sign it, I don't know if there's any particular place.
No, it's just listening.
Oh, cool. The 96 lecture series? Wow. So you're really hardcore. Very good, Meg. Sure thing, yeah. I'll hop. Right? Okay.
You lost.
Oh, yeah. Thank you. All right. Yeah. Okay. Yeah. Good. All right. Very good. Thank you. Yes.
Hi.
All right. Oh, hi.
Aaron Anderson, Stanford graduate.
So
thank you for the Cal Stanford
no offense.
dig.
That's the way it is.
He's a chemical engineering transplant to our chemistry department. So
Right. Yeah.
he's got some redeeming qualities.
Yeah. No. When teaching my class, if I were to not, dig Stanford like that, then I would be lynched by my own students and stuff. So and it's just so perfect because, as you know, the rivalry is so great and mutual respect. Obviously, both great institutions, but during big game week, if you peep a word of support for Stanford, at the Cal campus, you get lynched, and vice versa, right? So
who's going to win big game
Oh,
this year?
Stanford, hands down. I mean, we've got a really crappy team with a new coach, but maybe he'll turn things around. But we're going from rock bottom, and it's going to take him a while. We've got this amazing offense. This quarterback leads the nation, but we have a sieve-like defense. We've been allowing 500 yards a game. Yeah. I mean, now, admittedly, we played Oregon last Saturday and Ohio State the Saturday before, and they're both really, really good. But, they shellacked us. The various polls are predicting we will come in second or third last in the 12, whereas the polls are also predicting Stanford will probably be number 3 plus or minus 2. It's just that Oregon is really good. And UCLA appears to be pretty good this year, too. So, yeah. So when were you at Stanford?
Well, I was there for graduate school.
Oh, cool. Yeah. In chemistry, you said. Yeah.
Chemical engineering.
Chemical engineering, yeah. Mm-hmm.
So I was there from 5 to 9.
Yeah. Cool.
It's a great place to live.
Yeah.
I'm a Minnesota native.
Yeah.
Really enjoyed living in the Bay Area.
Yeah. Well, it's a great place. And, we get many undergrads who come to grad school from there, and we send many of our undergrads to Stanford. So, I have some close collaborators there. But nevertheless, got to put in that dig, so.
And I'm looking forward to your watching your DVDs. Although I'm getting them from the library. I'm not buying them, so I apologize about not filling the coffers. But
Right. Yeah.
But I've really been enjoying these great courses.
Oh, good. Yeah. I get lots of them in other fields, and mostly listen to them since I don't have much time to watch TV. So like the music ones and philosophy and other things where you don't need to see images. Mine aren't sold audio only because it's such a visually rich course, right? Yeah.
The one I'm listening to right now, which if you like language, is amazing. It's about the history of the English language.
Oh, cool.
And it's just fantastic.
Yeah.
It's done by a guy from Stanford, actually.
Oh, okay. Right.
Seth Lehrer, I think is his name. But
And then if
it's
you like
fantastic.
music, Greenberg's courses, I mean, he's done like 29 courses with them. He, in fact, quit his job at the San Francisco Conservatory of Music to just produce courses for those guys because he gets so many royalties and stuff. Because there, they sell audio versions, and that more than doubles their sales. Because people like me who are too busy to watch it on TV, will listen, while driving to work or whatever.
Well, I live up in the Twin Cities.
Well,
so
there
I
you go.
drive
Oh my
an
goodness,
hour
that's
here and there,
So it's way the hell better than listening to drivel on the radio, So yeah. Well, cool. And your name again?
Aaron Anderson.
Oh, Aaron
So I'm in
Anderson.
the chemistry department. with Steve,
Cool.
And,
Yeah.
Been here for a couple of years.
Yeah.
Second career, actually.
Yeah?
I was in the medical technology industry
Oh, okay.
for a number of years, and then came back to
academia. Yeah. Interesting. Right. Good.
Nice
All
to meet
right.
you.
Well,
Enjoyed
let's
your talk.
let's
Fantastic.
yeah. Head up. Let me just grab my stuff.
Sure.
I don't want to get on the plane. Thank you for the cough medicine. I survived. Yeah, no, I'm sure it helped, Now I have something.
you want more ice?
Welcome back, folks. We're just about to get started in like 15, 20 seconds here, so please find your seats and settle in for another wonderful talk. So you ready? I'll wait for this one big group to settle in. It's my pleasure at this time to introduce my colleague in physics, Professor Tom Huber, to introduce Professor Ting.
Thank you. Discovering the fundamental nature of the universe requires scientists with vision, ingenuity, and persistence. Dr. Samuel Ting exemplifies these important
traits. Dr. Ting has been at MIT since 1969 and is the Thomas D. Cabot Professor of Physics at MIT. He was born in Ann Arbor, Michigan. As he states in his Nobel biography, my parents had hoped I would be born in China, but as I was born prematurely while they were visiting the United States, by accident of birth, I became a U.S. citizen. After growing up in China, his family moved to Taiwan when he was just 12 years old. Then, at age 20, he returned to Ann Arbor. It took him just 3 years to receive his bachelor's degree in math and physics, and only another 3 years to get his PhD. As a lifelong Michigan football fan, I'm certain that he has some very strong opinions about the Gopher Wolverines game this weekend. In the early 1970s, Dr. Ting had the vision to propose constructing a high-resolution electron-positron spectrometer at Brookhaven National Lab. He has some interesting observations in his Nobel acceptance speech. During the construction of our spectrometers, and indeed during the entire experiment, I encountered much criticism. The problem was that in order to gain good mass resolution, it was necessary to build a spectrometer that was very expensive. One eminent physicist made the remark that this type of spectrometer is only good for looking for narrow resonances, and there are no narrow resonances. Nevertheless, since I usually do not have much confidence in theoretical arguments, we decided to proceed with our original design. In 1974, contrary to expectations, Dr. Ting did indeed find a narrow resonance. This corresponded to a new particle they called J, which was the first direct experimental evidence for the charm quark. In nearly record time, in less than 2 years, he was the co-recipient of the 1976 Nobel Prize in Physics. The Nobel Prize Committee said in the press release, the difficulty was sorting out a very small number of daughter pairs from a horde of millions of other particles streaming forth. It was like hearing a cricket close to a jumbo jet taking off. In 1995, Dr. Ting proposed a far bolder experiment to construct a particle detector to be attached to the International Space Station. Under Dr. Ting's leadership, it took over a decade and the work of 500 physicists from 16 countries to design and construct the alpha magnetic spectrometer. Unbelievably, after the $1.5 billion detector was already constructed, it nearly didn't get off the ground. When NASA decided to retire the space shuttle fleet in 2010, all remaining flights were devoted to completion of the space station. This would have left the AMS sitting worthlessly on the ground. It took Dr. Ting's persistence and lobbying of President George W. Bush, NASA, and the Congress to pass a bill authorizing one final flight of Space Shuttle Endeavour to transport AMS to the space station. Since its launch in 2010, the AMS has recorded over 400,000 positrons. In March 2013, Dr. Ting presented the results of this study, which may provide evidence about the nature of dark matter. CERN theorist John Ellis puts it this way: by being that much more clever and that much more careful than everybody else, Sam's able to get things out that other people missed. It's with great pleasure that I introduce Dr. Samuel Ting, who will talk to us today about the alpha magnetic spectrometer on the International Space Station.
Thank you very much. I only have one small comment. The Congress of the United States do not talk to physicists. And certainly also the White House. And I remember my wife and I went to a White House reception for Nobel laureates. Professor Fitch was in front of us, and shook the president's hand and said, I'm Fitch from Princeton, I'm a physicist. President Bush said, I'm in politics. I think it's really by a stroke of luck we managed to put AMS on the International Space Station. The International Space Station has a size of 110 meters by 80 meters, namely exactly the size of a football field. The construction cost is about $100 billion. I think that's the main reason the Congress decided, gee, probably it's a good idea to use it for science. So on May 16th, 2011, AMS was sent to space. This is what it's like today. In 2 years, we have collected 40 billion cosmic rays. This is much more than all the cosmic rays collected in the last 100 years. Let me share with you the physics of charged cosmic rays. Cosmic ray was discovered in 1912 by Victor Hess. 1932, positron, the antimatter of the electron, was discovered by Carl Anderson. 1947, Cecil Powell discovered the pi meson. All three received the Nobel Prize. From 1936 to 53, an enormous amount of particles were discovered. After 53, accelerators being built, so people gradually switched to accelerators. But as accelerators become increasingly more costly, to do experiment in space is an alternative. And this is the first precision general purpose magnetic spectrometer in space. There are two kinds of cosmic rays traveling through space. Neutral cosmic rays, light rays or neutrinos, have been measured by Hubble, by Kolbe, by Planck, by WMAP. Many fundamental discoveries has been made, and you have heard elegantly described before. But then there's also charged cosmic rays. Because it has charge, it must have a mass. Because it has a mass, it's absorbed in Earth's atmosphere. So to measure charged cosmic rays, you have to go to space. Because it carries a charge, you must use a magnet. Because only in a magnet, positive bend one way and negative bend the opposite way. But put a magnet in space is somewhat difficult. You remember a magnetic compass, one end will go into north, another end will go to south. So if you're not careful, if you put a magnet in space, so the space station or space shuttle will lose control. And this is one of the reasons it took a long time to put a magnetic spectrometer in space. So using a magnetic spectrometer on the International Space Station, ISS, is a unique way to provide precision long-term measurement of original high-energy charged cosmic rays. Some of the physics goals include search for the origin of dark matter. We heard around 90% of the matter in the universe is not observable, It is called dark matter. A galaxy seen by telescope is what you see on the left. And theoretically, if you could see the dark matter in the galaxy will look on the right. Another example is the search for the existence of antimatter in the universe. The Big Bang origin of the universe required matter and antimatter to be equally abundant at the very hot beginning. We heard an elegant talk this afternoon about LHC, which tried to understand the condition at the beginning of the universe. What we want to do is to look the other side, see whether there's a universe made out of antimatter. Let me just mention, search for antimatter started from already in 1972, an experiment by George Smoot and Louis Alvarez and others. And they were the first one to put a magnetic spectrometer in a balloon. So this is the thing we sent to space. It's 15 feet by 12 feet by 9 feet, weighs 7.5 tons. It has 300,000 channels of electronics and 650 microprocessors. It is a trillion electron volt. TeV means trillion electron volt. Precision multi-purpose spectrometer. Particles and nuclei are defined by their charge, which we call Z, and energy, which we call E. On the top is a transition radiation detector, which identifies electron positrons. And then, doesn't move. Silicon tracker, there are 9 of them, which measure Z and E, or P. Then electromagnetic calorimeter measure energy of electron positron, and something called time-of-flight measure Z and E. The magnet measure the sign of charge. And ring image Cherenkov counter measures Z and E. It's a precision detector you use in accelerators, but you send to space. Z and E are measured independently by tracker, by reach, by time of flight, by echo. You need to remember once in space, if something doesn't work, you cannot send a graduate student to fix it. So it is a large international collaboration, but by certain standard, it's a small one, only involving 15 countries, 44 institutes, about 600 physicists. Most of the detectors, in fact, all the detectors, were made in Europe and in Asia. Detector and electronics. I have never done experiment in space before, and so as I proposed this experiment, I received this cartoon. And this cartoon was very useful because it made me realize how difficult it is to do experiment in space. So on top of the detector, it's called transition radiation detector. It identifies positrons and electrons. It's mostly done in Germany, and this is a group of physicists. Took them 10 years effort to do this. In this detector, there are 9,000 long and thin tubes. Out of 9,000, we choose 5,000 and center to 100 microns, namely 1/10 of your hair. And once you see it, you don't know what to do, so you send to a CAT scan machine in the hospital at night, make sure they're centered. Another detector called time-of-flight detector, made in Italy and United States. Electronics is designed by United States, and measure nuclear charge and the velocity. Then we have silicon tracker. There are 9 planes, 200,000 channels, measure the position to 1/100th of your hair. These are mostly done in Italy and Switzerland. You notice the Italians are ever colorful, dressed like their national flag. In space, the space station rotates around the Earth every 90 minutes. The temperature changes greatly, from minus 20 degrees centigrade to plus 40 degrees centigrade. But in order for the detector to be precise, you have to maintain to 1 degree. How do you do that? So we developed a system where the accumulator stores liquid CO2, use the pump, go to the heat exchanger, and go to your electronics. Absorb the heat from the electronics and come out in red color, and that means it's a gas CO2. Go through the condenser and go back. It's easily said and never been done in space. In fact, most of the detector we've been doing, and most of the people think cannot really be done in space. Another detector is called ring image Cherenkov counter, abbreviated as RICH. It measures nuclear charge and its velocity, has enormous amount of photosensors. And these are done by the French and the Spanish. Then finally, we have something to stop all the electron positron, and that is called a colorimeter. It's a precision measurement of direction and energy of passing light rays and energy. There are 50,000 fibers, 1 millimeter in diameter, uniformly distributed inside 1,200 pounds of lead. So there are total 300,000 channels producing 7 gigabit per second information. That's much too large than what the space station can download. So the 7 gigabit per second data is processed by 650 computers to reduce to 10 megabit per second. The first detector has 30 computers, process 5,000 signals. The second device, silicon tracker, has 212 computers processing 200,000 signals, and so on and so forth. Once everything is done, we send to the ESA, means European Space Agency, to simulate the condition in space. So on the right is AMS in the thermal vacuum chamber, where the pressure is like the pressure on the moon, and the temperature goes from minus 90 degrees centigrade to plus 40 degrees centigrade. On the left is the picture of AMS, and to look for the interference, make sure the signal can come down without interference. Before and after you do the space test, we send the detector to the accelerator and to measure all its properties. Make sure before the test and after the test, the thermal vacuum test, the detector have not changed. The detector finally was too big for a 747, and so the US Air Force was kind enough to provide a C5 and came from Dover, went to Geneva, and to pick us up. And in Geneva, there was a big sensation because nobody had seen such a large airplane before. And they made a headline of Geneva newspaper. So we were sent to Kennedy Space Center. At Kennedy Space Center, the first thing we did is to match AMS with the payload attached system simulator. namely a mock-up of a space station, to make sure everything will fit. It's better you check this before you are in space. And just before the flight, the astronauts invited me to have a dinner with them. And I must say I was quite nervous, but they were very calm. And then I thought I should support them. And this is my main support of NASA just before the flight. Just before the flight, I asked to be left alone for a while on the launch pad. Try to think through all the decisions, all the discussions I'm involved in the last 16 years. Try to question myself, is there anything wrong? Are there anything I'm suspicious? Because if there are, no matter what, you cannot let it go once it's gone, and then you have lost everything. I remember spent about 4 hours there by myself, and after that, I just feel my whole body was really icy, because I was really scared about what will happen. And after that, they close the shuttle bay, the astronauts go to the launch pad, and I was sitting between two government officers, listening to the countdown. Of course, I did not understand a word what they're saying, because they speak very quickly. And so this is the night before the launch. And so this is the launch of Endeavour before the passing through the cloud, and just pass through the cloud. And then after 123 seconds, 1,000 tons of fuel is spent, and then you are near space. 2 days later, you gradually approach the space station, and then the next day, the pilot gradually maneuvers the space shuttle toward the space station. And then AMS is grabbed by this shuttle arm on May 19th. By then, of course, there's no more weight, and you can use your finger to push it. And so at 5:15 a.m., we installed on the space station. Took us 4 hours to check everything, and we start taking data 4 hours later. So the space station fly around the world every 90 minutes. And there are 3 satellites. You can see T171W, T1275W, and so forth. These satellites receive information from the space station and transmit to the ground. And all information then goes to Marshall Space Center and then go to the control room at CERN. So the information goes to a Tetra satellite, goes to White Sands, and go to Marshall Space Center, and then go to our control room. In the last 2 months before flight, I suddenly realized, gee, what happens if the satellite doesn't work anymore? And so I talked to NASA about putting a computer in the crew quarters and train the astronauts to use the computer. And they were kind enough to agree to that. What I did not realize, of course, a computer like this costs $2,000 or $3,000. Once you want to put in space, you need to add 3 more zeros behind your cost. So on the space station, the thermal environment is constantly changing due to the position of the sun. When the sun is on the right side is hot. The other 2 sides are cold. When sun is on top, the top is hot, the 2 sides, all the other sides are cold. Remember now you are in vacuum. Also, the radiator reflects the light, and also the solar panel reflects the light. All of this, you have no control. So we have no control of space station orbit, movement of solar panel and radiators. But all the detector, in order to maintain its precision, must be kept in its temperature limit. And so we have 1,000 temperature sensors and 300 heaters on board. For the detector called TRD, there are 24 heaters, 482 temperature sensors, and so on and so forth. Well, this is our control room located in Geneva, Switzerland. Another thing I forgot is in accelerator, you have Christmas, you have New Year, and you have weekends, and you have machine shutdown. But in space, the space station goes around all the time. And so there's no such a thing as Christmas and New Year and the weekend. Unfortunate oversight by me. So let me share with you some of the results we have seen in the first 2 years. Because this is a unique detector, and because I think in the next 20 to 30 years, nobody will be foolish enough to send another detector in space, given the difficulties I encountered. So we decided to analyze the data very carefully. So we organized the team into 2 groups, analyze the same subject. And they meet with me every Friday at 11 o'clock. And so most of the work are done in Germany, in Switzerland, in France, in Spain, in Italy, and in Taiwan. So as I mentioned, one of the physics objectives is to search for the origin of dark matter. I already mentioned most of the matter in the universe you cannot see, that's why it's called dark matter. Collisions of cosmic rays produce positons. Collision of dark matter will produce additional positons. This characteristic of additional positons can be measured very accurately by MS. This is an idea first pointed out quite some time ago by Mike Turner and Frank Wilczek. After we published our first result, Mike Turner wrote me a letter, remind me of this work. Of course, I know this work quite well, but he also mentioned, since he's the president of American Physical Society, he found out I have not paid my dues. So according to the theory of Turner and Wilczek, the positon fraction, namely the number of positons compared to the total number of electron positons as function of the energy of positron electron, you have a smooth curve from collision of cosmic rays. But then you have a 2 enhancement curve corresponds to possibility of existence of new type of particles. Neutrino would be one, and could be others. And collision of these will produce excessive positons. Because those particles has a finite mass, and therefore when you go up, and then you have a sharp cutoff. So in the first 1.5 years, we collected 25 billion events, 6.8 billion are electrons and positons. This one picture shows an electron at 99 giga-electron volt. Another one shows positron at 100 giga-electron volt. One is the front view, another is the side view. And then in the back are the shower shape. I show this to show how clean, how easy it is to identify this. So this is our first result. The data for measurement shows from 1 to 10 GeV, indeed, the fraction decreases because they come from collision of ordinary cosmic rays. But after 10 GeV, the rate increases up to 250 GeV. That is very strange, because that obviously is not from collision of ordinary cosmic rays. But from 10 to 250 GeV, it gradually decreases the slope by nearly order of magnitude. Namely, it's flattened out. And there's no sharp structure in this spectrum. If you look more carefully in a linear scale, you will see in red is our measurement, in blue and green our early measurement, shows 2 or 3 things. One is the spectrum increases with increased energy and then flattens out. If you were to compare with theoretical models, our measurement look like this. And we now have 2 or 3 more points. And let me just mention, it does not seem to be continually increasing. This was published in a journal called Physical Review Letters. In the first 5 months, there are many, many theoretical models explaining our results. And there are also many newspaper articles. And this is from The Economist, and shows space station and show a detective. Certainly doesn't look like me. And then it was an article in New York Times, in the Wall Street Journal. I found out the people who are dealing with finance actually give a good description of our work. And then so also in German newspaper, and in many newspapers, this one is very interesting. La Repubblica is a very well-known Italian newspaper, has a complete description of our experiment and show a picture. But unfortunately, this picture has nothing to do at all with our experiment. So, sometimes happens in Italy with this. So we have some also interesting new results. We just looked at the electron spectrum. The electron spectrum, the red one is ours. It shows what you will see if you have a very precise detector. show the spectrum, the red point goes up and then decreases, and in great disagreement with the previous measurements. And remember, the electron spectrum decreases with energy, but the positron increases with energy. That is very strange. Why the positron spectrum is so different from electron? After all, they are pairs. And also, why the positron spectrum changes behavior, gradually increases at 35 billion electron volt. So that is the second result. The third result is, of course, if you measure electron positron together, that's our measurement. And this measurement shows the value of doing a careful experiment in space. And this red point is our measurement. Our measurement clearly show you look near 10 to the 3, you see an enhancement from previous measurements, and this has attracted enormous amount of attention, and that's not reproduced by us. Also, even at low energy, our measurement has nothing to do with previous measurement. Then the question is, where the positron come from? Does it have a unique source? And we'll look where the distribution is, and found it is totally isotropic. Come from all the directions, the distribution is uniform. The two black dots is because space station is flying at 52 degrees, so you have a region you cannot see. In 2001, there was a very important article in Science magazine by a detector, mostly by the European Space Agency, called Pamela, and where they measure the proton spectra. You notice the proton spectra that's on the left. Let's see, on the left, you see the spectrum decreases, and then suddenly have a break. And also for helium spectrum, it's smooth, then drops down, then goes up. This has aroused enormous amount of interest, and many people are proposing new experiments to understand the sudden discontinuity. So we measured the proton spectrum, but measured to an accuracy of 1%, not 30%. If you look at ours, that's the blue one, and ours shows no discontinuity. And the data just go down smoothly. Similarly, this is our measurement of helium. And helium also shows it is a smooth curve and has nothing, there's no structure, no discontinuity. I mention this because space is a very hostile, very difficult, and you really have to do things very, very carefully. So in the last 100 years, measurement of charged cosmic rays by balloons and satellites have typically contained 20 to 30% uncertainty. We will provide cosmic ray information with 1% uncertainty. The 30-time improvement in accuracy will provide insight in space science. And because of this, now the space station has become a unique platform for precision physics research. We are now continue to collect data. The data come down 16 billion events per year. We will continue to look for dark matter, see how quickly it drops down, and look for the existence of antimatter and search for new phenomena. Search for the existence of antimatter in the universe. Well, on the space station for 10 to 20 years, we were able to search for the existence of antimatter, depends on how you assume the intergalactic magnetic field. You can reach about 1,000 MeV/s. But that's a model-dependent statement. Let me remind you, antimatter was first proposed by Paul Dirac in his Nobel lecture in 1933. He noticed the equation of motion of relativity and quantum theory, mass, m, appear in square. Therefore, it's equal to m times m and minus m times minus m. So Dirac asked, what is minus m? And leads to the theory of antimatter. So for a real genius, getting a Nobel Prize is quite easy. The first antimatter was discovered by Carl Anderson, who received a Nobel Prize in 1936, show a positively charged electron. In 1965, there was an early experiment done by me and Professor Lederman. The physicists produced antimatter particle in a complex form. Namely, we observed antideutron, which is an antiproton and antineutron formed together. And since then, I've been interested in whether there's a universe made out of antimatter. So cosmic antimatter cannot be detected on Earth because matter and antimatter will annihilate each other in the atmosphere. Matter and antimatter has opposite electric charge, so you need a magnet to measure the charge of antimatter. Now, to measure antimatter, the first thing you need to do to make sure your detector is sensitive to all the elements seen on Earth, namely the periodic table. So this is the mapping of periodic table by us in space, but measured to an accuracy of 1%. The question, therefore, is once you have done this, then you have confidence in your detector, and then you can look for something new. Let me mention the space station cost is about 10 times the Large Hadron Collider. The Large Hadron Collider, as we heard this afternoon, has 4 really beautiful experiments. On the space station, up to now, only has AMS. Finally, let me share with you what we really will see. When I start doing physics, the highest energy accelerator are the proton synchrotron at CERN and Brookhaven National Laboratory. The purpose for this accelerator was to study pion-nucleon interaction, namely try to understand nuclear force. What was discovered at CERN was the existence of neutral current, leading to the major discovery of Z and W bosons, which transmit electroweak force. At Brookhaven, there were 2 kinds of neutrinos, breakdown of fundamental symmetry called CP, the discovery of J particle. All first 4 experiments were awarded the Nobel Prize. Fermi National Laboratory, when it was built, was to study neutrino physics. What was discovered was the 5th and 6th quark. Stanford Linear Accelerator Electron Positron Collider, originally is to study property of electricity. What was discovered was something called partons, the fourth quark, and third type of electron. In Hamburg, Petra, it's a large electron-positron collider. The original purpose is to look for the sixth quark. What was discovered was forces of gluons, predicted by Frank Wilczek. A large underground experiment called Super Kamiokande, the original purpose was to look for lifetime of proton. What was discovered was neutrino have mass. Hubble telescope originally was to look for galactic survey. Among its many discoveries, the existence of dark energy. So when you build something new, you ask experts' opinion, what you're going to get. And when you do a precision experiment, and almost never have anything to do with your original discovery. So exploring a new territory with a precision instrument is the key to discovery. This afternoon, we have heard an elegant presentation about Higgs. Higgs, of course, is a major discovery, but it really is my hope we can find something more than the Higgs. So I have mentioned the experiment will be there for 20 years, and we're going to reach to about 1,000 megaparsec. And somebody sent me this cartoon and said, what we will really see. So cosmos is the ultimate laboratory. Cosmic rays can be observed at energies higher than any accelerator. But the most exciting objective is to probe the unknown, to search for phenomena which exist in nature we have not yet imagined nor had the tool to discover. The German physicist and philosopher Christopher Lichtenberg wrote in his diary 200 years ago, to invent a remedy against toothache which would take it away in a moment might be more valuable than to discover another planet. But I do not know how to start a diary of this year with a more important topic than the news of a new planet. It was the planet Uranus, discovered in 1781, which was recently investigated more closely by Voyager. Even at that time, one was confronted with a problem which is as important today as 200 years ago. Should we build satellites to explore the universe and accelerators to investigate microcosm at a time when burning problems like energy production, diseases, overpopulation, and so forth, trouble our society? In the 21st century, we enjoy unprecedented advancement in technological development, such as in the field of communication, computers, transportation, healthcare, and so forth, which had a dramatic effect on the quality of life. What is often forgotten is the fact that the foundation of this achievement were laid down some time ago by scientists who were driven by intellectual curiosity, not by economic concern. So this is my little pyramid. What is shown in the x-axis are distances. Physics basically study of distances. And then you have frontier science in 1920s, 1930s, and this century. 100 years ago, the frontier science was optics, thermodynamics, and mechanics. Now, of course, it's used in television, in radio, in aircraft. In the 30s, the frontier science is quantum mechanics, solid-state physics. Now it's used for transistors, semiconductors. In the 40s, the frontier science is nuclear. Now it's used in energy. for large distances. In the 30s, we studied sun and cosmic radiation. Now, we use it for navigation and timekeeping. What does this mean? The pyramid has grown with new applications, increasing its height, where fundamental research continually widens its base. The role of basic research implies that it finds itself in the utmost corner of the pyramid, and hence is sometimes blamed for being too far away from daily life. Only after some time, when application grow and public is acquainted with the strange new phenomena, they seem to become real. The prime motivation for basic research is curiosity, the innate passion to learn something new or obtain a deeper understanding of natural phenomena. Basic research, of course, also serves as a catalyst to industries and in development of new technologies. Results of basic scientific research, though difficult to predict in advance, have had a profound effect in the quality of life. Thank you.
Thank you, Professor Ting, for that wonderful talk and for your persistence in this incredible endeavor. I would have said the talk was out of this world, but I thought I might get a little grief for that one. At this time, I'd like to call our panelists up to the front for one more question and answer period tonight. We have a little time constraint, but we're going to have time for some Q&A. There will be a few people walking around with cards for questions, and so hopefully we'll find them and send your questions in, or send them on the internet and we'll get them asked. Thanks.
Let's see.
All right, we'll begin the question session with a question from Professor Gates.
Thank you. And first of all, of course, I'd like to congratulate our presenter for a brilliant presentation explaining the progress of what's going on in terms of doing fundamental physics in space. My questions, in fact, are not so much about the science, but a little bit about sociology in some ways. There were two underlying themes to your presentation which one could detect. One of them was, as we look at the experience around the AMS, we begin to see that there is a wider global participation in doing this kind of fundamental science. You talked about your groups in Europe and in Asia. And so my first question, and it's actually a two-part question. The first question is, do you think that we as a nation have reasons for concern as we see this globalization of science? That's question number one. And then
allow me to answer you.
Absolutely.
Okay. Even though the group is very large, and like in all the groups in physics, it's always few people who come. Even you may have 1,000 people in the group, and sooner or later, very quickly, you will identify few students or few faculty members. And these are the ones who are going to make a difference. And it's very difficult to predict where they come from. And for our experiment, we do have very good people from Russia, from United States, from MIT, and from Germany, from Italy, and from Switzerland. Not many, few people, but they are the ones who really make a difference.
The second question is, you have been a pioneer in terms of the AMS, and the nice history that you gave of particle physics talked about the fact that when we first started thinking about really high energy particle physics, it was actually cosmic rays. That's where we as a species got into the business. And then there was a transition that mostly occurred at Berkeley with Alvarez and the accelerators that started at Berkeley. But now it looks like we might go into a phase where we return to using nature as our accelerators and then building ever more sophisticated detectors that we would put in space. So I'd like to hear your reaction to that thought.
No, I think there are a large branch of physics can only be done by accelerator. There's no question, because you have the intensity and you have the control, and also a key thing. Something goes wrong, you can go to fix it. And in space, you don't have that luxury. We have 400% redundancy, just to make sure. Fortunately, nothing has gone wrong so far, but this does not mean tomorrow or day after something could happen.
Thank you.
In past years, there's been a lot of interest in strangelets, particles that would have very unusual charge to mass ratios compared to the nuclei we know. What sort of constraints can you put on those things? Have you seen anything like that?
Strangelets, as you know, was first also Ed Wheaton worked on this, Jack Sandweiss worked on this. We have not looked at strangelets and antimatter and all these things. What we have decided to do is to do the simplest, the easiest one first, just to make sure we understand the detector. We'll get around to that in a year or so.
I see. Another, maybe well, I don't know, if it's too technical question, we can ignore it, but at very high energies, there was questions about excesses of protons, and then there was the question of whether they might be iron nuclei or something like that. So whether very heavy nuclei might be produced in exotic processes in space. Can AMS shed any light on that at all?
We have measured up to Z equal to 40. I cannot show it on the scale because on a log scale you don't see it. And we should be able to measure to uranium.
I was really interested by your positron ratio as a function of energy because it's looking really intriguing. So I wondered, I know that AMS is only 10% throughout its sort of ultimate data set, but what's the reach that you can go to in terms of energy? How far out?
I would think 1 TeV. We are now at 300 GeV, factor 3. We have now about 10 positrons above 1 TeV. But I think it's important we don't publish things with large errors. So we want to wait till the error becomes small to see whether Frank is right or not.
Well, my prediction is hypothetical. It's okay. Anyway.
Other questions from the panel?
Yeah, it would certainly be interesting. Well, it would be, of course, one of the great discoveries if it turns out that this is the way that dark matter is found or identified as a particle.
But it is really very strange why positron spectrum goes up, flattens out, goes up again. It's the flattening out part that's different. And the question, a very important question is, could it be due to pulsars? Okay? Many people look into that. And we also measure antiproton to proton ratio to see how it behaves. Antiprotons are more difficult to be produced by pulsars because the mass is so heavy. So we now do a very precise measurement of antiproton to proton ratio.
No results yet.
Let me say we have two groups. And no publishable result. It's really very important to have all the young people into two different groups have a chance to talk to each other.
You might worry also about gamma ray bursts and magnetars producing a strange spectrum as well, not just pulsars.
What we want to do is, this is the first time people have a precise spectrometer.
Yeah.
We just want to very carefully measure everything without any prejudice. Because, as I mentioned, in the next 20, 30 years, probably it's difficult to build such a detector put in space. And it is really very important we don't make a mistake.
That's one thing that surprised me is when you said 20 to 30 years. I guess I've never thought of the space station continuing for 20 to 30 years. It's a very expensive thing. And so do you really think it'll continue for 20 to 30 years?
The space station at this moment, well, I don't know what happened today since the government closed.
They had to turn off the oxygen in the space station.
But the space station is supposed to stay till 2020. But the Europeans have said, look, we want to do it till 2028. So our detector has enough storage. So we use xenons and CO2s for 30 years.
So you said you confined yourself for 4 hours prior to the flight. If you had figured out that something's wrong, what would you have done? I mean, wasn't this the last chance to send it up? And
I would probably ask NASA to take us out of the shuttle and fix it.
But do you think they would have flown again?
No, but
the flight was only for AMS.
the flight is for AMS. So if I take it, many people will be very upset because there were 500,000 people want to visit the shuttle launch. But at that moment, my main concern is there something wrong? Right. Have I forgotten something? You can't worry about other people's opinions.
Well, there's money too, I guess.
I forgot to connect that wire.
Yeah. If it had delayed, it would have cost a lot more money too. Once it's that close to launch and then to take it back would have also cost NASA money, right?
Once you send to space, you cannot come back.
No, I meant if that launch had to be scrubbed at that point, the machine taken out, redone, and put back in, that would a large amount of dollars for NASA, right?
That was not my consideration.
Sure. It shouldn't be.
And, my main purpose is to make sure that I have not made a mistake.
I agree.
Made a mistake.
Yeah, I agree.
We have a question from the audience that was about comparing the AMS data to the Pamela data, and the question is what makes your error bars smaller, but the answer there is obviously statistics of events. But the big question I have is, in both the proton data and the helium data and Pamela, there's this discontinuous derivative, there's this hint of this inflection, and it was at similar energies for both. Do you think it was a systematic error? Do you have any idea what happened?
I have mentioned to my collaborator, never comment on other people's experiments.
I totally respect that. Thank you.
Yeah. I do want to mention two things. First, the detector is about 100 times larger. And second, the detector has many sub-detectors which correlate with each other. So you have many measurements you can match. But most important, before we went to space, we went to CERN test beam. So we know exactly what everything behaves. So in space, if something different, we will know. It's very important to always suspect you may make a mistake.
Another question from the audience, which I think gets at the ending of your talk, which was, what are your thoughts about our ability to continue to be curious and advance science?
I think the distinguished panelists in this table can answer more than me. Frank can answer that.
Well, I'm certainly still very curious, and I don't think human nature is changing. Yeah. But on the other hand, human motivations do change, and I think there are some disturbing developments in our country with tremendous rewards going to bright people who work in finance, who might have gone into physics, for instance, that I think are very unfortunate.
I think it's not actually some of us said that when there was the big financial crisis, it was really good because a lot of the potential people who go into finance would then do something useful. But I think there's another disturbance, which of course we've all lived through in particle physics, and part of the SSC was a problem too, is that in hard economic times, it's easy to point a finger. As Sam was pointing out, it's easy to make it seem as if physics at the forefront is useless, and it's easy to cut it, and it's a very small constituency. And the scientific community isn't single issue like abortion or something like that, so it's a very easy target. And it's really important, I think, for events like this, for the public to understand what the issues are, so that to maintain that level of curiosity and interest, and realize that at some level this is what society's all about.
But there's also the problem that although a lot of physics still can be done by relatively small groups in their own small laboratories. Some of these big questions are becoming monumentally expensive to solve. Like the next thing beyond the Large Hadron Collider is going to be just enormous. And we're continually worried about losing the James Webb Space Telescope if it gets cut. And the next thing beyond that will be enormous. And figuring out whether the dark energy really is or is not the cosmological constant is going to be enormously expensive.
And we have a built-in...
So we've got a problem.
In this country, we have a built-in problem that the SSC was approved by 3 presidents. I mean, every projects when they're approved, healthcare, can suddenly be stopped. And it's a real problem because every big project is going to take 20 years, and during 20 years, there are always going to be economic cycles. And if you have to keep approving a big project every year, you're virtually guaranteed this country is going to do nothing big.
And it ignores the whole argument about the economic spin-offs from science as well, which you can't ignore. I mean, what we've talked about has been the inspirational aspect, which is so important for getting people interested into science education, for becoming science literate, and that pays off all over society. But the spin-offs that we develop in the course of our experiments benefit society and economics and pay off long-term as well. And by not investing in that long-term scientific research, by not getting spin-offs like the web that just revolutionize the way that we shop, the way that we access information, the way we transact, well, we limit and we stunt ourselves. So it's important to take that into account as well.
And I'd like to say that an event like this and the turnout and the interest and enthusiasm is really an inspiration. And thank you. And we need more of this.
Yes.
Professor Gates.
I'm probably the member of this panel that has some of the greatest burdens in terms of policy recommendations around science these days. And one of the things, part of the reason why I asked my question to Professor Ting is because a number of us worry enormously about what is happening in our country in terms of its traditional support for science. Yes, we lost the SSC, but the truth of the matter is that recently, well, first of all, events like this are enormously important, and we commend our colleagues here at Gustavus for organizing these things. But the truth of the matter is that recently in our country, there have been rather clear signs that the support for science is diminishing. And it's diminishing for a very identifiable reason. Namely, that it's getting caught up in the political currents of the country, and the people who used to be amenable to supporting science are starting to change their minds. And so one of the things that is of utmost importance is that the scientific community itself recognize this change of environment, that we organize ourselves and our supporters, such as this wonderful audience here, to make sure that that there is a voice for fundamental science that will be heard in Washington. And this is not an easy task. And so the greatest challenge, I believe, will be not that we don't want to see our international colleagues join us, because we all believe that the distribution of intelligence and initiative is a normal bell curve everywhere in the world. It's not just confined to our country. But the truth of the matter is that unless we do some things in our society that get the message out about the value of science, we in fact stand in position to lose some of the already diminished support that is present in the country. On the occasion of my last visit to a Nobel conference, I commented that the cost of the SSC was about 3 to 4, maybe 5 B-2 bombers. And yet we lost it over that cost.
So let me second that, because like some of my colleagues, I spend a lot of time in other countries, and the thing that I observe time and time again is countries that are in the early and developing stage have placed tremendous emphasis on education science and technology, that they see that clearly as the route to becoming an advanced country, but every advanced country is taking it for granted that they have strong infrastructure, that they have good education, they have good science, and they're cutting the budget for those things as they're in financial difficulties, including Japan as an advanced country, even though Japan is better than some places. But all across the board, you're seeing all the advanced countries taking for granted that they're going to have leadership in education and science, and it doesn't happen. And so failing to understand the importance of education and science means you're going to cede the leadership of being a country that has a high standard of living and good health for its people, and generally all around good life that people from a liberal arts college would appreciate. And so it turns out to be much more critical than we think, because you look directly at the countries that are investing in their education and their science, and they're the ones that are progressing most rapidly. I mean, the correlation is so incredibly great. You look at the places where the high school kids are scoring very well, they're the ones where the economies are growing the best. It's the human capital, right? We might sell a lot of gas and oil in the United States, and some Middle East countries do, but it's the places that develop their human capital and make it work to a high level is that way. And science and technology is part of the tools that lead to the innovations and the things that make it so that you can have an advanced society that's prosperous.
And well, yeah. But I think it's appropriate, given that Professor Ting gave the talk, to mention that the other aspect of exciting, exotic physics at the forefront, which may not even, and I'm first to admit that it may not have any practical value. Certainly what I do doesn't. But it attracts the best and brightest students from around the world. And Professor Ting came to this country, and I came to this country from Canada because of the opportunities to pursue that. And not everyone's going to then go into particle physics, but they're going to go and maybe create a new company. And so being at the leading edge brings the best people in, and that's a really important, that this country has depended on that incredibly for its history. We don't, no.
I know we have a concert in about 20 minutes, so I think we're probably going to call the Q&A to an end now.
Yeah, I think we need to finish tonight. Just a couple housekeeping things really quickly. If you borrowed one of the iPads for captioning, please return that tonight so we can get it recharged so you can use it again tomorrow. And if you could clean up the area around where you've been seated, take all of your personal items with you, because this area will be cleaned tonight and the chairs reset. So please take things with you. The concert is in the chapel at 8:15. I hope to see you there. And we reconvene tomorrow morning with our first talk at 10 o'clock. Thank you.